Hello, 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 hello. Hello, hello, hello. Hello, 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 and welcome back, all of you. Can you hear me? Hello, all of you. Am I audible? Am I visible? That's great. So let's get started with the session. What are we going to see in today's session? We are going to complete the 12th class syllabus, and this is going to be the roadmap. How are you going to begin and what we are going to do? First of all, electrostatics, that means the basics of electric charges and field. After that, electric potential and capacitance, and after that, current electricity. So this is going to be the first half. We are going to cover till electrostatics and current electricity. Let's say somewhat about 7 or 7:15, 7:20 something. Okay. After that, we'll have the first break. After the break, magnetism, magnetic effect of current, magnetism and matter, electromagnetic induction. Okay. After that, we'll have a short break and then AC, ray optics, and after that the wave optics part and the modern physics. Yeah, some students are asking what about the remaining part of 11th class. So let me tell you that what is remaining: thermo, oscillation and waves. Okay, these three chapters were remaining, so it would cost us nearly something about 2.5 hours. Okay, so I'll be taking a separate session and you will be getting the notification in the community post. Okay, on the same channel, community post. Okay, please check the community post. I'll confirm the time and then I'll tell you that we are having this remaining portion session on might be tomorrow or day after tomorrow. Okay, so don't worry, we'll do that. So now we are beginning with the discussion of electrostatics. So first discussion is the discussion of charge. So let's get started. Okay, yeah, gravitation also. Mukesh will cover gravitation also in that session. So what is basically a charge? Charge is a property of matter. How do we define charge? Charge is a property of matter due to which it can attract or repel any other matter. Now how it does so, how charge does so, we know that if you talk about the charge, so there is a special property linked with a charge. That is the property of, tell me in the chat, what's that property? That's the property of electric field. That means if a charge is at rest, I hope you all know this, that if you talk about a charge, we classify the properties of charge in three categories depending upon the motion of charge. That means if a charge is at rest, quickly what it does, it generates electric field. I am writing short form, you please keep on writing. What it does, it generates electric field. If a charge is moving how? If a charge is moving with constant velocity, if a charge is moving with constant velocity, then along with the electric field there is also generation of which field? Electric field plus magnetic field. Okay, see, on this basic discussion that I'm telling now, on this small discussion, there was a question being asked in NEET. Okay, so please be very attentive. Please be very attentive. See, every small topic of 11th, I think 3 or 4 chapters which are remaining, Kavita, Venkatesh, everyone who is asking, I'm telling in general that we'll be covering it, might be tomorrow or day after tomorrow. So now focus on what I'm telling, okay, because it's going to be a very long session, might be 11 hours, might be 12 hours, okay, and we are going to cover 14 chapters in this marathon. So I want you to be mentally stable, okay, so just listen what I'm saying. So if you talk about the charge which is accelerated, okay, accelerated charge. So if a charge is under acceleration, oscillation, then what happens? Then it radiates electromagnetic radiations. It radiates electromagnetic waves. Okay. So if a charge is accelerated, it does what? It radiates energy. It radiates electromagnetic waves. You should know this. Okay. Basic discussion. Now, what are the properties of charge? How you define charge? You define charge as the property of matter. It's the property of matter due to which it can attract or repel any other matter, isn't it? Now we are saying that charge is always a scalar, it's always conserved, it's quantized, and it's invariant. So one by one I'm telling you the meaning. Charge is a scalar, that means you can do simple addition. If there is a charge of +3, if there is a charge of -2q, so the net charge you can say as plus 1q. Okay, that means 3 minus 2 simple 1q. Charge is conserved. That means if a body is giving charge to some other body, if two bodies in charge are being in contact, then what happens? Then the total charge of the system always remains constant. Charge can never be created, neither be destroyed. Charge is quantized. That means the amount of charge that you're going to get, the total charge that you're going to get, is always going to be an integral multiple of the smallest possible value of charge. And what is that smallest possible value of charge? All of you in the chat. That smallest possible value of charge is plus minus 1.6 into 10 to the power minus 19 coulomb. Sir, what is this value? Plus minus 1.6 into 10 to the power minus 19. This is the charge of, if you say minus, charge of electron. If you say plus, charge of proton. Okay, cool. After that, mass may increase or decrease during charging. Now, this is very important. Try to understand what I'm saying. This is very important, all of you. If this is body number 1, okay, if this is body number 1, this is body number 2. Let's say body number 1 is having greater amount of charge and it is having a greater potential. If you bring these two bodies in contact, this is having q1 charge, this is having q2 charge. Let's say some amount of charge from body 1 has transferred to the body 2. Which charge can transfer? Can protons transfer? No, only electrons can transfer. So let's say, just we are understanding in layman language, just let's think what I'm saying. Think about what I'm saying. Okay, these are some electrons. It had 1 0 0 0 0, this much number of electrons. So what this body A did, it transferred 50,000 electrons to the other body. What it did, it transferred 50,000 electrons to the other body. There is some mass associated with every electron. So don't you think that the mass of A has decreased and the mass of B has increased? Why? Question is why? Why it has happened? Because the body A has lost electrons. What the body A has done? The body A has lost certain amount of electrons and the body B has gained certain amount of electrons. Is this point very clear? Very basic point. I'm not taking a lot of time on this point. Let's take the discussion further. Charge is not possible without mass, but mass is possible without charge. This is plastic. It is having mass, but it is not charged. No net charge is there. But charge is not possible without mass. There cannot be charge without the possibility of mass. Okay. Specific charge is simply the ratio of charges to mass. 1 coulomb is this much ESU. Okay. This much ESU, another unit of charge. Specific charge we have written Q by M. Let's take the discussion ahead. Okay. So here we go. Mass may increase or decrease. You have said, you have seen, no worries. A very simple question coming in front of you. Read the question. Which of the following charge is not possible? What you need to do, the total charge should be n times of E. Okay. Should be n times of E. So I'm giving you 40 seconds for this question. This is the first question. A, B, C, D, E are the options. Read the questions and get started. All of you. Read the questions and get started. Quickly. Get started. I'm seeing the options. Quick. Fast, all of you. Be quick. Let's see what you do. Mohammad, Shafi, Divyanshu, Anubrata, Ria, Taj. All of you give the answer. Time up. See what the question says. Which of the following charge is not possible? He is asking not possible. Okay. So be very careful that what you need to check first of all. The total charge should be n times of E. If you talk about the first option A, that's simply 2.69 equal to n times of E. E is 1.6 into 10 to the power minus 19. So is this possible? Is this amount of charge possible? Is this amount of charge possible? Definitely yes. This is 2.69 divided by 1.6, isn't it? Into 10 to the power 19. That means there are n number of electrons. A lot of electrons are there, isn't it? A lot of electrons are there. Aditya Singh is saying that this is MR. See, everything is same, Mr. Aditya. The only difference is about the mode of communication. I hope that you understand this thing. So if you already know, then there's no need of being here. Rest of you who want to study, just give the answer. What is the point? How many number of electrons are going to be here? 2.69 divided by 1.6 into 10 to the power 9, 10 to the power 19. So this much amount of electrons are possible in the situation. Yes or no? Definitely. So A is correct. This is possible. 2 by 7 times Coulomb. Is this possible? Is this possible? Q equals to 2 by 7 C equals to N times of E. So how much is E? You can write N is 1.6 into 10 to the power minus 19 C. So this is also possible. N is going to be how much? That's going to be 2 divided by 7 into 1.6 into 10 to the power minus 19. If you calculate this is also a large number of electrons. So this is also possible. The C part. What is the C part? 1.8 E. See, what the quantization says, what the conservation says, that either you would get charge equal to E or 2E or 3E or 4E or 5E. 1.8 E. Not possible, because the smallest value is E. Simple. Okay. So this is not possible. You can calculate this. This is simply 3 times E. Okay. So every answer is possible except this one. So this is the answer. Okay. So let's take the discussion ahead. Here we go. Which of the following is not true about charge? Rest charge produces electric and magnetic field. Again, 30 seconds for this question. All of you. 30 seconds for this question. 3, 2, 1, and the time starts now. Read the question, get started. Read the question. I'm observing your answers. All of you. I'm observing your answers. Be fast. Let's see what you do. Quick. Quickly. Quick. Get started. Okay, time up. Now see, as I said, that if you talk about the properties of charge based upon its motion, so you know that if a charge is at rest, it generates what? It generates only electric field. If you talk about a charge which is moving with constant velocity, then along with the electric field, there is also magnetic field. Okay, yeah, that's cool. And after that, if you talk about the properties of a charge when it is accelerated, then what happens? Electromagnetic waves are being generated. So what you can say regarding the question, you can simply say that a rest charge produces electric and magnetic field. Yeah, that's true. That's okay. That's fine. Okay, this is true. Charge depends upon the speed of the body. Think about this. Charge is relativistically invariant. Write this point. Okay, all of you, sir and ma'am, write this point. What I'm saying, this is a very important point that I'm saying. Charge is very important statement I'm giving you. Okay, charge is relativistically invariant. Okay, that means it does not depend upon the velocity. That Q is independent. Okay, dependent of speed. Write it down. Okay, but mass depends. Okay, listen, mass depends. How? We know that m equals to m naught divided by root over 1 minus v square by c square. Okay, this is the concept of relativity. This is how the mass is going to vary if you vary the speed of the body. Okay, so this is important. Okay, IMP. Based upon this particular concept, there is being a question asked in NEET. I'll be giving that question. Okay, so yeah, let's come back to the point. Charge depends upon the speed of the body. No, it does not. So they are asking which option is not true. So this is not true. So this is going to be the answer, isn't it? Charge cannot be converted into energy and energy into mass. Now see what the option C says. Charge They are asking about wrong. Listen. They are asking about the wrong option. So is the first option correct? Rest charge produces electric and magnetic field. No, this is also false. Okay, this is also false. That means answer is true. They are asking that which statement is wrong. So first statement is wrong, and they are asking about the wrong statement. They are asking about not true. So yes, this is our answer. This is also our answer. Charge cannot be converted into energy and energy into mass. What is mass energy equivalence? Then what is mass energy equivalence? Isn't it? So this is also again a false statement. During charging, mass of the body increases. During charging, mass of the body increases. A, B, C, D, E. All of you, I want to see your answers in the chat. A, B, C, D, E. Madhu is saying A. Arjun is saying A. Shubham is saying A. What rest of you people are saying? All of you quickly. What all of you are saying? Give your answers in the chat. Fast. They are asking about the wrong statement. So yes, this is the wrong statement. This is also the wrong statement. This is also the wrong statement. During charging, mass of the body increases. Not always. Conduction, induction, friction. Not always. Okay, so this is also wrong statement. Oh. Bring your friend Sontu. Ask him what is the answer. He is confused. Mr. Sontu is confused. What is the answer, Mr. Sontu? Sontu is saying that the answer is E. Okay, so this is the answer. Let's take the discussion ahead. Here we go. Some questions. These are a bit early. We'll do these questions after the topic. Just they are misplaced. Don't worry. Okay. So we have seen regarding the charge. They are scalar, quantized, conserved, invariant. Okay. Unit Coulomb, ESU, Franklin, EMU. Okay. Now see, methods of charging. We are talking about the methods of charging. So there are three methods of charging. Charging by friction, charging by induction, and charging by conduction. Simple. What is charging by friction? That means you actually have to rub two bodies. Okay. You might have seen that if this is a, let's say you have pieces of paper. Okay. Let's say you have small pieces of paper and this is comb. So what do? You rub the comb on your hair and bring the comb near the paper. So what happens? It gets stick to the comb. Okay. Have you done this? Have you people done this sometime? Or what you can do, you can take balloon. Okay. Just take a balloon, inflated balloon, and rub that balloon against any object and then bring it closer to the flow of water. Let's say there is a stream of water. You bring it, the water gets attracted to the balloon. Why it happens? It happens because of the charging, and this charging is due to the friction. Okay. After that, induction. See, there's a very interesting example of induction. I'm giving you, listen. Let's say this is an object. Okay. And you bring a negatively charged rod closer to this object. This rod is negatively charged. And this is a neutral object. What kind of object is it? It's a neutral object. Now imagine that you are in college, and in your college, any of the good actress has, visited. Might be Katrina Kaif or Kiara Advani, whomever you like. Okay. So let's say this is that actress. Okay. Or let's say this is positively charged. You are in the college. Okay. There's a function, and some actress or some celebrity has came over there. So what will happen? All the boys are going to run over there at one side, isn't it? And all the girls are sitting on the other side, something like this. See, all the boys went over there to see that who has came. All the girls are sitting because they don't consider themselves less to that celebrity. Okay. So all the girls are this side, all the boys have shifted that side. So now what has happened? Charge redistribution has happened. Yeah, Samantha, let's take Samantha. Okay, no worries. So whoever has came, okay, that makes no difference. Try to understand the point. So all the boys went one side, all the girls are sitting on the other side. Now what can happen if you earth this system? Okay, if you earth this system, then what's going to happen? Then all the charge, then there's going to be a transfer of negative charge from earth to this particular body, and you are going to get this whole positive charge is going to get, okay, vanished. Then you are going to get this negative charge on the system redistributed, something like this. Have you even touched the body? Have you even touched the negative rod to this body? Definitely no. Still you are getting charge. What kind of method is this? This is what we call as the induction. This is what we call as the induction. Okay. So opposite and equal charges may be lesser. Equal and opposite charges are generated due to friction, because if this is one body, let's say this is a charged body, this is a charged body, okay, and you are rubbing this body to a neutral body, you are rubbing two bodies. So what's going to happen? Some charge is going to get transferred from A to the body B. Okay, equal and opposite charges in friction. If you talk about induction, opposite charges, okay, and equal or maybe lesser. If you talk about conduction, then conduction is simply the touching process. Okay, if you touch this rod to this body, then there would be transfer due to the conduction. Okay, let's take the discussion further. Here we go. Now we are talking about the Coulomb's law. Now this is very interesting. Let's say you need to calculate. Who want to sit on the charges? Let's say we have Tulendra and we have Venkatesan. So this is Mr. Tulendra, this is Mr. Venkatesan sitting over two charges. Let's say this charge is Q1 and this charge is Q2. Okay. So this is Tulendra, this is Venkatesan. Okay. So let's say both these charges are positive. So what's going to happen? There is going to be repulsion, because we know that if you talk about like charges, they do what? They repel. If you talk about unlike charges, they do what? They attract, isn't it? So if these are like charges, they are going to repel, and what is going to happen? They are going to repel equal opposite. The force of repulsion between the two charges is going to depend upon the magnitude of the individual charges and is going to be inversely proportional to the square of the separation between the two charges, isn't it? So if you remove the proportionality, this is going to be F equals to K times of Q1, Q2 divided by R square. Sir, what is K? K is nothing but 1 upon 4 pi epsilon naught. Okay. What is going to be the value of K? That's going to be 9 into 10 to the power 9. Sir, what is going to be the unit? If you talk about the unit of K, the unit of K is going to be Newton meter square per Coulomb square. Newton meter square per Coulomb square. Okay. Sir, what is epsilon naught? Epsilon naught is the permittivity of any given medium. Okay. Listen. Epsilon naught is the permittivity of medium. Now, what's the basic difference between electrostatic force and the gravitational force? If I talk about electrostatic force, see, if let's say these are the two charges. Charge number 1, charge number 2. Okay. If you keep these charges at some separation, they are going to attract or repel. Let's say the separation is same. You have placed these charges in water or in kerosene or in alcohol. No alcohol. Let's say you have placed these charges initially they were in air. Now you have placed them under water. So is the amount of attraction or repulsion, whatever that is it going to change or not? Definitely it's going to change. Why is it going to change? It's going to change because of this parameter that's involved over here. Over here. This is permittivity. Permittivity. This means the tendency of a medium to permit the electric field within it. Okay. And for different mediums, it is different. And remember the relation, relative permittivity is permittivity of medium divided by the permittivity of free space. So if you say that the charges Q1 and Q2 are placed in a medium, if the charges Q1 and Q2 are placed in a medium of permittivity epsilon m, then the force is going to be 1 upon 4 pi epsilon m Q1 Q2 divided by R square. So you can clearly see that this epsilon m, what can I write about the epsilon m? We can say that epsilon relative permittivity is permittivity of medium upon permittivity of vacuum. So epsilon m can be epsilon r into epsilon naught. So f dash is going to be 1 upon 4 pi epsilon naught epsilon r Q1 Q2 divided by R square, isn't it? Definitely yes. So can you find out the relation between the initial force and the new force, definitely yes, you can say F dash is F divided by epsilon R. Very important relation, very important discussion. Have a look at this. Have a look at this quickly. All of you, have a look at this. Fast, fast, fast. Yeah, so what are we saying? We are talking about the electrostatic force. What is important regarding the electrostatic force? It is a conservative force. What is a conservative force? A force whose work done is independent of the path. What am I saying? I'm writing in short. Work done by the conservative force is independent of the path. Okay, this is what we call as the conservative force. It's a central force, that means it acts center to center. It's a long ranging force. It obeys inverse square law. It is medium dependent. Every single point is very important. I hope that this point is absolutely clear. Okay, K Q1 Q2, K Q1 Q2 divided by R square. F dash or F medium is simply F divided by K. You can also write K, you can also write epsilon R. Okay, K is nothing but epsilon R. Call it dielectric constant, call it the relative permittivity, makes no difference. Okay, so let's take the discussion ahead. Are you all having a good time? Okay, are you enjoying? That's very important. Okay, just enjoy the concepts. Let's take the discussion further. Okay, so we'll be covering every single thing, no need to worry. Vector form. What is the vector form? Now see, if you have two charges placed at some separation, let's say this is the charge number 1 Q1, this is the charge number 2 Q2. Okay, so this is charge number 1, and the line joining the origin to this point is what we call as the position vector. What do we call it? We call it as the position vector. Okay, so this is the position vector R1, this is the position vector R2. Okay, see, I'm giving you a very short question. Okay, very simple question I'm asking you. Just tell me that there are two charges. Okay, there are two charges. Listen very carefully, listen. This is a question of 500 rupees. Okay, I'm not going to give you 500 rupees. The one who is going to give wrong answer is going to pay us back. Okay, so let's say this is a charge of 10 coulomb and this is a charge of 1000 coulomb. Okay, so this is body number A, this is body number B. Who wants to sit on body number A? Who wants to sit on body number A? Let's say Vivek is sitting on the body number A. We are making Vivek sit on the body number A. This is Mr. Vivek sitting over here. Okay, and this is who wants to sit on the B? Let's say Riya is sitting on the body number B. Riya is sitting on the body number B. Okay, now the point is that which of the following options is correct? The force on A due to B, the force experienced by A due to B is going to be greater than the force experienced by B due to A. Force experienced by B due to A is going to be greater than the force experienced by A due to B. FAB equals to FBA. D option, we don't know. Then who knows? Mr. Sontu knows. Where is Sontu? He is standing over here with a blank face. What is the answer? A, B, C, D, A, B, C, D, A, B, C, D. Quickly. ABCD, ABCD, ABCD. Answer quickly. Quick. What is going to be the answer? See, this is the property of Coulomb's force. This is the property of Coulomb's law, that the forces that you're talking, okay, the force that you're talking about, it always acts equal and opposite no matter what the charges are. Okay, it always acts equal opposite. That means the force experienced by Vivek due to Riya equals the force experienced by Riya due to Vivek. Okay, no matter what happens, it's going to be FBA equal to FAB. Okay, magnitude. Okay, let's take a magnitude over here because the directions are going to be opposite, equal and opposite. Okay. See, now the point is, what's the point? The point is that you need to find out the relation in vector form. Okay. So if you are sitting on any one of the charge and you want to calculate the force due to the other charge, okay, sit on one charge and calculate the force due to the other charge. So definitely it's going to be along the green line, yes or no? The force experienced by 1 due to 2 is going to be over here, over there, like this and this. Force experienced by 1 due to 2, if the charges are equal, if the charges are of same nature, they are going to repel, na? So force on 1 due to 2 is repulsive. Force on 2 due to 1 is repulsive over there. So one over here, another over there. So one here, another there. Okay, something like this. Getting the point? That means the force is going to be along this line. So what is this line? This is R12. Okay, the position vector joining 1, 2. And how do we represent direction? How do we? Who is this? Rushi Bachkar. How are you, Riya? How are you, Riya? Rose. मम्मी को बताता हूँ अभी. I'm telling your mom, telling your parents, see what he is doing. 2 दिन बाद एग्जाम है. You having exam after 2 days, ना? What are you doing? You want flying chappal? No flying chappal? Study quietly. Don't do all this. Listen, all of you, what I'm saying. R12, this is the position vector. Okay, this is the position vector. Now listen. So the force is going to be F equal to KQ1 Q2 divided by R square. And what's going to be the direction? The direction is going to be R cap. The direction is going to be R cap. Okay, direction is going to be R cap. Something like this. What is R cap? R cap is the position vector. Position vector is nothing but the vector divided by its own magnitude. So you get the same formula, something like this. Or you can also write the formula. As K Q1 Q2 divided by R cube, and this is R vector. Okay, let's write it as R12, and this is R12 magnitude whole cube. Is this point very clear? Okay, let's take the discussion ahead. Okay. Before this, electric field. So what basically electric field is? We know that when the charge is at rest, it has the property, it generates what? It generates electric field. Okay. Electric field. Listen very carefully. Electric field. What actually it is? It is the property due to which a charge can attract or repel any other charge. A charge can attract or repel any other charge. Okay. Due to its property of electric field. Listen now. If you keep another charge in its vicinity, what is vicinity? Vicinity means its neighborhood. Okay. If you keep another charge over here, okay, this is going to either attract or repel. So how do you measure this? You measure it as the force experienced by a unit charge. Who is this? Go and stand over here. You are standing over here. Okay, you are standing over here. This is what? This is a unit charge, test charge, unit charge. Okay, force experienced by a unit charge is nothing but field. Okay, you know, if you talk about an infinite wire, what is basically the infinite wire? We apply the Gauss's law and find out this relation. I hope you remember the relation. All of you, how many of you remember the relation? We find out something like this, applying the Gauss's law, like this. The electric field lines are coming out. Are you remembering this expression? Do you remember this expression? Infinite charged wire. All of you. Infinitely charged wire. What is the relation for infinite charged wire? That's nothing but what? How do we find it out? We can simply find it out using the expression phi equals integral E dot ds equal to q by epsilon naught, isn't it? And what is lambda? Lambda is nothing but the charge experienced on a unit charge. Sorry, lambda is nothing but charge per unit length. Okay, substituting these values over there, you get E equals to 2k lambda divided by R. Isn't it? How many of you remember this? How many of you remember this? 2k lambda by R. Okay, so E equals to 2k lambda by R. I am putting it in a dabba. I am putting it in a bracket. Okay, put it over here, something like this. Apart from this, if you talk about the electric field on the axis of a ring, so remember what is basically the ring. This is the ring. This is a ring. And what is the axis of a ring? This over here is the axis of the ring. Okay, this is the axis of the ring. Go and stand on the axis. Let's say you are standing over here. Let's say you are standing over here. This is a charged ring. It can either be positively charged, it can either be positively charged, or it can either be negatively charged. Something like this. Something like this. These are going to be the forces. Okay, these are going to be the forces. Now listen very carefully, all of you. So the net field is going to be along this direction. Yes or no? Who is this? This is your friend Sontu. Ask Mr. Sontu, where is the field? He's saying that the field is over there. So what is the value of the field? How can you remember this expression? The way I remember, just listen. If you talk about the electric field, if you talk about the electric field at the center of the ring, all of you, how much is going to be the electric field at the center? How much is going to be the electric field at the center? All of you quickly in the chat, fast. How much is going to be the electric field at the center? If you are talking about a charged ring, okay, if you are talking about a charged ring, let's say you are standing at the center. So what is going to happen? Equal opposite repulsion from every side. That means E at the center, E at the center is going to be 0. Yes or no? That's cool. Very nice. If you talk about electric field at some point P, okay, at some distance X, let's say that the radius is R, call it X, call it A, makes no difference. So electric field is going to be how much? Electric field is going to be how much? This much. How much? See, A Q X upon R square plus X square to the power 3 by 2. If you substitute X equal to 0, if you substitute X equal to 0 into the same expression, you get the answer as 0. If you substitute X equal to 0 into the same expression, you get the answer to be 0. Okay, so just remember this formula is applicable to both of the systems. I hope that the point is absolutely clear. Okay, let's take the discussion ahead. Here we go. Here we go. Here we go. Here we go. If you talk about a dipole, sir, what is a dipole? First of all, a dipole is a system of equal opposite charges. Okay, let's write about dipole. Let's write about dipole. Minus Q plus Q. Okay, equal opposite charges separated by some distance D. So sir, what is the dipole moment? Dipole moment is simply the magnitude of charge into the separation. Okay, is it a scalar quantity or a vector quantity? It's a vector quantity. If it's a vector quantity, what is going to be the direction? The direction is always from negative charge to positive charge. Okay, the direction is always from negative charge to the positive charge. Okay, what is Deepanshu saying? Sir जी, अगर एक conducting sphere में equal magnitude के दो opposite charges हैं तो शांति रखना यार, अभी करेंगे अभी सारी बातें, अभी सुनते चलो. Listen, direction is always from negative to positive. What is going to be the unit? What is going to be the unit? Unit is going to be charge, coulomb into meter. Okay, so this is the dipole moment. Now there are two systems. One is the axial system and another is the equatorial okay system. Equatorial system, axial system and the equatorial system. Now listen, what is the axial system? If these are the two charges, minus Q and plus Q, okay, and you are talking at some, who wants to go and sit on that point? Who wants to go and sit on that point? Let's say we are taking, who wants to go? We are taking Praveen. Let's take Praveen. Okay, this time. So Praveen is standing over here. Mr. Praveen is standing over here. Okay. So you are measuring, first of all, listen, you are measuring the distance from the point P. Okay. Let's say you need to find out the dipole moment at this point where this person is standing. So you are measuring from the center. of the dipole. This distance is r. What is the distance? This distance is r. Okay. Now listen, this is minus q, this is plus q. So one separation is this much, another separation is this much. How much is going to be the electric field? First of all, what's going to be the direction? I want you to think about the direction. Hello, all of you. Can you listen? Some students are just sending hearts, but they are not giving the answer. So give the answer. Okay. So. Kundan, I'm taking the questions of JEE and NEET both. Don't worry. What is going to be the direction? What is going to be the direction? Due to minus q, it's going to be attractive. Due to plus q, it's going to be repulsive. But definitely, the electric field of whom is going to be greater? Of the charge number 1 or of the charge number 2? Electric field of charge 1 and charge 2, who is greater? Electric field due to charge 1 is E1, electric field due to charge 2 is E2. Whose value is going to be greater, E1 or E2? Simply answer what I'm saying. E1 is greater or E2 is greater? Quick. Fast. Who is going to be greater? E1 and E2, who is going to be greater? Definitely the field due to 2 is greater because the distance is lesser. So the net electric field at the axial point, very important discussion. Very important discussion. Net electric field is going to be along this direction. What is the direction of net dipole moment? It is also along this direction. Therefore, we get a positive over here. Okay. Okay. All of you. If you talk about the equatorial position, now listen. This is minus q. This is plus q. This is the equatorial line. This is the point P where you need to find out. So due to minus, it's attractive. Due to minus, it's what? It's attractive. Yes. Due to minus, it's attractive. Due to plus, it's repulsive. So the net field is going to be along which direction? I'm just asking about the direction. This is the direction of net field. This. Preeti is saying, please go slowly. Preeti, last time what happened that we were studying till 3:30 in the night and still the syllabus was not finished. I want to finish the complete syllabus today. Nahi re baba. We have to go fast. Okay. ऐसा कैसा गुंडा बनने का रे तू? So this is the net field. ऐसा कैसा डॉक्टर बनेगा रे तू? So this is P. Okay, this is P, this is E. E net, P net. Okay, is this point very clear? So this is going to be opposite direction. This is the opposite direction. E and P are in the opposite direction. That means there is going to be a negative. There is going to be in the negative. Okay. So this is minus. Okay. Minus of Kp by R cube. Minus of Kp by R cube. You have to remember these points. Very important points. Okay. These are very important points. I hope that you're going to remember these points. So let's take the discussion ahead. After that, the hollow non-conducting sphere. If you have a shell, all of you, if you have a shell, go and sit inside the shell. Who want to go inside the shell? Who wants to get inside the shell? Who wants to get inside the shell? Let's take Sashmita Raut. Sashmita is inside the shell. Okay. Sashmita is inside the shell. So tell me one thing. That what are going to be the different forces acting on you? The forces are going to be along every possible direction. Let's say this is a charged conducting sphere. Okay. So on this particular person, on Sasmita, every possible direction is going to be, okay, there are going to be forces on every possible direction in equal opposite sense. Okay. So the net force, net field inside the shell is going to be always 0. Okay. If you talk about the surface, so when you are at the surface, you consider whole of the charge to be concentrated at the center. So at the surface, it's simply kq by r square. And if you come outside the shell, If you come outside the shell, okay, this is you standing over here, okay, this is you standing over here. So what you need to do, you need to take the separation from the center, okay. That means what? E inversely proportional to r square. So if we talk about the graph, E is 0, E is 0 up till what point? Up till surface. So at the surface, E is maximum, and after that, E inversely proportional to r square. I hope that this point is absolutely clear. Shobna Sisodia is asking, sir, aap kya padha rahe ho? Beta, this is home science. I was teaching how to make tea. You know tea, chai. So what we need to do, first we need to take water, then we need to take some air, then we need to mix water and air, and then tea would be, you know, prepared. Try this at home. Okay, bye bye. Now listen. 1.5 घंटा हो गया. After this, people are asking, what are you teaching? Which subject are you teaching? Very nice, very nice, very nice. Oh my God. So this is non-conducting solid sphere. Let's talk about a non-conducting solid sphere. Okay. So if you talk about a non-conducting solid sphere, this is a non-conducting solid sphere. This is a non-conducting solid sphere. So what is the point with this solid sphere? It is having charge distributed throughout the volume. Okay. So if you talk about any given point, let's say you are talking about any point. Okay. You are standing over here. You are standing over here at this point. You are standing over here at this point. Then what happens? You need to find out the value of field at this point. That means inside. Then you are going to go and stand over here at this point on the surface, and then you're going to come out. Then you're going to come out. Okay. Then you're going to come out. People are saying, Hindi mein bhi kuch dijiye. What do you want in Hindi? Samosa? Vada pav? Hindi mein bhi kuch dijiye. Listen. Sorry. Sorry. Don't distract me, okay, all of you, quite. So what I was saying, this is a solid sphere. So you need to find out the net electric field at different locations. So just remember, you don't need to go through the derivation. Just remember these 3 points. That the main thing is that what is the electric field inside. So electric field inside, this region is inside, this region is outside, this is on the surface. Definitely electric field on the surface is maximum. Okay, if you talk about inside, then inside E is proportional to R. Electric field is proportional to R. So if you come on the surface from inside, then definitely it's going to increase. So this is going to be the graph, okay, proportional to R. This is KQ by R square and inversely proportional to R square. So I hope that this point is absolutely clear. So here we go. Electric field due to a plate conducting. Now see, I'm giving you very important discussion over here. This is very important. Okay, I'm not saying this. Who is this? Who is this? Tell me, who is this? What is the name of this person? Who is this? See, thin sheet, thick sheet. Okay, this is also called conducting sheet. This is also called conducting sheet. Okay, this is also called conducting sheet. Conducting. Okay, this is also called conducting sheet. Listen. You forgot him. This is your friend, Sontu. People are saying me, not you. This is Sontu. Okay, so Mr. Sontu is saying. What is he saying? He is saying that if you talk about a thin sheet, let's say this is a thin conducting sheet, something like this. Okay. So what is going to happen over here? There is going to be electric field throughout. How is going to be the electric field? This is going to be the direction of the electric field. Okay. So what kind of system are you going to take? What kind of system are you going to take? Okay, just a second. Yeah. What kind of Gaussian system are you going to take? What kind of Gaussian surface are you going to take? Take a cylinder, something like this. Take a cylinder, something like this. Okay. So how many surfaces are there? There is surface number 1. There is surface number 2. And there is this curved surface. There is this curved surface. There is this curved surface. Curved surface. Okay. Something like this. Now see, the expression for electric field over here turns out to be E equals to sigma divided by 2 epsilon naught. Just remember that if it is a thin sheet, there are going to be 2 surfaces from which you are going to get the net flux. Therefore, it's going to be 2 over here in the denominator. Now, if you talk about a thick sheet, or a conductor, something like this, okay? Let's say this is a charged thick sheet. Okay. Okay, something like this. This is the electric field. Okay, so there is only one surface due to which there is going to be the electric field. How much is going to be the electric field? That's going to be sigma divided by epsilon naught. Remember this point. This is very important. Is this point very clear? Is this point very clear? All of you? Done. Let's take the discussion ahead. Okay, so sigma by epsilon naught, sigma by 2 epsilon naught. Okay. Okay. Now another discussion, torque and the potential energy on a dipole. If you talk about a dipole, listen. First of all, question. If this is the dipole, okay, and in the second situation, this is the dipole, okay, this is the dipole, case number 1, listen, case number 1, case number 2, very carefully listen the question. 1,000 rupees for this question. I'm not going to pay. The one who gives wrong answer is going to pay me. How much? 1,000 rupees. 1,000 rupees only. Okay, I'll give my Paytm number. You have to transfer that amount. Okay. So this is this is case number 1, and this is case number 2. Case number 1, case number 2. Okay. So there is electric field. There is electric field. Something like this. Electric field. This is the electric field. This is the electric field. Like this. Okay. Cool. So. First option. Force in the first case and force in the second case, both are 0. Force in the first case 0. Force in the second case not equal to 0. Force in the first case not equal to 0. Force in the second case equal to 0. Force in the first case, force in the second case, both are 0. And the D option, pay me 1,000 rupees. And the D option, pay me 1,000 rupees. Quickly. A B C D. Tell me. Oh God. One more question. Quickly. What is going to be the answer? Quickly, all of you. Fast. See. No, I'm not saying that the answer is C. I'm saying C over here. Look over here. What I'm saying, if this is the first case, what is going to be the direction of force? If this is the field, this is going to be the force F equal to QE. And this is going to be the force F equal to QE. Yes or no? So what is the net force? What is the net force in the first situation? F net is going to be plus QE minus QE. That is 0. Similarly, in this situation, plus QE minus QE, net force is always going to be 0. So the answer is C. Mukesh will pay me 1,000 rupees quickly. Mr. Mukesh, give me. And everyone who has, Ria is also going to pay me 1,000 rupees. Miss Ria, be fast. Okay, so here we go. This was regarding the force. So what we have said that the net force on a dipole placed in uniform electric field. This point is very important. Uniform electric field is always equal to 0. I hope that this point is absolutely clear. So here we go. See, you're talking about the torque. What is torque? Listen. Torque is simply force into perpendicular separation. F is equal to Q times of E. So if you substitute, you get P cross E. That means tau equals to PE sine of theta. That means P cross E. Important discussion. If the angle is 0, torque is 0. Simple. If the angle is 0, sine 0, 0, torque is 0. Okay. If there is torque, if you're doing certain amount of work in the situation, where that work goes, let's say this is a dabba. Okay, this is a black coffee. If I do certain amount of work on this glass, this is energetic black coffee because it is having energy now. Normal black coffee, energetic black coffee. Why? Because I have done certain amount of work in raising the energy of the system. Therefore, the work that I have done is going to get stored in the form of potential energy. Yes or no? Yes or no? Tell me quickly. The work that I'm doing is going to get stored in the form of energy. Okay, that's fine. So this is going to be the expression. If the angle is 90 degrees, simply torque equal to PE. If you talk about the potential energy, so potential energy is minus of P dot E. That means PE cos of theta. Okay, PE cos of theta. Now let me tell you the stable, unstable, and neutral equilibrium. Listen very carefully. Listen, all of you. The three cases. Very fast. See, if this is the electric field, okay, E, and you have tilted the dipole in this direction. You have tilted the dipole along this direction. Okay. Now tell me, you have tilted it anti-clockwise. So what are the directions of forces acting? This is one force. This is another force. Where the force wants to bring it back, something like this. Yes or no? The force wants to bring it back in the original position. So this is the case of stable equilibrium. Okay, that's fine. But what if I rotate the system in the opposite sense? What if I rotate the system in the opposite sense? That means I am rotating the system. Along this direction. Okay. That means I have rotated the system along clockwise direction. Okay. So what is the force acting over here? Something like this. And the force, just a second. The force acting on minus Q over here, the force acting on plus Q over here. It's never going to come back to the original position. It's going to tilt in the opposite sense. So this is unstable. Okay, simply. And what is neutral equilibrium? That means, let's say that the dipole was placed. See, I'm just giving a rough example. If this is a bowl, this is a marble, you displace the marble, it comes back. This is the stable equilibrium. This situation is the unstable equilibrium. And you just displace the marble, it comes from position A to position B. Everything looks exactly the same. This is what we call as the neutral equilibrium. So now the point is that you need to remember the expression for the torque as well as the potential energy. Okay. So let's take the discussion further. If we talk about the properties of electric field lines quickly, if this is positive charge, this is the negative charge. So what are the electric field lines? They are the lines coming out radially from the positive charge, or the lines going in radially, something like this. This is what we call as the electric field lines, isn't it? So these are imaginary lines. Actually, are there some lines? Let's say I have a charge. I was walking. This is a charge. This is Mr. Sontu. Mr. Sontu was walking. He was walking. This is the electric field. Electric field lines came. Mr. Sontu got hit from the electric field lines. He fell down the ground. Have you ever seen this situation? Does it happen? Definitely no. That means these are what? These are imaginary lines. Okay. Tangent to these lines gives you the direction for the force. Okay. Tangent dropped along the curves gives you the direction to the force. Continuous, differentiable, continuously differentiable functions, they are always directed from positive to negative, does not form closed loop. Electric field lines never form closed loop. Okay. They can never intersect. Why two electric field lines can never intersect? Listen. Why two electric field lines can never intersect? Because if two lines are intersecting, the tangent drops gives you the direction of the electric field line. Okay, gives the direction of the force acting on a charge. So that charge, if two lines are intersecting, let's say this and this, so you're going to have two tangents at that point. Okay, that means the particle is going where? If you keep a charge over here Q, so the charge is going to get along this direction or that direction. That's the confusion. Oh. This is not possible. So they cannot intersect. Okay. So greater the amount of charge, greater the number of field lines. Okay. Let's say this is one charge. This is charge number 1. Okay. This is charge number 1. This is charge number 1. Okay. And see, this is charge number 1 and this is charge number 2. 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 Which is having a greater magnitude? Definitely the charge along with greater field lines are associated is having a greater magnitude. Yes or no? Quickly. Yes. So this is cool. Inside a conductor, electric field lines are always zero. This is very important. Okay. Electric field inside conductor is how much? Is always zero. So let's take a conductor. Okay, this is a charged conductor and this is a cavity inside the conductor. Let's draw it properly. Okay, this is a cavity inside a conductor. Let's again draw it properly. Okay, this is the cavity inside a conductor. Okay, now what happened? You applied an external electric field over here, something like this. So what is going to happen? We know that in a conductor there are n number of free electrons. Parveen V, what happened? Are you gone mad? What are you writing? Venkatesh, Parveen, what are you doing? यहाँ देखो सामने, focus over here. What are you doing? What are you writing? Wali Mai update. What update? See what I'm saying? If this is a conductor, this is the electric field. Remember the example of that Samantha, Kiara Advani, whoever came in the college. So what's going to happen? All the electrons are going to settle on the one side. All the positive charge you're going to observe on the other side. So there is going to be an induced electric field in this situation. Now if you talk about the net electric field, who wants to go and get inside that, stand inside that particular system? Let's take Gangadhar, Mr. Gangadhar. Okay, or let's take Mr. Shaktiman. So he is standing over here, something like this. So ask him that what is the net field over there. So what is he going to say? He is going to say, okay, you're talking about the net field. Oh ho, E net. E net is nothing but E external, okay, and E internal. the vector sum of E external and E internal, but that turns out to be 0. Why? Because the induced field is going to be equal and opposite to that of the external field. Okay, the magnitude of induced field is equal and that's opposite to the direction of induced to the external field. That's why E inside is 0. Okay, so let's take the discussion ahead. Here we go. Okay, so electric field lines are always perpendicular to the conducting surface. Very important point. Another important point I'm going to explain you. Electric field lines are always perpendicular to the surface. Let's say this is a conductor. This is a conductor. Okay, listen, first point, any charge that you place at the center of the conductor, any charge you place inside a conductor comes at the surface of the conductor. Okay, any charge you place inside a conductor comes at the surface of the conductor. How? Something like this. See, this is charge. Let's bring the charge. This is charge. Let's bring the charge. This is plus Q. What is this? This is induced negative charge. And what is going to happen? The whole positive charge has came at the surface of the conductor. So first point, any charge that you place inside the conductor is going to come on the surface of the conductor. Very important point. Okay, very important point. So remember that whatever charge you place at the surface of the conductor is going to reside at the surface. What I'm saying, any charge placed inside conductor resides. Okay, resides where? Resides where? Resides at the surface. Resides at the surface. Wow. Okay. Next point, that the electric field lines are always perpendicular to the surface. Electric field lines are always perpendicular to the surface. Okay. See, next point I'm writing. Important points. First point I've written. Second point I'm writing. Electric field lines. Write it in your words. Okay. Electric field lines are always perpendicular to the surface of whom? Surface of the conductor. Surface of the conductor. Okay. Now you know that what is basically the work done. Work done is nothing but integral of F dot dr. Okay. So we can write, let it be. Okay. We'll discuss this after some time. Come over here. Come back. So this is the point that I have given. It's proportional. It's perpendicular to the surface. Okay, that's cool. After that, electric field intensity. Electric field intensity is inversely proportional to the spacing between the lines. Greater the strength of the charge, greater the intensity of the field, closely packed it would be. Okay, closely packed it would be. Okay, yeah. Come back to the point. Come back to the discussion. Now see. If we talk about the charges placed in electric field, so different situations we have. Have a look over here. This is the first situation. Okay. So if you place a positive charge, go and sit on this charge. Okay. This is the electric field. So positive charge is going to experience a repulsive force. If I am a positive charge, this is the electric field. I am going to get repelled over here. Okay. Something like this, isn't it? Definitely yes. If this is a negative charge, go and sit on the negative charge. See, who is this? Who is that person sitting over there on the negative charge? This is the electric field. He is going to experience an attractive force in this direction. That's cool. Okay, that's fine. Okay. Now what? If you talk about the acceleration, second point. So basically, what is acceleration? Acceleration is nothing but force divided by mass. Force is nothing but QE divided by the mass. So acceleration is QE divided by m. So this is the acceleration. Okay, that's fine. Okay, that's fine. If you talk about this situation in which you have a pendulum, okay, let's say you have a pendulum. See, if we talk about a pendulum, okay, place this pendulum in an electric field. Listen very carefully. Everything I'm deriving in front of you, okay, every important point. You are not going to get the question paper out of these notes. This is my guarantee to you. Okay, you are not going to get even a single question which is not mentioned in these notes. Okay, after the exam of NEET and JEE means, you can simply sit and observe that what all we have seen and what all has been asked. That's going to be exactly same. So now it's up to you that how much you can take from the discussion. Okay, no Sriram, we are not going to forget the Gauss's law, don't worry. Now see, yeah, if you talk about the pendulum, so let's say this is a charge Q, okay, mass M, electric field E, this is the electric field E. Okay, so what is going to be the force acting over here? This is going to be F equal to QE. This is going to be F equal to QE. Okay, F equal to QE, and this is going to be another force acting over here. This is going to be another force acting over here. Who is this commenting here? Praveen, you mad or what? Don't do this nonsense, okay? Continuously you are just spamming. What is this? Behave like good people. Okay. Stop doing this, whatever you're doing this, spamming and all. A lot of students who are studying. So maintain some decorum. Maintain your image. It doesn't mean that no one is watching you, no one is standing in front of you, so you're going to comment anything. Is this how you are going to behave in an offline class? What is this? Okay, all of you come back. Anyone who is going to do all this nonsense, okay, just think once that there are some people who are studying and who are dependent upon the discussion. It might not make a big difference in your life. Okay, not everyone is a doctor or an engineer. Okay, and I don't expect everyone to be doctors or engineers, but you have to be at least a good citizen of this nation. Okay, be a good person. It's not important to be something, very great, but just be a good person. That's the first and most important thing. Okay, now let's get back to the point. What are the forces acting over here? This is QE, this is mg. QE and this is mg. QE and this is mg. Now listen. So what are we saying? What is going to be the angle? Let's say this angle is theta. This angle is theta over here. Okay. So this angle is theta. This angle is also theta. Okay. So if I complete the triangle, I can say this is QE, this is mg, this angle is theta. So what is going to be tan theta? Tan theta is nothing but opposite upon base. That means QE divided by mg. QE divided by mg. Tan of angle theta is equal to QE divided by mg. So this is the expression in front of you. This is the expression in front of you, okay, for tan theta. Okay, that's fine. Now let's say this is the general situation. This is normal pendulum which is kept. But what if the pendulum was oscillating and you have applied an electric field? So definitely there is going to be some change in the time period, isn't it? Let's say this is the pendulum, third case. This is the electric field you have applied. Okay, that's fine. So what is going to be the net acceleration? Net acceleration A net is going to be net force. That means mg plus QE divided by the mass. Force divided by the mass. So this is going to be force divided by the mass. So this is going to be the net acceleration. Substitute the net acceleration. T equal to 2 pi under root of L by G. T equal to 2 pi root over L divided by G. Instead of G, you have to write A net. Instead of G, you have to write A net, and that is A net. That is A net. Okay, is this point very clear? So this is going to be T equal to 2 pi root over L by G. And what if the electric field is in the same direction but the charge is negative? Listen, charge is negative. So definitely the force F equal to QE is going to be in the upward direction. So mg in the downward direction, QE is in the upward direction. mg in the downward direction, QE in the upward direction. Okay. mg in the downward direction, QE in the upward direction. Listen over here. So T equals to 2 pi root over L by G. Focus over here. See, so this is the discussion. Let's take the discussion ahead and here we go. Okay. Yeah, so we are doing some questions. First question coming in front of you from Coulomb's law. This is from NEET 2019. How much time do you require for this question? How much time do you require for this question? Let's say I'm giving you 45 seconds for this question. Okay. I'm giving you 45 seconds. So come over here. 45 seconds for this question. 3, 2, 1. For every question, keep on marking +4 -1. +4 -1. Okay. And just keep on adding your scores. So time starts now. All of you, be quick. Quick, 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 quick. Fast. Fast. Quick. बेटा आपकी मम्मी से बात करता हूं मैं कि देखो क्या कह रही है लड़की, शादी नहीं हुई है तो शादी कर लो। लगवाता हूं फोन में शाम को, ठीक है अनन्या, पेरेंट्स से बात करते हैं अभी। ओके, टाइम अप। फिर पड़ेगी फ्लाइंग चप्पल और तब आपका मन लगेगा पढ़ने में। ओके, सो डोंट डू दिस, जस्ट फोकस ऑन द क्वेश्चंस। लिसन, so what is it this question saying? 2 point charges A and B having charge Q and minus Q respectively are placed at certain distance apart and force acting between them is F. Okay, that's fine. If 25% of charge of A is transferred to B, let's say in the initial situation these are the two charges, this is plus Q and this is minus Q, that's fine. Plus Q and minus Q, okay, that's fine. So what is the separation between them? The separation between them is R. So the force is going to be K times of Q1 Q2 divided by R square. This is equation number 1. In the second situation, what's going to happen? In the second situation, you are transferring certain amount of charge. So 25% of charge of A has been transferred to B. So which charge gets transferred? Protons or electrons? Definitely electrons. So if you are transferring 25% of the charge, that means Q by 4 has transferred to B. So this is how much? This is Q minus Q by 4. This is Q minus Q by 4. That means this is 3Q by 4. 3Q by 4. Okay, that's fine. That's fine. This is the separation R. This is the separation R. And this is the next, another charge. How much it is? This is Q plus Q by 4. Q plus Q by 4. Okay. Q plus Q by 4. This is going to be how much? How much? 5Q by 4. 5Q by 4. Okay, that's fine. So what is going to be the new force in this situation F dash? That's going to be K times of Q1, Q1, Q2. Okay, Q1 into Q2. Quickly, all of you. Q1 into Q2. Q2 is 5Q by 4 divided by R square. Okay, that's fine. So how much this is? How much this is? They are simply asking the force between the charges becomes. The force between the charges becomes how much it has became now. Okay, this is Q minus Q by, oh sorry, this is wrong, just sorry, this is my bad, this is Q by 4 amount of charge, Q by 4 amount of charge has transferred over here. Okay, so here it is minus Q by 4, isn't it? And over there where it has gone, how much charge has been gone over there? That is going to be plus Q by 4. So this is going to be minus Q plus Q by 4. So how much this is? How much this is? Tell me. This is 3Q by 4. That's fine. And this is minus 3Q by 4 now. This is minus 3Q by 4. Yes. Okay. Okay. Is this point very clear? So this is going to be how much? This is going to be 3 with a negative sign, q, divided by 4. So this is going to be 9 by 16. 9 by 16 times of k q square divided by r square. K q square divided by r square. Equation number 2. So what is going to be the answer quickly? This is going to be 9 by 16 times of f. 9 by 16 times of f. So I hope that this point is absolutely clear. Yes or no? All of you. Next question quickly. Another question coming in front of you is this. Read the question what it says. Just a second. Just a second. Do this one first. Do this one. Do this one. Do this one. This is a nice question. A charge q is placed at the center of the line joining the two equal charges q. The system of 3 charges will be in equilibrium if q is equal to. What are they saying? They are saying that this charge is q and even this charge is q. Okay, that's fine. And what you're doing? You are placing a charge small q at the center of the line joining the two. You are placing the charge small q. Now see, small q is always at the center. Small q is always at the center. So it's going to be at equilibrium. Yes or no? What about every other charge? They are asking that whole system, all the 3 charges should be at equilibrium. That means you should start, even if you stand at 1, 2 or 3, the system is going to be at rest. No matter where do you stand, the system is going to be at rest. Okay. So I'm giving you 30 seconds for this question. 3, 2, 1. The time starts now. 3, 2, 1. The time starts now. Quickly, all of you. I'm observing your options. I'm observing your answers quickly. Do this, do this, do this. Quick, quick, quick. All of you. Be quick. Last 10 seconds. ABCD. Mark it fast. Quick. Finally, time up. Time up. Now see, go and sit on any of the 3 charges, but not on the center one because it is always at equilibrium. So let's say we are going and standing over here. Okay, this is your friend. Who is your friend? Mr. Sontu standing over here. So what you need to find out? You need to find out the force acting on this charge should be 0. For what value of q is it 0? First of all, if I ask you that what is the direction of force, this is 1, this is 2, and this is 3. Okay. So the force acting on 3, we are talking about the force acting on 3 due to 1 and due to 2. The force acting on 3 due to 1 is over here. Let's call it as F1. Let's call it as F1. Okay. So this is along the right. The force acting on Mr. Sontu should be 0. And if it is 0, it's only going to be 0 when this charge is negative. So that the other force is attractive. This should be negative. This should be negative. So positive gets cancelled out. Are you getting the point what I'm saying? Why I'm saying that this should be negative? If it is negative, then only this force is going to be attractive. One force repulsive, another force attractive, then only the net force is going to be 0. Okay. Okay, yes or no? All of you not responding. What happened? Are you sleeping, all of you? Quick. Yeah. So what we can say? We can say that the force 1 should be equal to force 2. Force on 3 due to 1 should be equal to force on 3 due to 2. Okay. We can write this. 3 due to 2. So F31 should be equal to F32. That means KQQ divided by whatever the separation is, R square equals to KQQ. This should be negative divided by R by 2 the whole square. That means R square by 4. R square by 4. Okay, that's fine. KQQ gets cancelled. R square gets cancelled. So Q is nothing but Q by 4. So this is the answer. Simple. Okay, quick. Let's take the discussion ahead. So here we go. Here we go. Which question? Let's say do this question. Okay, simple. Do this question. Two positive ions, again 2010. Nice question it is. Okay. Read this question, what it says. Two positive ions, each carrying a charge Q, are separated by a distance d. If F is the force of repulsion between the ions, the number of electrons missing from each ion, is going to be, quick. So what it's going to be? It's going to be F equals to K Q1 Q2 divided by R square, or whatever the separation between them is, D square. Okay, whatever the separation between them is, let's call it as D. So D square. Okay. So this is the expression. What you need to find out? You need to find out the number of electrons missing from each ion. Okay. Number of electrons missing. Okay. So I'm giving you 45 seconds for this question. The time starts. Now. Here you go. Quick. All of you, I'm observing your answers. Be quick. All of you. Fast. Last 20 seconds. Everyone, respond quickly. Everyone, respond quickly. What it's going to be? Yeah. Time up. Simply what we can do, we can substitute Q equals to NE over here in the expression. Okay. We can substitute Q equals to NE over here in the expression. So what it's going to be? It's going to be F equal to K. K is nothing but 1 upon 4 pi epsilon naught. Q1 is NE. NE and this is NE. Okay, so Q1 equal to Q2, Q1 equal to Q2 equals to NE. So Q1 into Q2 is N into E the whole square divided by D square. So from here what you can do, you can find out the value of N, and directly you can see this is nothing but F into 4 pi epsilon naught D square. D square should be up, E square should be down. That means C is going to be the answer. Very simple. C is going to be the answer. Okay. How many of you got the correct answer? A very small amount of students got the correct answer, although it was a very simple question. Okay, so let's take the discussion ahead. Here we go. Read the question. Another important question. Point charges plus 4q, minus q and plus 4q are kept on the x-axis at point x equal to 0, a and x equal to 2a. Okay, so I'm drawing the situation. I'm drawing the figure. All of you, listen quickly. Mukesh, a lot of questions that I'm taking, they are from both JEE mains as well as NEET. Okay, so don't worry, just solve properly and give the answer in the required amount of time. Okay, take it as a task, take it as a challenge that you have to solve it before I solve, and mark plus 4 minus 1 corresponding to every single question. So here we go. What the question says? The question says that there are point charges plus 4q, okay, minus q and plus 4q. This is plus 4q minus q plus 4q. What are the points? This point is x equal to 0, this point is x equal to a, and this point is x equal to 2a. Okay, that's cool. That's okay. That's fine. So who is in stable equilibrium? Who is in unstable equilibrium? Simply, if you displace the central point, okay, let's keep your friend. Bring your friend. Who is your friend? Mr. Bring Montu this time. Okay, so this is Montu. This is Montu. Okay, so this is Mr. Montu. Look at the hairstyle. So if you displace Montu, this is Montu standing at this point. If you displace him from the center, okay, towards the left, that means you are going closer to this charge. The force is going to increase due to this charge. Is going to come back. If you displace it towards the right, the force due to this charge increases, it comes back. Isn't it? Definitely yes. Definitely yes. Definitely yes. Yes or no? Yes or no? Definitely yes. So this is under stable equilibrium. Minus q charge is under the stable equilibrium. Then if you talk about plus q plus 4q, if you displace plus 4q over here, the force of repulsion decreases. The force of attraction also decreases. Okay, also decreases. Yes. If you bring it closer, bring it closer. Bring it closer. Bring it closer. First of all, give the answers. What's the answer? Arjun is saying B. Ishika is saying B. Deep Jay is saying all charges are under stable equilibrium. Mohanji is saying B. All of you, quick. First of all, give your answers. Why there are still mixed answers? Ishika is saying, some are saying A, some are saying B. Some are saying A, some are still saying B. Why so? Why so? Why so? Why so? Quick. 10 seconds more. 10 seconds more. 10 more seconds. All of you. Quick. See. Next point, all charges are going to be under stable equilibrium. If you displace the plus 4q charge over here, what is going to happen? The force on this charge due to the central charge is going to increase definitely as what's going to be the magnitude K, Q1, Q2, okay, K, 4Q1, Q2 divided by whatever the separation is, A by 2, the whole square. Okay, A by 2, the whole square. Okay, listen. So this force is going to, if you bring it closer, the force is going to increase. The force of repulsion is also going to increase. That means yes, it can be in stable equilibrium. So the answer should be all are going to be under stable equilibrium. Okay. Now listen. If another question comes in front of you, let's say this is a particle M, charge Q placed at rest under the uniform electric field and then released. The kinetic energy attained by the particle after moving a distance y. Point is, if you keep a charge at rest, if you place a charge at rest, what is the meaning of rest? The meaning of rest is that initial velocity should be 0. Okay. And there is a uniform electric field. So if there is a uniform electric field E, definitely there is going to act a force QE over here. So if this is the force, F equal to QE, what is going to be the acceleration? Acceleration is going to be force divided by mass. Okay. What is he asking you? He is asking the kinetic energy. So what is going to be the kinetic energy? The amount of work that you do gets stored in the form of kinetic energy. Yes or no? The amount of work that you do gets stored in the form of kinetic energy. So what is the work? Work is simply equal to the change in kinetic energy. Okay. So how much is the work done? Work done is force times of displacement. Is the force constant? Definitely yes. Force is constant and that is equal to QE. That's a constant force. So work done is simply going to be QE into displacement. That's why. QE into displacement. That's why. Quickly, yes or no? All of you. Quickly. Yes or no? Is this point absolutely clear? That's cool. Let's take the discussion ahead. Here we go. Okay. Here we go. Have a look at this particular figure that's given in front of you. This is a question asked in 2004. Okay. The given figure gives electric field lines of forces due to two charges, Q1 and Q2. What are the signs of the two charges, Q1 and Q2? What are going to be the signs of the two charges? 10 seconds for this question. All of you. 10 seconds for this question. What is going to be the answer? Fast. A, what is positive charge is what? Positive charge, electric field lines are outside, something like this. Electric field lines are always outside, something like this. Okay. If you talk about a negative charge, electric field lines are inward. Okay. That's cool. So if this is a negative charge, and this is also a negative charge, then only this situation is possible. I don't think it needs a great more time than this. So simply it's going to be, both are going to be negative. What's the answer? Both are going to be negative. Let's take the discussion ahead. Let's take the discussion ahead. Okay, just a second. We are going to begin with the Gauss's law first, and then again we'll do some more questions. Okay, just a second, just a second, just a second. Okay, yeah. So here we go, here we go, here we go. Here we go, 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 here we go. Yeah. Before that, read this question. What this question says, a thin conducting ring of radius r is given a charge q. This is a thin conducting ring and it has been given a charge q. This is a nice question. This is a good concept. Okay, asked in 2008. So this is the system in front of you. I want you to give the answer. I want you all to give the answer. What this question says. Electric field at the center of the ring O due to the charge on the part AKB due to this segment. Okay. You need to find out the direction of the, electric field at the center of the due to the charge on this part ACBD. Okay, this part, ACDB, this part. Let's take this into two parts. Okay, let's do this way. Cool. ABCD. 10 seconds for this question. Only 10 seconds for this question. 3, 2, 1. The time starts now. All of you begin. Quick, quick, quick. Fast, 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 fast. Observing your answers. All of you, quickly. I'm having a look at your answers. What are you giving? Be fast, be precise. Calculate properly and think and then give the answer. Time up. See. Listen. The point is that if you are at the center of this particular system, what is going to be the net field on you? How much is going to be the net field on you if you are at the center of that ring? Definitely the net field is going to be how much? That's going to be 0. The net field at the center is going to be 0. Isn't it? Yes. Yes. So can I say that this is segment number 1 and this whole is segment number 2? So the total E1 plus E2 is going to be equal to 0. E1 plus E2 is going to be equal to what? That's going to be equal to 0. Okay. And what are they saying? The electric field at the center O of the ring due to the charge on the part AKB. This is E. So you are saying that this is E. Simply. Okay. And what's the direction? The direction is going to be along this line. So it should be equal and opposite. E2 should be minus times of E1. Oh, so what can we say? We can say that this is going to be the direction. That means it's going to be E along OK. Very simple. What do you say, all of you? Nice concept, isn't it? Interesting. What do you say, all of you, quickly? You can get the notes of the session on the app. Okay, Sadiq, is this point clear? Okay, so let's take the discussion ahead. Here we go, here we go, here we go, here we go, here we go. Okay. So before getting into the question, let me tell you something about the flux and the Gauss's law. Okay. Let me tell you something about the flux and the Gauss's law. What is basically the concept of flux? The concept of flux is nothing but the number of any quantity crossing a given system. If I talk about the flux of wind, let's say there is a window, okay, and there's wind which is flowing something like this. This is the wind which is flowing, okay. So if wind is flowing, this is the wind that's flowing something like this. Okay, so the amount of wind that is flowing, I'll be giving break at 7:20 or 7:30. Okay, till then you have to be here, and if you want to go, you can go. I'm not going to stop anyone, but the break is going to be at 7:30 sharp. till that we have to finish potential and current electricity. Then only we are going to finish the complete syllabus by the end of might be 3 or 4 in the night. Okay. Yeah. So this is going to give you the number of how much wind is crossing the given region. That's the flux of the wind. Okay. Similarly, if you have electric field lines, so how much electric field line is crossing a given surface area? How much electric field line is crossing a given region? This gives you the flux of the electric field. And the electric field, the electric flux, which is denoted by phi, that depends upon what? That depends upon the electric field, that depends upon the area, and that depends upon the angle between the electric field and the area vector. Sir, what is the area vector? What is the area vector? If this is the area, the perpendicular drawn to the area is the area vector. So we take it as cos theta. Sir, what is the theta? Theta is the angle made by the area vector and the electric field. I hope that this point is absolutely clear. So what do we write? We write that the flux is nothing but phi equals to E dot A. Sir, what about a closed surface? What about a closed surface? We are going to say that for a closed surface, electric flux is going to be integral of E dot ds. Integral of E dot ds. Okay. Phi equals integral of E dot ds. Okay. Is this point very clear? That's cool. So now if we talk about the Gauss's theorem, if we talk about the Gauss's law, what Mr. Gauss said, Gauss's law, Gauss's theorem. So what this gentleman said, he said that the flux passing through a closed surface, okay, the total flux passing through a closed surface is going to be integral of E dot ds, which is going to be Q in, divided by epsilon naught, Q in divided by epsilon naught. So this is the complete statement of Gauss's theorem. I hope that this point is absolutely clear. Okay. I hope that this point is absolutely clear. So I'm giving you an example. Let's say this is a cube. Okay. This is a cube. And I have placed, all of you keep listening. Very important discussion this is. I have placed two dipoles. This is minus q. This is plus q. This is minus q. And this is plus q. There are two dipoles inside. So how much is going to be the flux? Through the system? A option, 4 times of q. Listen. Just a second. 4 times of q by epsilon naught. B option, 2 times of q by epsilon naught. C option 0. D option we don't know. Is it? Definitely D is not the option because we know. We are not dumb. Isn't it? Vandit Kumar is saying Hindi mein padhao mere bhai, English channel hai. Padh le chupchap. We have a separate Hindi channel. Okay. On which already the marathon has been done in Hindi. English film chal rahi hai yahan pe. Okay. Yeah. So anyways, what's the answer? Quickly. ABCD. ABCD, ABCD, ABCD. ABCD, ABCD, ABCD. What's the answer? See, the total charge inside is how much? The total charge inside is plus q minus q plus q minus q. Q in is 0. Q in is 0. So the total flux is going to be 0. So the answer to this question is going to be 0. Simple. Remember that the total charge over here is the charge enclosed. If I keep a charge outside, listen, if I place another charge outside over here q, is this charge going to create a flux through this system? Definitely no. Is this charge going to create a flux through this system? No. We are concerned only with the charge enclosed, but the electric field is going to be due to all the charges. What do I mean by all the charges? The charges which are inside, as well as outside the system. Okay. Remember this point. Remember this point, okay? This is very important discussion, okay? Gauss's law on one page, flux and Gauss's law on one page. So now let's take the discussion ahead. There's a question coming in front of you. Read this question. Read this question. +4 -1. Okay. +4 -1. Fast. Quick, 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 quick. All of you. Be fast. Give me the answer. A, B, C, D, A, B, C, D, A, B, C, D. A, B, C, D, A, B, C, D, A, B, C, D. Last 3, 2, 1. And the time up. What it says, a square surface of side L meter in the plane of the paper is placed in a uniform electric field acting along the same plane. Oh, what the point is? The point is that this is the plane. This is a plane. This is a plane. Okay, this is a plane. This is a plane. Okay. And this is the surface that I've drawn. And the electric field is also, along the same plane. Okay. If let's say this over here is the plane and this is the surface, I've placed it like this. So is the electric field line going to cross it? Definitely no. Definitely no, it's not going to cross it. Okay, it's not going to cross. That means no electric field line is going to cross the surface. No electric field line is going to cross the surface. Okay, so the net flux is going to be 0. Okay, this is the answer. Let's take the discussion ahead. Here we go. Yeah, read this question, what it says. This is the same question. I'm not taking this question. Another same question, exactly same concept. Okay, repeated. So we are not taking it. So even in this situation, if it is in the plane, the answer is going to be 0. Just okay, quick concept. Let's take the discussion ahead, and here we go. Read this question. A spherical conductor of radius 10 centimeter has a charge. Charge has been given to you, distributed uniformly. What is going to be the magnitude of electric field at a point 15 centimeter from the center of the sphere? Now, what kind of surface is it? What is being given to you? Spherical conductor. Okay. And the charge is distributed uniformly. Charge has been distributed uniformly. You are talking about the solid spherical conductor. Okay. You need to find out the charge. You need to find out the electric field at a point 15 centimeter. At a point 15 centimeter from the center of the conductor. Have we seen the concept? Isn't it? Definitely, yet we have seen. So I'm giving you 30 seconds for the calculation. Okay, 30 seconds for the calculation, or let's say 45 seconds for the calculation. +4 -1, the time starts now. All of you begin. All of you begin quickly. Begin. Quickly do this. Okay, it's calculative. It's calculative. You have to calculate. Okay, and give the answer. You do this. Okay, this is a very simple question. I'm leaving the calculation for you. Okay, we are coming to a conceptual question. Let's come over here. This is the conceptual question. Read the question, what it says. Go through the question. The question says that the electric field at the center O of a semicircle of radius A having a linear charge density lambda. Okay, this is semicircular charged ring. Okay, important discussion. Remember, I'm giving you two important points. Listen. Infinite wire and semicircular charged ring. Okay, lambda charge Listen, listen, listen. Charge, 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 charge. We have just derived the expression. We have just derived the expression, yes or no? Definitely yes, we have. So first of all, tell me what's the direction of electric field at any given point P. The direction of electric field is radially outward, and what's the value? That's 2k lambda by r. You can also write k. You can also write k as 2 divided by 4 pi epsilon naught lambda by r. That means 1 by, or simply lambda by 2 pi epsilon naught r. Okay, and if you all of you focus over here. No, nothing else you have to discuss. Okay, just this concept. Listen to the concept. Very important discussion this is. Okay, I'm telling this to everyone who is not attentive in the chat. If you talk about the direction of electric field, first of all, tell me what's going to be the direction. What's going to be the direction? Okay, what is going to be the direction due to this particular system, which is having uniform linear charge density lambda? So 1, 2, 3, 4, 5, 6, 7, 8. Tell me the direction. Tell me the direction of electric field at this point. Go and stand at this point. Okay. Take Mr. Who is this? Who is your friend? Who is your friend? Mr. Sontu. And this is Mr. Montu. Okay, Mr. Sontu. And this is Mr. Montu. Okay. So take your friend along with you. Take your friend along with you. Sontu, Montu standing at different points. What is the direction of field? 1, 2, 3, 4, 5, 6, 7, 8. Quickly. Just give me the direction. All of you, just give me the direction. I'm asking everyone. Yeah, can't see your options. Just a second. Just a second. Just a second. I cannot see your chats. Just give me a second. Okay, that's fine. Yeah, now I can see your options. Please tell me the direction. I'm only asking about the direction. I'm not talking about the value. All of you, I'm not talking about the value. I'm just asking about the direction. Tell me the directionality. What's the direction? Okay, that's fine. That's cool. And what's going to be the value? And now tell me what's going to be the value. What's going to be the value? The value is going to be the same. Okay, this is the direction, and the value is going to be exactly the same that we have written over here. That's why I've written these 2 points closer to each other. This is 2k lambda by r. Okay, this is 2k lambda by r. Yes, that's fine. That's cool. And if I talk about an arc, okay, if you talk about an arc, so if this is an arc, okay, let's say this arc makes an angle theta at the center. This arc makes an angle theta at the center. So it's going to be how much? It's going to be electric field is 2k lambda by r times of sine of theta by 2. Okay, so you can verify the result. If you talk about theta equal to 2 pi. What is theta equal to 2 pi? That means if it is a complete ring, okay, then E is going to be how much? That's going to be 2k lambda by r into sine of 180. How much is sine 180? That's 0. So the answer is going to be 0. The answer is going to be 0. If you talk about theta equals to pi, that means if it's a semicircular ring, so you can verify that E is how much? E is nothing but E is going to be 2k lambda by r into sine of 90 degree, isn't it? Pi is 180 divided by 2. Sine 90 is 1. This is nothing but 2k lambda by r. This is nothing but 2k lambda by r. Remember, very important discussion this is. Okay, very, very, very important discussion. Okay, let's take the discussion ahead. Simple question coming in front of you. Read the question. +4 -1 2000. It has been asked in 2000. So the timer is 30 seconds. The time starts now. All of you begin. The time starts now. All of you be quick. Give the answer. Fast, fast, fast. Simple, very simple discussion. Very nice. All of you gave the answer in 10 seconds only. So this is the answer. What is the answer? What is the answer? 2k lambda by r. What is r? R is a. Okay. And what is lambda? Sorry, not lambda. What is k? K is 1 upon 4 pi epsilon naught. So this is lambda divided by 2 pi epsilon naught a. So this is the answer in front of you. Lambda divided by 2 pi epsilon naught a. C is the answer. So here we go. 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 What is the flux through a cube? What is the flux through a cube? All of you. Of side A, if a point charge is at one of its corner, let's take a cube. Let's take a cube. This is a cube in front of you. That's fine. This is a cube in front of you. That's nice. And what are you doing? You are placing a charge at some of its corner. You have taken a charge at some of its corner. Okay. You have taken a charge with some of its corner. Quick, 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 quick. Anyone who is doing spamming now, don't do this, nonsense over here. There are a lot of other places where you can go and do all this. Have some shame that people are studying over here. I don't know what you are doing or whomever you are. And even if you are related to education or not, I don't know. But please think that someday, if someone is going to do this behavior with your siblings or your brother or your sister or your family member, then what are you going to feel? Okay. So if someone is studying, respect this thing, and I don't want any kind of spamming over there in the chat. I just saw some of the IDs that are actually very weird. I don't have the time to go right now and just to report this. Okay. It takes 5 minutes, but I don't want to waste the time of everyone. That's why I'm telling you very clearly, please don't do this, or else you have to face the consequences. Is this point very clear? Now rest of you give me the answer. You have placed the charge at the corner. You have placed the charge at the corner. Okay. So if you are placing the charge at the corner, how much is the contribution of this charge? The contribution is Q by 8. So the flux is going to be Q by 8 epsilon naught. Q by 8 epsilon naught. Phi equals to Q by 8 epsilon naught. That means the answer is going to be Q by 8 epsilon naught. This is going to be the answer. Okay, simple question. Just remember, I'm giving you some basic discussion. Listen, all of you, I'm giving you some basic discussion. If this is a cube, if this is a cube, if this is a cube, okay, if this is a cube, you place a charge inside it. If a charge is placed, if a charge Q placed, all of you be very attentive. Okay, if charge is placed inside, then what happens? Let's say this is the charge placed inside. Then the flux is going to be Q by epsilon naught. That's fine. Okay, whatever the charge Q is. Okay, capital Q divided by epsilon naught. If you place it at the face, if you place it at the face of the cube, if you place it at the face of a cube, so the contribution at the face, this is the face, okay, you place it over here. The contribution is half at the face. The contribution is half. Okay. So this is going to be how much? This is going to be phi equals to Q divided by 2 epsilon naught. If you place at the corner, if you placed at the corner, the contribution is going to be 1/8. Corner. The contribution is going to be 1/8. That means Q divided by 8 epsilon naught. Remember this basic discussion. If you place at the edge, that's going to be 1/4. Okay. Yeah, this is the concept related to solid chemistry. Exactly. Okay, exactly. Another question. A charge Q is enclosed. A charge Q is enclosed by a Gaussian spherical surface of radius r. If the radius is doubled, then the outward electric flux is going to be only 20 seconds. Only 20 seconds for this question. Only 20 seconds for this question. What are they saying? They are saying that there is a charge Q inside a surface. If you double the surface, how is the flux going to change? Begin. Nice question based on the application of Gauss's law. Nice question based on the application of Gauss's law. Quick. Fast. Quick. Mm-hmm. Mm-hmm. Let's see what you do. Okay, time up. Time up. 30 seconds, I said. A lot of you, what are you saying? Let me see. A lot of you are giving the correct answer. Most of you are saying same because we know that's independent of the type of surface that you take. If this is a charge Q, okay, this is a charge Q. No matter you take the surface like this or you take the surface like this, the Gaussian surface like this, or you take the Gaussian surface like this. In all the situation, take this or take this or take that. In all the situation, every situation, the flux, what is flux? The number of field lines that are crossing the system. That's something that's going to remain. That's what is going to remain. That's what is going to remain same. So this remains same. Okay. Here we go. Hollow metal sphere. This is from 2019 latest question. Oh ho. Latest question. NEET 2019. NEET 2019. Latest question. Read the question. What the question says. Okay. Hollow metal sphere of radius r is uniformly charged. The electric field due to the sphere at some distance r from the center. What is it saying? He is talking about the 10 seconds for this question. ABCD 10 second. ABCD 10 second. Let me observe the answers. Answer quickly. Fast. ABCD. Time up 20 seconds. What are you saying? 0 as r increases for r less than r and then decreases for r greater than r. Okay. Now see what this question says. We are talking about a hollow sphere. So we know that if this is a hollow sphere, okay, you make an object sit inside the hollow sphere. Who is this? This is Sontu or Montu. Okay. He is standing inside the hollow sphere. Ask him that what is the field. Ask him what is the field. What is he going to say? He is going to say that E inside is always 0. Okay, that's fine. If you make another friend of yours stand over here, who is this? This is Sonti. Okay, ask her what is the net field. She is saying that, okay, sir, the net field is going to be KQ by R square. Okay. That means E inside is 0. E inside is 0. Okay, this is inside. This means inside and then decreases as you come out. R less than R, you are inside, so E is 0. R greater than R, E is inversely proportional to R square. Okay, I hope that this point is absolutely clear. Mukesh, have patience and just give the answers. Okay, what we are saying. Just remember one thing regarding the solid angle. Okay, just remember one thing regarding the solid angle since you're asking. Okay, the most common question that has been asked from the solid angle, if you place a charge Q at the corner, at the vertex of a cone, you need to find out the flux. Okay, just 2 minutes I'm taking on this discussion, not related to the question, but still someone was asking, so I'm giving the answer. So read this. Okay, just compare the flux through the complete angle. Let's say this is phi dash, so phi dash is going to be pi divided by 4 pi. This is the total angle into solid angle, which is omega. Okay, solid angle, that's omega. Substitute the value over there. Okay, let's take the discussion ahead. Here we go. Another nice question coming from you, in front of you, from NEET 2019. NEET 2019. Quickly. Read this question. Two parallel infinite line charges with linear charge density plus lambda minus lambda. How much is it? Plus lambda minus lambda. Okay, you are asking at the center. Okay, you are talking at the center. So commonly what do we think? What is going to be the net field? What is the direction due to the +1? It's along the left. Due to the minus, it's again along the left. That's going to be E net is going to be 2 times of 2k lambda divided by r. That means k lambda by r. And what is k? What is k? What is k? K is 1/4 pi epsilon naught. Okay, lambda by r. So this is lambda upon pi epsilon naught r. D is the answer. D is the answer. Is this point very clear? All of you? Okay, so here we go, 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 here we go. Next question quickly in front of you. From mains 2010, from JEE mains 2010, quickly, what the question says? The question says that the electric field at a distance of 3r/2 from the center of a charge conducting spherical shell of radius r is E. The electric field at a distance of r/2 from the center of the sphere. Electric field at a distance of 3r/2 conducting spherical shell. Electric field at a distance of r/2. That means where you are standing. Only 10 seconds for this question. Only 10 seconds for this question. Simplest of the question. Quickly, Pratiksha is saying answer is 0. Okay, Arjun is not giving the answer. Sarkar, Mukesh, Punita, quickly, Ishan. Time up, time up, time up, time up. Since you get inside the surface, inside the sphere, the answer is going to be 0. No need to think. Okay, very basic, very simple discussion. Okay, if we take the discussion further, let's take the discussion further. Okay, here we go, here we go, here we go. Some questions have been mixed here and there. Okay, next question, very simple question. Next question. Quick. Ten seconds. 3, 2, 1, begin. 3, 2, 1, begin. Which of the following is correct? Unit for electric field: volt per meter, Newton per coulomb, joule per centimeter. Time up. If you talk about the electric field is nothing but, if you talk about the electric field is nothing but force acting per unit charge. Okay, that means Newton per coulomb is the correct answer. Okay, the relation between, you are going to study just right now, we are going to study the relation between field and potential. So the relation between field and potential is going to be E equals minus of dV by dr. That means volt per meter is also the correct answer. This is also the correct answer. Another relation you are going to study regarding the energy, electrical energy density. Okay, so we say that the energy density, energy per unit volume is nothing but half epsilon naught E square. Okay, remember electrical energy density, electrical energy density, electrical energy density. This is the permittivity, this is the electric field, this is the energy density, energy per unit volume. So sorry, electrical energy density. So this is going to be joule per coulomb. So simply all are the correct. All of the above are correct. Okay. Which of the following, next question, which of the following option is correct for Gauss's law? The next question point is not coming. Which of the following option is correct for Gauss's law? If you talk about the Gauss's law, just a second. Yeah, now say. Valid for any type of charge, not always useful. Electric field due to all the charges outside. Contour says ABC. Now tell the answer. Contour is saying ABC. Which of the following option is correct for Gauss's law? We are talking for the Gauss's law. Okay. So, which of the following option is correct for the Gauss's law? It is valid for any type of charge distribution, not always useful, electric field due to all the charges outside or inside. Okay. Tell me the answer. Quick. All of you. First of all, what is Gauss's law? Gauss's law says that phi equals to integral of E dot ds equals to Q in divided by epsilon naught. Okay. Yeah. So very clearly I said that the charge is only the charge enclosed, but the electric field is due to due to all of the charges, all of the charges which are present. So is Mr. Sontu saying what Mr. Sontu is saying? Is it true? Tell me. Sontu, what Mr. Sontu is saying. Who is Sontu? This is Sontu. Okay, your friend. Sontu says ABC. So A, valid for any type of charge distribution. Yes, it is valid. Not always useful. Yes, it is not always useful. If you don't have a symmetric Gaussian surface, you cannot find it. Try to understand. It is valid everywhere. It is valid everywhere. But you can find out the electric field only if the distribution is symmetric. Then it would be convenient to find out the electric field. Okay. Electric field is due to every charge which is present in the vicinity. Electric field is due to every charge which is present in the vicinity. What is vicinity? Neighborhood. Okay. Any charge which is placed either inside the surface or outside the surface, electric field is due to everyone. But the flux is only due to the charge enclosed. So this is also true. This is also true. That means Mr. Sontu is saying true. So D is the answer. D is the answer. Okay. Okay. Another important question. Very important question. Okay. This question is for 5,000 marks. 5,000 rupees. Okay. What is the meaning of 5,000 rupees? That anyone who is going to give wrong answer is going to pay me 5,000 rupees. Okay. So now read the question. Ratio of electric field. The ratio of electric field at a distance of r and 2r from the infinite charged sheet. Infinite charged sheet. Okay. So this is the infinite charged sheet. Okay. You want to find out the ratio of electric field at point A is to point B. Tell me quickly. What is going to be the electric field? The electric field is going to be sigma by 2 epsilon naught. Okay. That means it's independent of the separation. It's independent of the separation bar. Okay. This is R. This is 2R. That means the answer is going to be 1:1. Okay. That's cool. Let's take the discussion ahead. Here we go. Now see what it says. Graph of electric field versus R has been given to you. Okay. So we are talking about a point charge. If you talk for a point charge, okay, see, for a point charge, first of all, if this is a point charge, you want to find out the direction of electric field. You want to find out the value of electric field. So what are you going to write? You're going to write E equals to KQ divided by R square. KQ divided by R square. Okay. After this, if you talk about a line charge, okay, let's write the expressions first of all. This is the line charge. This is the line charge. This is the line charge. Okay. So what is the expression going to be? That's going to be 2k lambda by r. Okay. If you talk for a dipole, you should remember that's what? Kp by r square. Kp by r square, isn't it? Kp by r square. Yes, definitely this content is very helpful for CUET as well. JEE mains questions we are taking, NEET questions we are taking. So don't worry, just focus on the concepts. Physics is same for boards, for JEE, for NEET, for CUET. Just be very clear with the concepts. Okay. Third point, it's again inversely proportional to r square. Inversely proportional to r square. Inversely proportional to r. And this is independent of r. Independent of r. Okay. Independent of r. Okay. So what is he asking? The graphs. So first of all, if you talk about a point charge, so it's going to be parabolic. Okay. Inversely proportional to r square. If you talk about line charge, rectangular hyperbola. How to compare? The slope. Are you aware about how to compare the slope? All of you, are you aware about how to compare the slope? See, dipole, some people are asking about the dipole. So if you remember, we have seen the dipole over here. Where we have seen the dipole? Here we have seen the expression for the dipole. This. Isn't it? This is the dipole. Okay. R cube. So have I written R square? Oh, okay. Got my mistake. Really sorry. I have written R square over. That's what I was thinking, that why you saying R cube. So I think I might have written R square over there. So I'm correcting it. Really sorry. Okay, really sorry. My mistake. This is dipole. This is R cube. Okay. R square is the variation for potential. Remember that R square is the variation for potential. Okay, for dipole, electric field is inversely proportional to R cube. Okay. Now the question arises, sir, how to compare the slope? See, in order to compare the slope, we drop a tangent. Okay. We drop a tangent. Now I'm telling you how to compare the slope quickly. Then you can compare it over there. SLOPE. First of all, a very basic method that I also gave in the previous session. Okay. If you have three curves, if you have three curves, 1, 2, and 3. Okay. So what you can do, you can drop the tangents. Tangent number 1, tangent number 2, and tangent number 3. Okay. All the slopes are negative. Now I'm asking you 1, 2, 3. You want to find out that whose slope is going to be maximum. So what you need to do, just imagine that these are the slides in a garden. So go take a child wherever you find a small kid. Just ask that kid to come, take him and make him sit on this slide. Okay. Ask him, are you afraid? He's saying, no, I'm cool. Okay. I'm fan of Avengers. I can do anything. So he's not afraid. Then okay, you're not afraid. Make him sit over here. Okay, take him and make him sit over here. Now you're afraid. He's a little bit afraid, little bit worried. Okay. Take him to the third one. What he's doing is shouting. He's calling his mother. His mother is coming. Okay. And you are running. This is you. You are running, wa. Okay. Mother coming, wa. Okay. So you are running. That means the slope over here is maximum. So how to find out the slope? Slope is nothing but dy by dx. So in the three situations, in the first situation, the electric field is given inversely proportional to R. So if I take it as y, if I take it as x, slope is dy by dx, isn't it? So y is inversely proportional to x. So let's take it as like this. Okay. Let's take it like this. If you differentiate it, dy by dx, that's going to be what? That's going to be minus x to the power minus 2. Okay, something like this. If I give you another function, let's say in the other function, y has been given proportional to this. That means y inversely proportional to r square. So you can write it like this now. Let's say the constant is k for some time. R to the power minus 2. Differentiate it. What's the slope going to be in the second situation? That's going to be minus 2 into r or x, whatever it is. Okay. X to the power minus 3. Okay. That means slope is inversely proportional to x cube. Okay. Slope is inversely, it's dependent upon this particular parameter. Okay. And in the third situation, in the same manner, you can find out the slope for the another variation. Okay. So now we are beginning with the next concept of electric potential. Okay. Another important discussion. First of all, what is potential? How do we define the potential? Potential is defined as the amount of work that needs to be done. See, if this is a charge Q, all of you, if this over here is a charge Q, and you need to bring another small charge from infinity to any given point P, don't you think that there is going to be certain amount of repulsion that this charge is going to face? Yes or no? This charge, when you bring him close, there is going to be a continuous repulsion acting on the charge due to the capital Q charge. Yes or no? Yes or no? That means you need to do certain amount of work in bringing the charge near this charge. Yes or no? Yes or no? All of you. So what are we defining? We are talking about the work done on a unit charge. We are talking about the work done on a unit charge. So potential is defined as work done on a unit charge in bringing that charge from infinity to a given point. Remember, without without acceleration. That means at constant velocity, at constant speed. Okay, without acceleration. Okay, without acceleration. Okay, is this point very clear? So the point is that continuously in this situation, the work done, the force is going to change. Force is variable now. Yes. So work done is going to be integral of F dot dr. So you are defining potential as integral of F dot dr divided by Q. Remember this. Okay. So what is the expression for work done? You can say work done equals to integral force. Force is K Q1 Q2 divided by R square into dr. So this is work done. And what is potential? Potential is work done per unit charge divided by unit charge. Charge gets cancelled out. Yeah, oh, we didn't give the answer for previous one. Don't worry, after this we'll be giving the answer. Okay, just a second. Let's complete this discussion. I thought that I gave the answer. No worries. Come here. So the potential is going to be, see, this is KQ by R square. This is electric field E. KQ by R square. This is electric field E. I am writing a negative sign. Why I am writing a negative over here? I'm going to give you the reason. I'm going to give you the logic for this negative. So the relation between field and potential, is this, minus integral of E dot dr. What is the significance of this negative sign? What is the significance of this negative sign? Very important discussion I'm giving. Write it down. Along the direction of electric field, potential always decreases. Along the direction of electric field, potential always decreases. Very, 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 very important discussion. Okay. So if I draw the line of electric field, if I give you the direction of electric field, let's say this is the direction of electric field. This is the direction of electric field. Okay. And you're walking from point A up till point B. So the potential is going to increase or decrease? The potential is going to decrease. If you walk from B to A, if you are going from A to B, the potential decreases. If you are going from B to A, the potential increases. Okay. If you are going from B to A to C, if you are going from A to C, if you are going from A to C, then what? Then the potential remains constant. Please note it down. Very important discussion this is. All of you, please note it down quickly. This is very important discussion. Okay. Done? Noted? All of you? Okay. Okay. Now let's get back to the question. Let's get back to that question. I thought that I gave the answer. Okay. But I just explained and I didn't give the answer. So I'm telling you now. Listen. First of all, point charge inversely proportional to R square. Okay. Let's write it a bit clearly. Okay. So what I'm saying, the point charge electric field is inversely proportional to R square. For line charge, inversely proportional to R. For dipole, inversely proportional to R cube. Okay. And for sheet, it's independent. Okay. So what we are going to say, let's say this is line number 1, 2, 3, and I'm drawing another line. This is line number 4. Okay. So minimum slope, greater slope, maximum slope. Minimum, greater, maximum. Okay. So this E1 is dependent to inversely proportional to R square. E2, inversely proportional to R. E2 is inversely proportional to R square. E3 is inversely proportional to R cube because the slope is increasing. And E4 is independent. So what we can say? We can say that the answer for point charge, this is point charge inversely proportional to R square. Okay. So this who represents? This is represented by E2. This is represented by E1. This is represented by E3. 3, and this is represented by E4. E1, E2, E3, E4. This is the answer, okay? All of you, this is the answer. Is this point absolutely clear? Is this point absolutely clear? So let's get back to the point. Let's get back to the point. Let's get back to the discussion that we were having. We were discussing regarding the field and potential. Okay. So here we go. This is the relation given in front of you. Delta V minus integral of E dot dr. Delta V equals minus integral of E dot dr. And what is potential? And what is potential? Work done on a unit charge in bringing it from infinity to a given point. Okay. Let's say this is the potential at any point A. Basically, it's the difference between infinity and that point A. Work done in bringing that charge from infinity to that point. Okay. So we know that electric field is a vector quantity. So it can be written as the vector sum of the electric fields along all the directions. Okay. Exi plus Eyj plus Ezk. So this can be written as Ex. What is Ex? What is Ex? dV by dx I cap. dV by dy j cap. Okay. dV by dz k cap. Okay. I hope that this point is absolutely clear. Just remember this. Here we go. Here we go. Okay. Yeah. After this, if you talk about the electric potential energy, just keep on noting, you know that F equals to minus of dV by dr. This is a statement I have given you that in the direction of electric field, the potential, if you are walking along the direction of electric field, the potential is going to decrease. Okay, keep on noting potential energy. The potential energy is going to be integral of F dot dr. Okay, that means the work done against the conservative force. Okay, so what are we taking? We are taking the conservative force over here. Conservative force. This is work done against the conservative force. Okay. Okay. Remember this. This is the expression in front of you. Okay. Here we go. If you talk about the electric potential for a point charge, let's say this is a point charge Q. Okay. And you need to find out the potential at point P. So what is going to be the potential at the point P due to this charge Q? This is simply going to be K Q by R. Okay. If you talk about the potential at the center of a ring, now listen very carefully. Some systems I am giving you, you can directly remember the expressions. Okay. So if you talk about a point charge, let's say this is a point charge, Q. So at some distance R, the potential is going to be K Q by R. Fine. If you talk about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 infinite point charges which are placed something like this. Okay. If you talk about infinite point charges which are placed something like this. Okay. And it makes a ring. What it makes? It makes a ring. Okay. It makes a ring. So you need to find out the potential at the center. Let's take a small charge dq over here. So what you need to do, you need to find out the potential due to that small charge, that's dV, that's k dq divided by r, yes or no? Since it's a scalar quantity, you can simply say that the total potential is going to be integral of dV. Okay, so what it's going to give you, it's going to give you V. How much it's going to be? K Q by R, because integral dq means the sum of the small elements due to every element that's present over here. Okay, dq, that's q. Okay, is this point clear? Now if you want to find out the potential due to a ring, if you want to find out the potential due to a ring at its axis, something like this. Okay, something like this. Let's say this is a point P, this distance is x and this distance is r. Okay, listen all of you quickly. You want to find out the potential at the point P. So what you need to do in this situation, take this small elemental charge dq. Let's say that this separation is z. What are you going to do? You're going to take the potential due to every given element, yes or no? Yes or no? So how much it's going to be? it's going to be potential equals to integral of K dq divided by Z. It's a scalar quantity. Simply K by Z comes out, integral dq. What is integral dq? Integral dq means the total charge q. So the answer is going to be nothing but K q divided by Z. And what is Z? What is Z? Z is nothing but root over r square plus a square. Okay, so it can be written as kq by root over r square plus a square. Okay, nothing new. Remember this point, this is very important. Let's take the discussion ahead. So if you talk about the potential for a dipole, so again, if it's axial position, this is minus q, this is plus q, okay, and this is the point at which you need to find out the potential. This is the point at which you need to find out the potential. Okay, let's say that this distance is r and this is a. Okay, this separation is a. So you're going to write the expression something like this. You're going to write the expression something like this. Now what if r is greater than a? Then the expression turns out to be kp divided by r square. You remember I have by mistake written over there inversely proportional to r square. Then I said that this is the relation for the potential. Okay, so this is the potential at the axis of a dipole. This is the potential at the axis of a dipole, inversely proportional to r square. Okay, apart from this, if you talk about the equatorial line, so if you are talking at the equatorial line, if you are talking at the equatorial line, this is minus q, this is plus q. Okay, this is plus q. Remember, all of you, if you talk on this line, this is minus kq by whatever this separation is r. Write it like this, minus kq by r. So net potential at any point on this white line is going to be 0 only. It's going to be how much? It's going to be 0. Okay, I hope that this point is very clear. Let's take the discussion ahead. Now see, the change in kinetic energy equals the loss in potential energy. The point is that if this is a charge, if this over here is a charge q, okay, and let's say this is the electric field, that you have applied, so definitely there is going to be a force acting on the charge. Yes, so it moves from a point A up till a point B. So if the charge moves from one point A, up till some point B, then in this situation, how much work is going to be done? How much work is going to be done on the charge? The work done is going to be Q delta V. Simple. This is the work done. And in what form you are going to observe this work done? In which form you are going to observe this work done? This is going to be observed in the form of change in kinetic energy of the system. I hope that this point is absolutely clear. So here we go. Okay, after this, if you talk about the hollow sphere, all of you quickly, if you talk about a hollow sphere or a conducting shell, okay, conducting shell, this is a hollow sphere or simply a conducting shell. So remember one thing, that the electric field inside is 0. Okay, electric field, this should be V. Electric field inside is 0. So the potential inside is constant. Okay, just a second. This is V. Okay, by mistake it's typed PE over there. Makes no difference. Okay, listen, if you talk about just this is E. Now see, I am giving the relation, all of you. If you talk, yeah, this is V, this is E, this has been written. I'm giving the relation, just read what I'm writing. Simply, if you talk about the electric field inside, that's going to be 0. If you talk about the shell, inside that shell, electric field is 0. Okay, inside that shell, electric field is 0. And what's the relation between V and E? You write that E equals minus of dV by dr. Okay, that's fine. If the electric field is zero. When can the electric field be zero? When can the electric field be zero? The electric field can be zero. When this function over here, this is a constant. This V is a constant. If V is a constant, if the potential, all of you, are you paying attention? Hello, 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 hello. All of you, are you alert? Are you attentive? Be attentive. If potential is constant over there, then the electric field is going to be zero. That means we know that E in is zero. It implies what? It implies that the potential inside is going to be a constant. The potential inside is always going to be a constant. Yes. Okay. That means the potential inside equals the potential on the surface. Electric field is kq by r square. Electric field inside is zero. Okay, that's fine. Another important formula that's coming in front of you regarding the potential inside a solid sphere. Inside a solid sphere. These questions, these formulas, you are going to get in the examination. Remember this thing, okay? These concepts you're going to see in the examination. Okay. So this is the potential, expression for potential. If you talk about the relation R equal to 0, okay, R equal to 0, that means at the center, so what are you going to get? You are going to get a potential as kq 3 by 2 kq by r. You are going to get the potential at the center as 3 by 2 times of kq by r. Okay, so this is nothing but 3 by 2 times, this is nothing but 3 by 2 times of, this is nothing but 3 by 2 times of potential at the surface. So potential at the center is 3 by 2 times the potential at the surface for a solid sphere. Remember this thing, all of you. Okay, is this point very clear? Okay, you're going to get the PDF in the app. Okay, at the app it would be uploaded. Don't worry, Mr. Reddy. Mr. Reddy, don't worry and be ready for the concepts. E outside we know that's kq by r square. Okay, now if you talk about the potential due to infinite line charge. Okay, let's say if this is an infinite line charge, this is an infinite line charge. Okay, that's fine. What is it? This is a charged wire. You want to find out the potential difference between the 2 points A and B. Okay, let's say you were standing at some point B and you're going closer to the wire. You were standing, listen, you were standing at some point A, now you're going at some point B. Okay, so what? Listen, all of you. पढ़ाई पे ध्यान दे दो, इधर आ जाओ, उधर आ जाओ. All of you listen. Are you alert? All of you. So please pay attention over here. And I don't think that anyone has invited you, Mr. Jayesh Sethi or whatever you are. Okay, you are free to go anywhere. No one is stopping you. So please don't disturb anyone else. And Anay Chowk se Chalo, idhar dhyan de, talk all of you. Listen. This is R1, this is R2. Now you're going from the point B up till the point A. So in this situation, what is going to happen? In this situation, what's going to happen? Ye dekho. I don't know whether you're a student or not. These cannot be students. If someone is teaching to anyone, some students or let's say whoever you are, they are just coming and what you are writing over here in the chat. आके जो है आप लोगों को गालियां दे रहे हो. So you think this is cool? क्यों भाई साहब, आपको लग रहा है कि बहुत अच्छा काम कर रहे हो आप? हाँ, इसमें कोई बड़ी बात नहीं है किसी को गाली दे देना. What is this? Please have some decorum. Just imagine that someday you are standing somewhere, your family member is standing somewhere, and someone says this to your father or your brother. What is going to happen? How are you going to feel? Okay, have some courtesy. अच्छे इंसान बन जाओ. ठीक है, कूल है तो फिर अगर अभी सुनो, बात ऐसी है कि मैकेनिकल इंजीनियर हैं, ठीक है, मैकेनिकल इंजीनियरिंग में जब आप जाते हो ना, तो वहां पे जो आप ये लिख रहे हो ना, ये बहुत थर्ड फोर्थ ग्रेड की गालियां मानी जाती है। अभी मैं आपको बहुत हाई लेवल की एचडी क्वालिटी वाली बताता, आई वुड हैव टोल्ड यू अ लॉट ऑफ मोर बेटर वर्ड्स देन दिस, बट आई कैन नॉट राइट द मोमेंट। ओके, सो एनीवेज लीव इट एंड कम टू द पॉइंट। बात ऐसी है that we are saying that if this is the distance r1, this is distance r2, you're going from point b to point a. So how much potential difference is going to be in that situation? You are talking about the electric field, so electric field is going to be, how much is the electric field going to be? That's going to be k 2k lambda divided by r, 2k lambda divided by r. That means inversely proportional to r, inversely proportional to r, yes or no? Definitely yes. You want to find out the potential difference, so what is the potential difference? You write delta v equals to minus integral of E dot dr, minus integral of E dot dr. So just substitute the value over here, just substitute the value over here. Okay, so substitute it over here, minus integral of 2k lambda by r into dr. Limits are from r1 to r2, or let's say from b to a. When you substitute it, you get what? When you substitute the limits, you get the expression as this. Okay, you get the expression as this. See, the point is that you are thinking that, okay, just you're sitting there and writing something, that's very cool. Just look at yourself in the mirror, okay, and ask yourself that whatever you doing, is this worth? Is this fine? Don't ask me, don't ask anyone else. Just ask yourself, okay, that whatever you're doing, is this worth? You're wasting your own time. If you talk about the electric potential difference due to the infinite thin charge sheets, then simply this is going to be sigma by 2 epsilon naught r1 minus r2. Okay, remember this point. Now let's come back to the concept of equipotential surface. We know that the relation between field and potential is what? E equals to minus integral of dv. See, you are writing E equals minus dv by dr. If V is constant, then what's going to happen? If V is constant, then what's going to happen? In that situation, E is going to be 0. Definitely yes, E equals to 0 when V is constant. Fine. E is 0 when V is constant. So now, if in any given situation, the potential is constant, let's say this is a surface, this is your friend standing over here. Who is this? This is Mr. Sontu. He is going from point A up till point B. He is going from point A up till point B. Okay. This is Mr. Sontu going from point A up till point B. So what is going to happen in this situation? The potential is constant. So delta V is 0. And if the delta V is 0, what are you going to write about the field? It is simply how much? It is simply minus integral of dv by dr. dv is 0, so what is going to be work done? Work done is integral of f dot dr. That means q delta v. That means the work done in moving along an equipotential surface is going to be 0. Work done along an equipotential surface is going to be how much? That's going to be 0. No matter what kind of equipotential surface it is, let's say you have a point charge. Okay, so then for a point charge, what's going to happen? For a point charge, this is a charge q. This is a charge q. Okay, this is a charge q. So the electric field lines are going to be something like this. What is going to be the equipotential surface? All of you in the chat. Equipotential surface for a point charge is going to be what? All of you, equipotential surface for a point charge is going to be what? Quickly. Sphere, cylinder, or a sheet. What's going to be the equipotential surface for a point charge? In the chat. Very nice. That's cool. Awesome response. It's going to be what? It's going to be a sphere. So this is the sphere in front of you. This is the sphere in front of you. And this is going to be the equipotential surface. So if someone is moving, along this equipotential surface, then the work done is going to be 0 because it's an equipotential surface. That's cool. If you talk about electric field lines, which are something like this, okay, what's going to be the equipotential surface for this kind of electric field line? All of you. For this situation, the electric field lines are going to be uniform parallel field lines. So the equipotential surface is a sheet. It's a plane. It's simply a plane. Okay. So if someone is moving along this plane, work done along this plane is going to be 0. Definitely yes. Third situation, if this is a charged sheet in front, a charged wire in front of you. If this is a charged wire in front of you, what is going to be the equipotential surface? Quickly. What is the equipotential surface going to look like? Quickly. The equipotential surface for this situation, for this plane, infinite wire, what it's going to look like? It's going to look like something like this. Okay. That means it's going to be a cylinder. Okay. Remember this discussion, very important. So let's take the discussion further. Electric field lines inside is 0. Yes, we know that E is 0 inside a conductor where the conducting material is present. So if E is 0, V is constant. E is 0, V is constant. Simple. Okay. Next point, electric field is always perpendicular to the surface. Electric field is always perpendicular to the surface. Fine. Potential at all the point is same. Surface to the center. Listen, potential at all the point is same. This is one statement. I'm writing it something like this. Listen, I'm changing the statement. Potential at all the point is same inside the conductor. Okay, conductor. Inside the conductor, potential is going to be same. That's cool. Okay. And if you talk about a solid sphere, then how much is the potential? How much is the potential? Potential at the center is 3/2 times the potential at the surface. Isn't it? Is this point very clear? Very nice. Very good, Neha. Very good, Mukesh. Very good. Everyone who is giving the answer. That's cool. Now tell me that what is the concept of grounding? Let's say if this is a surface, okay, it is having certain amount of charge. If you ground the surface, that means if you are doing earthing, okay, then what happens? Then the potential becomes 0. Okay, then the potential becomes 0. Remember this point. Electric field for a thin charge sheet is going to be sigma by epsilon naught. Energy density half epsilon naught E square. Pressure half epsilon naught into sigma square. Okay, remember this point. Now I'm telling you the concept of crowning. What is the concept of crowning? We'll be having a break after 10 minutes. So we are just about to finish this concept and we'll be having a break of 10 minutes at 7:30 sharp. Okay. Come back to the point. See, no need of replying anyone. You just focus on your concept. Let anyone say whatever they want to say. You are concerned with your result. You are concerned with your concept. So just focus on the concept. Okay. Come back to the point. So we are talking about the crowning. So what is basically crowning? Concept of crowning. If this is a surface, if it is having different points, of different shapes, let's say the areas are different. So clearly you know that electric field that you are writing sigma divided by epsilon naught. If the area is different, what is sigma? Sigma is charge acting per unit area. Okay. So if the area of the region like this, it's different. Definitely yes. So what's going to happen? Sigma is going to change. Don't you think so? Yes. So if the area is different, electric field is at those points is going to be different. This is what we call the concept of crowning. This is what we call as the concept of crowning. Okay, cool. Let's come back to the point. Parallel plate capacitor. Now, before getting into the concept of parallel plate capacitor, I am giving you two questions, very direct, very simple questions. I am giving you very direct, very simple questions. These are two sheets. These are two sheets. Okay, these are two sheets. This is having some charge density sigma, and this is having some charge density minus sigma. You need to find out the field inside. You need to field inside at point P. So E at the point P is going to be, I'm giving you the options. Okay, and I'm drawing the another situation. I'm drawing the other situation as well. These are the two sheets. Okay, and the charge densities are going to be sigma and sigma, same to same. Okay. So tell me the electric field at the point P in this situation as well. Okay, so A option, B option, C, D. Which is correct? A, B, C, D. Tell me. So A is going to be sigma divided by epsilon naught, sigma divided by 2 epsilon naught, sigma by 3 epsilon naught, and 0. And same are the options for the second one. Same are the options for the second one. Quickly. Fast. Focus only on your answers. Let anyone say whatever they want to say. Anyone can say anything. Okay. You just focus on your work and give me the answer quickly. We are not here to answer everyone. Quickly. That's great. Very good. Vivek Rao, very good. Neha, very good. Aman, very good. Nitish, that's great. Very good. Ishika, cool. Punita, that's cool. See, so the point is, I'm giving you a very simple rule of life. First, people will laugh at you, then they will try to, discourage you, then they will insult you, and finally, when they are done with it, they'll simply follow. Okay, so remember this rule. Okay, remember this rule and focus over here. So this is sigma, this is minus sigma, this is E, this is minus E, this is E, this is minus E. So E1, E2. So the net electric field over here is going to be sigma by 2 epsilon naught plus sigma by 2 epsilon naught. That's going to be nothing but sigma by epsilon naught. That means the directions are same, so the electric fields are going to get added. Okay, so the net field is going to get added. Okay, if this is plus charge, this is the repulsive field. Again, this is the repulsive field. So make your friend sit over there. Okay, this is your friend. Who is your friend? Mr. Sontu, standing over here. So ask him what is the net field. He is going to say that the field due to system 1 is at the right, the field due to system 2 is at the left. So the E net is going to be sigma by epsilon naught minus sigma by 2 epsilon naught. That means it's going to be 0. So for the second situation, the electric field is going to be how much? That's simply going to be 0. Is this point very clear? Let's take the discussion ahead. Now we are talking about the parallel plate capacitor. Basically, what actually a parallel plate capacitor is. What is a parallel plate capacitor? First of all, what's a capacitor? What is a capacitor? What is a capacitor? We are talking about a capacitor. Okay, that's fine. So capacitor is a device that stores energy in the form of charge. Okay, so the question can be, sir, battery is also spamming energy, battery is also storing energy. Okay, so what's the difference between capacitor and the battery? What is the difference between capacitor and a battery? Battery is going to provide you energy at a constant rate. Listen. If you think about a tap, okay, let's say this is a tap. From this tap, water is coming. Okay, at a constant rate. This is basically a battery. But do you think that this system would be able to provide water to a stadium, or let's say there's a very big vehicle or very big ship on which you need to provide water, you need to wash that ship, or that ship simply under the action of fire, you want to use water, okay, to cool that fire. For fire extinguishing, can you use this water from this tap? Definitely no. In that situation, you require a larger source. Something like this. Let's say this is a very big tank. This is a very big tank, okay? And there is water stored in this tank. Now what you can do, if you want to throw this water, over any given region, simply use that water, isn't it? So this is what a capacitor does, this is what a condenser does, and this is what a battery does, okay? So we are talking about a capacitor. The simplest form of capacitor is a parallel plate capacitor. So let's say these are the plates of a capacitor. Connect these plates to a battery. The moment you connect these plates to a battery, okay, there is charge that's going to get stored on the plates, and there is going to be an electric field in the system, E. Okay, there's going to be an electric field in the situation. Now the point is that what's the net electric field inside? So you know that if there are two plates, then E inside. If there are two plates, then E inside, it's going to be what? It's going to be simply sigma divided by epsilon naught. Yes or no? Definitely yes. Sir, what is capacitance? We know that the capacitance is the ratio of Q by V. Okay, capacitance is the ratio of Q by V. What actually capacitance is? It's the capacity of a system to store charge. Okay, remember, it's independent of Q and V. Very important discussion this is. Listen, it's independent of charge as well as the potential, but it depends upon the ratio of the two. So if you get a question that C depends upon ratio of Q and V. So is it true? Is it false? Quickly. Is it true? Is it false? How many of you are saying it's true? How many of you are saying it's false? Quickly. Is it true? Is it false? Is it true? Is it false? Quickly. What can you say? Is it going to be true or is it going to be false? Capacitor depends upon the ratio of the charges. Think about it, all of you. Capacitance depends upon the ratio of charge and the potential. Is it true? Is it false? It's 100% true statement. It's 100% true statements, because it's dependent upon Q by V. It's independent of individual charge or potential. But yes, it depends upon the ratio of Q is to V. Oh ho. Lot of you are saying true, lot of you are saying false. So everyone, listen very carefully. The ratio of charge and potential. Capacitance is dependent upon the ratio. It's independent of either you're talking about charge or potential. Simply, okay? Remember this point. Important. This is a very important discussion. Let's get back to the point. We were talking about the parallel plate capacitor. So we need to find out the expression for the parallel plate capacitor. Okay. Parallel. Quickly we are doing plate capacitor. Okay. So what is the expression for capacitance? We know C equals to Q divided by V. Isn't it? Definitely yes. What can you say about the charge? You know that sigma is charge acting per unit area, and V can be written as E times of L. Okay. And if this is a parallel plate capacitor, this is the area of the plate. This is the separation between the plates. So you can say that V equals to E times of D. Okay. So simply substitute the value over here. So C is going to be sigma into A divided by V. And what is V? V is equal to ED. Now tell me one thing. What is the value of E? What is the value of E? What is the value of E between the two plates? What is the value of E between the two plates? E is going to be sigma divided by epsilon naught. Sigma divided by epsilon naught. So what it's going to be? Sigma A divided by sigma upon epsilon naught. Sigma by epsilon naught times of D. So what it's going to be? It's going to be epsilon naught A by D. Simple? Simple, simple, simple. Yes or no? Epsilon naught A divided by D. This is going to be the capacitance of the parallel plate capacitor. Is it true? Tell me quickly. Cool? Okay, let's take the discussion ahead. Here we go, 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 here we go. So this is the expression for the parallel plate capacitor. Written every single formula over here. This is the capacitance for air. If you insert a medium between the plates of a capacitor, okay? If you insert a medium, dielectric medium between the plates of the capacitor, then this particular point, this epsilon naught, this term is going to change. You're going to replace epsilon naught by epsilon medium, okay? You're going to replace epsilon naught by epsilon medium, okay? So it's going to be what? It's going to be C dash equals to epsilon medium into A divided by D. And what are you going to write? What are you going to write? You are going to write epsilon medium. Epsilon medium is epsilon R into epsilon naught times of A by D. That means it's nothing but epsilon R times of C. That means C dash is epsilon relative times of C. Okay. So remember this expression, C dash is K times of C. Clear? All of you? Okay, let's take the discussion ahead. If you talk about a spherical capacitor, that's simply 4 pi epsilon naught R. The force on one plate due to another plate. Force on one plate due to another plate. What it's going to be? These are the two plates. These are the two plates of a capacitor. See, this is a discussion from which definitely there's going to be one question. Okay, in NEET, in JEE mains, one question is sure from this discussion. So the force acting on one plate of the capacitor due to the other. Let's say this is plate number 1 and this is plate number 2. So what is the force acting on one plate due to the other? There is electric field. How much is the electric field? Let's call it 1, let's call it 2. Okay. So the electric field of 1 is sigma divided by 2 epsilon naught. And what is going to be the force that's acting on the second one? What is going to be the force that's acting on the second one? Okay, that's going to be F equals to Q times of E. F equals to Q. What is Q? What is Q? Simply write the charge Q times of E. E is sigma divided by 2 epsilon naught. Okay. What is Q? You can write it as sigma into A, or what is sigma? You can write it as Q by A. Yes or no? Sigma is simply charge acting per unit area. So write Q as sigma into A. Substitute it over there. You get the expression for force on the plate, something like this. Okay, sigma is charge upon area. Sigma is, this is Q. Q square by 2 epsilon naught A. Okay, this is Q square by 2 epsilon naught A. Okay, pressure is simply force acting per unit area. This is sigma square by 2 epsilon naught. Very, very, very important discussion. Let's take the discussion ahead now. Okay, so I'm giving a, this is 7:30 now. I said that there would be a break at 7:30. Okay, so we are having a break. Till this is okay, let's say that the break is still, this is 7:36 for 15 minutes break, simply 15 minutes break. Okay, 15 minutes break. After this, we are going to complete capacitance. We are going to begin with current. We are going to start magnetism. Okay, magnetic effects of current and earth magnetism. Magnetism and matter. Magnetism and matter, or simply earth magnetism. Okay, this is what we are going to discuss after the break. Okay, so see you all after 15 minutes. Catch you. Okay. Welcome back, all of you. So let's resume the discussion. Okay. So here we are. We are discussing regarding the capacitor. So we have seen the capacitance of a parallel plate capacitor. What is the capacitance of a parallel plate capacitor? Right now you have said that C for a parallel plate capacitor is epsilon naught times of A divided by D. If you fill the capacitor with some material having some medium, no sound. Is it so? Hello. Am I audible? All of you? Audible, na? Yeah. Yeah. So if there is a medium between the plates of the capacitor, this is going to be epsilon medium times of A divided by D. And you can say that C capacitance when a medium is filled is going to be K times of normal capacitance. That's C. Okay. Okay, that's cool. If you talk about spherical capacitor, the capacitance is going to be 4 pi epsilon naught times of R. Okay, that's fine. Now the result for cylindrical capacitor. Okay, the result for cylindrical capacitor is going to be this, that's written in front of you. This, okay. 2 pi epsilon naught KL divided by log of R2 by R1. Okay, log of R2 divided by R1. Okay, R2 divided by R1. R1 and R2 are the radii. Now the point is that what happens when we combine two capacitors? What happens when we combine two capacitors? All of you, let's say you have two combinations. One is the series combination and another is the parallel combination. Okay, parallel combination. So if you're talking about the series combination, what is going to be same in the series combination? Tell me quickly. What is going to be same for the series combination of the capacitors? If this is the series combination, this is a battery. Okay, this is a battery. Let's say this is the capacitor C1, this is the capacitor C2, and this is a battery, okay, of potential V. So if the capacitors are in series, then the charge that's going to get stored, in the capacitors is going to remain same. Okay, that means the charge in both of them is going to be Q itself. Okay, that's fine. So we can say that the potential drop is going to be V1 plus V2. That's going to be V1 plus V2. V is what? V is Q by C. So you can write Q by C equivalent equals to Q by C1 plus Q by C2. Simple. So this Q gets cancelled out. 1 upon C equals to 1 upon C1 plus 1 upon C2. Simple. Okay, that's fine. After that, if you talk about the parallel combination of capacitors, let's say this is C1, let's say this is C2, and you have connected them something like this. So the C equivalent is going to be what? That's going to be C1 plus C2. How do we get this? Because the potential remains same. So you can say that the charge which is coming is going to get distributed as Q1 plus Q2, isn't it? So Q equals to C divided by V. Okay. All of you, is this point clear? Okay, that's fine. So these are going to be the expressions. For the combination of the capacitors. Okay. Parallel combination, potential drop remains same. The total charge that is combined, that is same. Okay. So this is C equivalent for series and C equivalent for parallel is simply C1 plus C2. Okay. Let's take the discussion further. Okay. So when two capacitors are combined, so what happens? Let's say this is one capacitor, okay, and it is charged. It is having certain amount of charge. Let's say the charge is Q1, and this is having capacitance C1. Okay, the potential is V1. There is another capacitor. Okay, there is another capacitor. Let's say this is C2, V2, and having charge Q2. Okay, C2, V2, C2, V2, and having charge, how much charge? Q2. If you join these two capacitors, then what happens? Charge flow is going to be there. Can we say that the total charge is going to be combined? No, total charge is going to be constant. Total charge is going to be conserved. Till what time the charge is going to flow? Till what level the charge is going to flow? All of you? Till what level the charge is going to flow? Till the time both of them get equal charge. Yes or no? Imagine these are two tanks having water. if you join them through a pipe, the water flows till both of them get the same water level, isn't it? In this situation, the charge will flow till both of them attain the same potential. So we can say, what can we say? We can say that the total initial charge equals to total final charge. Can we say this? Definitely yes. So can we say that Q1 is C1V1, Q2 is C2V2, and Q is nothing but Q in the final, which is also constant, is C equivalent times of V. What is V? V is the common potential. What is V? V is the common potential. Okay, that's fine. What is C equivalent? C equivalent is going to be C1 plus C2. What is C equivalent? That's going to be simply C1 plus C2. Okay. So what is this? What is this expression in front of you? This is going to be C1 plus C2 times of V. So the expression for V turns out to be something like this. The expression for V turns out to be something like this in front of you. Okay, remember this. Very important discussion. This is very important discussion. This is. Okay. Yeah. So after this, the amount of energy lost during the process is going to be half C1 C2 divided by C1 plus C2 times of delta V the whole square. Remember the expression as it is. All of you, is this point absolutely clear? Is this point absolutely fine? I can see. Okay, that's fine. Cool. Good. Okay. Let's take the discussion further. So here we go. Let's do some questions before we take the discussion ahead. Simple question, which of the following is correct? Which of the following is correct? Plus 4, minus 1. Okay, I'm giving only 20 seconds for this question. I'm giving only 20 seconds for this question. The time starts now. Okay, the time starts now. Quickly. ABCD, ABCD, ABCD. Read the question. Which of the following is correct? Which of the following is correct? Very simple question. Very simple question. Fast, I can see your answers. Ishika, Neha, Amitabh, Maya, Riya, Neha, Nitish. Oh, time up. See what the question says. Which of the following is correct? Electric potential decreases along the direction of electric field. If you remember the discussion, if this is the direction of electric field, take your friend. Who is your friend? Mr. Sontu. Let's say Mr. Sontu is going from A to B. Mr. Sontu is going from A to B. So definitely the potential is going to decrease. So this is correct. This option is true. Potential decreases if we move away from the negative charge. Let's check. If you have a negative charge, okay, this is a negative charge. Okay. So you are at point A and you are moving at point B. You are at point A and you are moving away at point B. Okay. Let's say this is the person standing at A. He is moving from A to B. So what is the value of potential that you're going to write? You're going to write V equals minus of KQ by R. So definitely, if you move away from the negative charge, the potential is not going to decrease. It's going to increase because it's negative. Okay. Minus 5, minus 3. Minus 3, minus 5. Think. Okay. So this is wrong. What about C? Potential increases if we move towards the positive charge. Yes. V equal to K Q by R. Okay. You can also think it something like this. Okay. See, if this is the negative charge, negative charge, he's saying potential decreases if we move away from the negative charge. If you're going away from the negative charge, you are going along the direction of field, because for the negative charge, electric field is like this. This is very important concept. So please tell me, is this point very clear what I'm saying? All of you. If you are moving away from the negative charge, you are moving along the direction opposite to the direction of electric field. And if you are moving opposite to the direction of electric field, the potential is going to increase. Yes or no? So this is wrong. Potential increases if we move towards the positive charge. Yes, that's true. So answer 1 and 3 both are true. How many of you got the correct answer as D? How many of you got the correct answer as D? Quick. Okay, that's fine. Let's take the discussion ahead. The next question in front of you is this: which of the following is not correct? Which of the following relation is not correct? Again, +4 - 1. 30 seconds for this question, and the time starts now. All of you be quick. Be quick. Quick. Fast. Fast, all of you. Oh, time up. Where are the answers? All of you, Deepika, Arun, Ishika, Maya. What the question says, which of the following relation is not correct? Work done by a non-conservative force equals to the change in potential. Work done by a conservative force is equal to negative times change in potential energy. This is potential energy. Okay. Work done by non-conservative force is delta U only when kinetic energy is constant and non-conservative force is acting against the conservative force. If work done by electric force is negative, then the potential energy must increase. Simple. Think about this. Let's say this is the bottle. Okay. I am taking this bottle from point A to point B. I am doing work against which force? Against mg. We are doing work against mg. So in taking the object from A to B, you are doing work against a conservative force. That goes where? That goes into the potential energy of the system. So work done against the conservative force. Okay, listen. If I take the example something like this, okay, this is an object. This is mg. This is external force, and we are taking the object from point A up till some point B. We are taking the object from point A up till some point B. Okay. So we are doing work against mg. We are doing work against this conservative force. So the work done by external force is equal to plus of mgh, and work done by the mg, that is the conservative force, is going to be how much? This is the direction of displacement, and this is the direction of force. So that's going to be minus times of mgh. So what we can say? We can say that work done by the conservative force, is how much? Minus times of potential energy. Okay. So match the answer. Now you can match the answer. Work done by potential force, by conservative force, equals the negative times the change in potential energy. Okay. Quickly, let's take the discussion ahead. Next question in front of you is this. This is the expression for V. You need to find out the electric field at point 1, 1, 1. So what you need to do in this situation? E is simply minus of dV by dr. Okay. So individually it's going to be minus of dV by dx. Okay. Minus of dV by dx plus minus of dV by dy plus dV by dz. So differentiate it and substitute the value of A, B, C, D quickly. All of you. Differentiate it. Substitute the value 1, 1, quickly. Quick. All of you. Don't waste time. You are taking so long for this simple question. Very good. Some of you are giving the answers. That's cool. That's nice. See. Most of you are giving the answer as B. So let's check whether it's B or C or D, whatever it is. Okay. Tanika is giving answer as B. Ria is giving the answer as B. Venkatesan, where's the answer? Hassan, where's the answer? Royal Army, where's the answer? Akash, where's the answer? Okay. Let's check. Let's check. See, first of all, if you differentiate the expression, what's dV by dx? Okay. You need to find out electric field. Na? So what's dV by dx? I cap, J cap, K cap. Okay. dV by dx, differentiate this expression with respect to x. So y and z are going to be constant. So this is going to be 2x plus z square. Okay. 2xy plus z square. Differentiate this expression with respect to x. This is 2xy and this is z square. Differentiation of x is 1. Substitute 1 over here. So this is 2 plus 1. This is 3. Okay. Similarly, if you find out Ey, that's nothing but minus of dV by dy. So it is going to be how much? It is going to be differentiate with respect to y. This is x square. This is what? This is what? This is 2yz and this is what? This is 0. So it's going to be 1 plus 2 again 3. Okay, cool. Ez, what is Ez? Ez is going to be what? It's going to be differentiated. This is simply 0. This is y square. This is y square. And this is 2zx. That means again 3. Very simple it was. Very simple. Very simple it was. What you did? All of you gave the wrong answer. Focus. Focus. Either focus or don't study. It's as simple as that. Okay. I am trying to give you every single concept, every single PYQ in this same session so that you can make the best out of it. But for that, you have to focus. Okay. Yeah. So what is going to be ENET? What is going to be ENET? ENET is going to be root over 3 square plus 3 square plus 3 square. That means 3 root 3 is the answer. That means the answer is D. Answer is D. Okay. I hope that the point is very clear. Let's take the discussion further. Let's take the discussion further. Okay. Simple question. No, not this one. Just a second. Yeah, try this one. Try this one. Try this one quickly. Quick. Fast. Electric potential at the center of a non-conducting sphere having a charge R is 0. Then the potential at the surface will be potential at the center of a non-conducting sphere has been given to you. Then the potential at the surface. Quick. ABCD. Just a second. Options are wrong. I'm changing the options. Electric potential at the center of a non-conducting sphere having charge R is 0. Then the potential at the surface will be. Then the potential at the surface just a second. I'm changing the options. This is not 0. Okay. This is not 0. This is having charge R, having charge Q, having charge Q and radius R. Charge Q and radius R. Okay. Is let's say that's V. Then the potential, basically there is a misprinting over here. Just a second, there's a misprinting over here. So what the concept is? The concept is that the potential at the center is nothing but the 3/2 times the potential on surface. Okay. So what we can say? We can say that the potential on surface is going to be 2/3 times, the potential at the center. So now if they provide you the potential at center, you can find out the potential at the surface. That's what the concept is. Okay. So there's a misprinting over here. This is the concept. Just note down the concept and remember this. Okay. Remember the concept. Let's take the discussion ahead. Yeah, next question. Work done in bringing a charge q from infinity to the center of a dipole. Infinity to the center of the dipole. Okay. 20 seconds for this question. 3, 2, 1, begin. Time starts now, all of you. Quick. Quick. Fast. Quick, quick, quick. 10 more seconds for this question. 10 more seconds for this question. Fast, all of you. 3, 2, 1. Time up. Okay. Basically, what is the work done? What is the relation between the work done and potential? We know that work done is nothing but q times of delta V. We know that work done is nothing but q times of delta V. So what is delta V? The potential difference between infinity and whatever that point is. Infinity to that point P. Okay. Whatever that point P is. This is minus q. This is plus q. Okay. And let's say that this point over here is P. So you are bringing the charge from infinity to that point P. What is the potential at point P? What is the potential at the point P? Minus kq by r plus kq by r, that's 0. So in short, delta V is going to be equal to 0. So work done is q delta V, which is nothing but 0. So the answer in front of you is how much? 0. Is this point very clear? Is this point very clear? Okay, let's take the discussion ahead. Read this question. Conducting sphere of radius r is given a charge q, the electric potential and the electric field at the center of the sphere respectively are going to be. Very simple question. We are not going to take a lot of time. Conducting sphere of radius r. Okay. So you are talking at the center. So potential is constant and the field is 0. Field is 0. He is asking about the potential and the field. Potential is kq by r and the field is 0. Simple. Simple. Okay. Let's take the discussion ahead. So here we go. Go through this question. 4-point charges minus q, 2q, 2q are placed at corners of a square. Relation between q and q for which the potential at the square is 0. Center of the square. Easy question. Quick. All of you. 45 seconds for this question. 45 seconds. Begin. Okay. Okay, so finally, time up. 10 more seconds. Okay, do this fast. Praveen, Venkatesan, Raghav, Sri. Who else? Aarti. Okay, so time up finally. So what you need to find out? You need to find out the relation between the charges so that the net potential is 0. So simply what you can say that the potential minus of kq divided by, let's say that the separation is r. Okay, I'm calling it as r. It is going to be same. Okay, because it's a square. Minus kq by r minus kq by r plus kq by r plus kq by r. Okay, equals to 0. Simply solve this. How much do you get? One more step. Minus k by r. Take k by r as common. So what are you left with? You are left with. What are you left with? You are left with. This is simply minus 1 by r. Okay, sorry, minus capital Q by r minus a small q by r plus 2q by r. Okay. Plus 2 times of small q. This should be equal to 0. That means how much this is? Minus plus. This is plus q plus q plus a small q. That means q equals to minus q. This is the answer. Simple. Q equal to minus q. Easy. Simply, if all the charges are same, no need to do this much. Okay, no need to even do this much. Simply, if you just think that what is the total charge, minus 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 plus plus. If these two become equal, these two are equal, net potential at the center is going to be how much? That's going to be 0. Okay. Is this point clear? Because the total charge in that situation is going to be q and this is going to be q. Okay. Okay. Next question in front of you is this. Read the question, what it says. The diagram below shows the regions of equipotential surfaces. A positive charge is moved from the point A. A positive charge is moved from the point A to the point B. Positive charge A is moved from the point A to the point B. So these are the options in front of you. In all the 4 cases, the work done is same. Maximum amount of work done is in the first situation. Maximum work is in the third figure. Second figure, maximum work in the third figure. These are the options. So 20 seconds for this question. 3, 2, 1, the time starts now. 20 seconds. What is work done? What is work done? Work done is Q times of delta V. Work done is Q times of delta V. Just think about the delta V in the situation. Fast. Nadia, which one? This one or previous one? Which question, Nadia? This one or the previous one? Time up. Work done is Q delta V. These are the surfaces. Let's call your friend. Who is your friend? What's the name of your friend? Mr. Sontu. Call Mr. Sontu. This is Mr. Sontu standing over here. He is moving from A to B. So how much is delta V? Delta V in the first situation is 20. Okay, sorry, from A to B, that's 40. Delta V in the first situation is 40. Delta V in the second situation is also 40. In the third situation, it is also 40. Oh, sorry, from 10 to 40, 40 minus 10, that's 30. Really sorry. 40 minus 10, that's 30. 30, 30, 30, 30, 40 minus 10, 40 minus 10, 40 minus 10. That means for every situation, delta V is same. And if the delta V is same, what can you say? You can say that the work done is same. Same amount of work is done in all the 4 cases. So this is the answer. This is the answer in front of you. Okay. I hope that this point is absolutely clear. Now read this question. Read this question. Go through this question. Quick. In a certain region of space with volume this much, the electric potential is found to be 5 volt throughout. 5 volt throughout. The magnitude of electric field. Only 10 seconds for this question. Only 10 seconds for this question. I'm observing your answers. Be quick. Nadia, yes means what? This one or the previous one? This or previous? Quick. Okay, time up. The answer is going to be simply A. What is the relation between field and potential? We know that E equals to minus dV by dr. If the potential is constant, field is going to be 0. If the potential is constant, we know that delta V is going to be 0. So E is equal to 0. 0 is the answer. Simple. Okay. 0 is going to be the answer. Okay. Now someone was asking this question. In this beta, what we did? In this question, simply it was delta V that we need to find out in the 4 situations. Okay. Your friend Sontu is going from A to B in these 4 cases. Okay. In these 4 cases. So if we find out delta V, we can comment on work done. Okay. I hope that this point is absolutely clear. This was the next question. No, not this question. We did. Next question was which one? This was the next question. Okay. So let's come to another question. Do this question. Simple. Okay. These are the points A, B and C, and this is the electric field line. A, B and C are the 3 points in a uniform electric field. Then the electric potential is. This is NEET 2013. This question is for NEET 2013. Quick. A, B, C, D. Bajrang Dal is asking this class is for JW or NEET. It's for both of them. Fast. Maximum at C. We know that if you move along the direction of electric field, bring your friend. Who is your friend? Montu. No, this time we are calling Montu. Okay, so call Montu. Montu is moving. Okay, along the direction of electric field, so the potential is going to decrease. Potential is going to decrease. That means we can say that VB is greater than VC, greater than VA. Along the electric field line, potential decreases. So maximum for C, very simple question. Okay. Oh, sorry, maximum for B. Maximum for B. Really sorry, this B. This is B now. Maximum for B. This is the answer. Correct, 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 correct. Perfect, perfect, perfect. Perfect. We are taking the discussion ahead. Some mixed questions are there, which we are going to take later on. Yeah. So, come to the concept of capacitance. Come to the concept of capacitance. Okay. The electrostatic force between the metal plates of an isolated parallel plate capacitor. If you talk about the electrostatic force between the metal plates of an isolated parallel plate capacitor, which is C, having charge Q, area A. Okay, so what is the expression for the force? F equal to Q times of E. What is the electric field between the plates of the capacitor? We have derived right now. Yes or no? This is the positive charge. This is the negative charge. We know that E is sigma divided by 2 epsilon naught. Yes. Yes. What is charge? What is charge? Charge. What can we write it? What can we write it? Sigma is charge acting per unit area. So sigma into A can be written as charge. Yes or no? Sigma is charge acting per unit area. So this is Q square by 2A epsilon naught. Remember the expression that we derived quickly? All of you, tell me the answer. Okay. Is it dependent upon the separation between the plates of the capacitor? Definitely no. Linearly proportional to the distance between the plates. Distance between the plates. Linearly proportional? Definitely no. Proportional to the square of the distance? Definitely no. Inversely proportional to the difference? No. Independent of the distance. So A is the answer. A is the answer. Very good. Very good. Very good. Very good. Very good. Very good. That's cool. That's fine. Okay. So this is a calculative question. This is a calculative question. Simply what you need to do, C equal to epsilon naught A by D, and C when you insert a medium is going to be K or epsilon R times of epsilon naught A by D. So I am leaving this calculation for you. Okay. It's homework. Let's come to the next question. Read this question. This is a nice question. Okay, read this question. What we are doing, I'm explaining the concept first. Basically what we are doing. Concept is on inserting dielectric. That means if you insert dielectric slab, on inserting dielectric slab. Okay, that means if you have parallel plate capacitor, and what you have done, let's say this is the parallel plate capacitor, plus 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 minus minus minus, fine. This is a dielectric slab, okay, of dielectric constant K. So what is going to happen in the situation? Royal Army, what are you doing? And Bajrang Dal, listen carefully, or else you will also be get blocked like the two fellow who were there, who were abusing in the chat. Okay, they got blocked. I don't want to block anyone. But the point is, people should maintain decorum now. Some sense of responsibility should be there, isn't it? Because a lot of students are dependent, on these sessions. Lot of students are clearing JEE and NEET through this medium. And some people, they just come and they think that, leave it. Okay, let's come back to the point. So the thing is that if you insert a dielectric over here, so C dash is going to be K times of epsilon naught A divided by D. Okay, epsilon naught A divided by D. This is going to be the expression, isn't it? Yeah, K times of epsilon naught A by D. Now, if you talk about E, what is E? E is 1 upon 4 pi epsilon naught Q by R, basically K Q by R square, isn't it? So we know that E is inversely proportional to, you can write epsilon medium is going to be epsilon naught into epsilon r. Can we write this? That means for a given medium, it is going to be 1 by epsilon r times of E. That means E dash is going to be E by K. Simply remember this. Simply remember this. Okay. E dash is E by K. That means if you insert a dielectric medium in between, then what's going to happen? Isn't it? Then what's going to happen? Electric field is going to decrease. Now go through the question. Two thin dielectric slabs of dielectric constants K1 and K2. K1 is less than K2 inserted between the plates of a parallel plate capacitor. The variation of electric field between the plates, okay, is going to be represented by, these are the two plates of the capacitor. These are the two plates of the capacitor. Okay, and these are the two dielectrics. These are the two dielectrics. Okay, K1, K2. A, B, C, D. 30 seconds I am giving. This is a nice question. 30 seconds I am giving. Quickly. Read the question, all of you. Go through it. Fast. Yes. Quick. Didn't start it. 10 seconds now. 10 seconds. Quick. A, B, C, D, A, B, C, D, A, B, C, D. A, B, C, D, A, B, C, D, A, B, C, D. Okay, time up. Electric field is going to decrease. If you insert the dielectric, definitely yes. So E dash is going to be E divided by K. Yes, we know this. That means if this is a dielectric constant K1, E is going to get reduced. K2 is greater than K1. K2 is greater than K1. So electric field in the second situation is going to get reduced even more. So this is normal electric field when there is no dielectric. See, normal electric field, no dielectric. This is E1 dash. This is E1. That means when you have inserted dielectric constant K1. This is no electric field. Again, insert the dielectric of constant K2. This is E2. Okay, so this is the situation. This is the answer. Okay, this is going to be the answer. This is going to be the answer. Let's take the discussion ahead. Okay. So this is the next question coming in front of you. Read the question. Just a second. Before this question, we'll do one more question. Yeah, do this. 3 capacitors, each of capacitance C of breakdown voltage V are used in series. The capacitance and the breakdown voltage of the combination is going to be capacitance and the breakdown voltage for the system. Read this question. How much time do you require for this question? 20 seconds, 30 seconds. What are we doing? We are using 3 parallel plate capacitors in series. 30 seconds I am giving for this question. 3, 2, 1. The time starts now. All of you, quick. Observing your answers. I'm observing your answers. Fast. Quick. Okay. 10 more seconds. Quick. Okay, time up. See what the question says. 3 capacitors, each of capacitance C, are connected in series. They are connected in series. Okay, that's fine. Okay, that's fine. And what are you talking about? You're talking about the situation. What is going to be the charge? Let's say the charges are Q. So what is C equivalent? First of all, C equivalent is C by 3. Okay. They are asking the capacitance. In the situation. What is going to be the capacitance? Capacitance is simply going to be C by 3. Capacitance is going to be simply C by 3. But it's available in 2 options. Try to understand the point. They are talking about the breakdown voltage. What is breakdown voltage? Okay. the amount of potential that you apply, so that there is the maximum electric field. Okay, the dielectric strength in that situation is going to be same. That means if you are talking about the potential difference in this situation it's going to be V by 3, V by 3, V by 3. That means the potential is going to get divided across all three of them. That's cool, that's okay. But the dielectric constant is, but the breakdown strength is not going to change. What I'm saying, this is a capacitor, it's having a breakdown voltage of V. If you're using it in series, definitely the potential difference across it is V by 3, but that doesn't changes the breakdown potential. So the answer is going to be what? Answer is going to be what? Think about it. Think about it. Capacitance and breakdown voltage of the combination will be, it's going to be simply, you are using 3 capacitors in this situation of individual breakdown voltages V, V and V. Okay, so what it's going to be? In series, the potential remains same across all 3. The potential drop is going to be there. So the total potential, you are going to write V equals V1 plus V2 plus V3, isn't it? So answer is going to be B. Answer is going to be B. Although there was C by 3 option in these 2 cases, but how we eliminated, that's very important. Okay, so let's try one more question. Let's try one more question. Read the question. This is from Odisha NEET 2019. Important concept. 1 minute for this question. 2 identical capacitors C1 and C2 of equal capacitance are connected as shown in the circuit. Terminals A and B of the key. Just a second. Let's check who is the spam. And here we go. Block the. Okay, that's cool. Gone. Okay, so let's come back to the discussion. So here we go. Come back to the point, all of you. Read the question. What it says, 2 identical capacitors C1 and C2 of equal capacitance are connected. Equal capacitance are connected as shown in the circuit. Terminals A and B of the key are connected to the capacitor C1 using a battery of EMF V. So what you need to do in this situation? Now they are disconnected. The terminal B and C are connected. First A and B, then B and C. Okay. Due to this, what will be the percentage loss of energy? You need to find out the percentage loss in energy. So how to find out the percentage loss in energy? That's simply going to be, percentage loss is going to be what? That's going to be loss in energy divided by the initial energy into 100. Into 100. This one, no worries. Listen, 2 identical capacitors C1 and C2, they are having equal capacitances. Okay, they are having equal capacitance. Initially, the terminal A and B are connected. Initially, this is connected. This is initial. This is initial. Okay, this is initially, they are connected. A and B are connected. Okay, so the capacitor is going to get charged. The capacitor is going to get charged, isn't it? After that, what is happening in the situation? You are connecting B and C. You are connecting B and C in this situation. That means initially you had one charged capacitor. Initially you charge this capacitor through this circuit. Listen, all of you. This is the capacitor C1. Let's say the charge over here is Q1 and the potential V. This is initial situation. After that, what you're doing? Once it gets charged, what are you doing? You are connecting this capacitor to another capacitor that is uncharged, which is having capacitance C2. Okay, which is having capacitance C2, and that is uncharged. So first of all, how much energy is going to be lost in this process? We know that the charge is going to be transferred till the moment both of them achieve the same potential, V, common potential. We know this. Find out the percentage loss in energy. Before that, find out the loss in energy. So what is going to be the expression for loss in energy? If you remember, half C1 C2 upon C1 plus C2 times of delta V the whole square. Isn't it? What is delta V? What is delta V? What is delta V? This is V and this is 0. V1 is V and V2 is 0. Okay, so substitute and find out. Delta V or delta U is half C1 C2. C1 C2 is C. Okay, both are C, isn't it? They are saying na equal capacitance. So this is C square by 2C into V square. This is the expression for energy loss. This is the expression for energy loss. Okay, and what is initial energy? Energy lost is half C square by 2C into V square. That means C square V square by 4C. Okay, that means 1 by 4 times of CV square. 1 by 4 times of CV square. Okay, that's fine. And what is the initial energy? Initial energy is simply half C V square. Percentage loss in energy. Percentage loss in energy is going to be C V square by 4 divided by 1 by 2 C V square into 100. This is going to be simply how much? This is going to be how much? This is going to be how much? This is going to be 50%. This is going to be 50%, isn't it? So the answer is 50%. It was a nice question. All of you have a look at the question. If you have any doubt regarding the question, please ask me. Go through the question. Go through the question. If you have any doubt regarding the question, please ask me quickly. Quickly respond, all of you. Pratik, Anbu, Pratik, Shakur, Ria, Nadia. What we did, we found the concept is, listen, all of you very carefully. The concept is, what you did actually, initially, you had a capacitor. All of you listen. This was the capacitor and this was the battery. Okay, so the capacitor is going to get charged. Let's say the charge Q1 flows through the capacitor from the battery. Okay, the potential is V. So this gets a potential V, and C1, this is the charge, this is the capacitance C1. So what is the initial energy? What is the initial energy stored in the capacitor? That's simply half of C V square. Now finally what happened? Finally you connected this capacitor to an uncharged capacitor. Okay, you connected this capacitor to an uncharged capacitor. Something like this. This was the terminal joined here. Forget this circuit. Later on, you are going to connect this circuit, this over here. So forget this circuit. Okay, these are the two capacitors. So now, what are we saying? This is C1, this is C1, this is C2. V1 is V and V2 is 0. So in this process, this charged capacitor is going to give certain amount of charge to the other capacitor. This capacitor is going to give certain amount of charge to the other capacitor. Okay, and how much energy is going to be lost in this process? Delta U equal to 1 by 2 C1 C2 divided by C1 plus C2 times of delta V square. This is the energy lost, and you had to find the percentage change. So what is percentage change? I have written the percentage change over here. Okay, this is the percentage change. Remember the expression for percentage change. That's simply what? Percentage change is change divided by initial into 100. This is percentage change. Okay, this is percentage change. Okay. So here we go. Just a second. Here we go. We are beginning another question. Next question that's coming in front of you. Okay. Just a second. We have done this. Mixed questions are there. Another important question, another important concept coming in front of you. Okay. Yeah, this one. There are some questions from different topics mixed over here. Okay. We'll sort them out in the next break. Capacitance of a capacitor is C1, which is charged up to a potential V volt. then connected to an uncharged capacitor of capacity C2, the final potential is going to be. Now this is a question based on the same concept. I want you to give the correct answer within 20 seconds. 20 seconds, dear students, 20 seconds, quick, fast. 20 seconds. Get started. Here we go, here we go, here we go. Quick, 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 all of you. Okay. Time up. Now see, if you have got the concept, definitely you should give the correct answer. Aarti is giving the correct answer, very good. Eswari is giving different answers we are getting. Why so? All of you check, please check, please check, please check, please check. Please check carefully, all of you. See, we know this is the initial situation. Okay, the capacitor number 1 is having a capacitance C1. It is charged up to a potential V. Okay, and then it is connected. Then what? Then it is connected to another capacitor. Okay, that's fine. What is the capacitance of the another capacitor? What is the capacitance of the another capacitor? It's C2. It's C2. Okay. You need to find out the final potential difference. So you should know that what are we doing? What concept are we applying? We are saying that initial charge should be equal to the final charge. What is the initial charge? Initial charge is C1 times of V equals to C1 V final or V common plus C2 V final or V common. Okay. So V final is simply going to be C1 V1 plus C2 V2 upon C1 plus C2. General expression you have to remember. General expression you have to remember. So this is the answer. What is the answer of common potential? What is the answer of common potential? That's C1 V1 plus C2 V2 upon C1 plus C2. Now in this situation, V2 was given 0 to you. That's why this is the answer. Okay. Okay. Simple. Simple, simple, simple. Let's take the discussion ahead. Okay. So here we go. 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 Okay. The work done in moving an electric charge Q in an electric field does not depend upon. Work done in moving an electric charge Q in an electric field. 10 seconds. 10 seconds for this question. Quickly, 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 quickly. Only 10 seconds. 10 seconds. No answer still yet. Why? So, time up. Let's see what you have done, what you have given. Amitabh, Nadia, Ishika, Elizabeth, Neha. See, work done in moving electric charge Q in an electric field. Let's say this is the electric field E. So this work done does not depend upon what? This is the charge Q. You're taking the charge from point A up till the point B. Take the charge from point A till the point B. So work done is equal to Q times of delta V. So it depends upon the potential difference. It depends upon the charge. Does it depend upon the mass of the particle? Does it depend upon the mass of the particle? Definitely no. So why so much time? Be very quick. This was a very simple question. Okay. Okay, that's cool. Let's take the discussion ahead. Let's take the discussion ahead. We are beginning with the discussion of current electricity. Basically, we are talking about conductors. Try to understand. When I talk about material, we classify material as conductor and insulator. What are basically conductors? Conductors are the material which conduct. Simply, conductors are the materials which conduct. Now, how do they conduct and what do they conduct? The conductors conduct because they have a lot of free electrons. Conductors are able to conduct because they are having a lot of free electrons. What are they having? They are having a lot of free electrons. And what these electrons are doing, what these free electrons are doing, they are moving here and there randomly. Okay. They are moving here and there randomly, continuously. Definitely yes. So what is the cause of current? When you apply a potential difference, what these electrons are going to do? Let's say there is a key over here. Let's say here's a key over here. The moment you complete the circuit, what happens? The moment you complete the circuit, all the electrons are going to move in a particular direction. And this is going to provide a unidirectional flow of electrons. this is going to provide a unidirectional flow of electrons. Okay, so this is what is going to provide unidirectional flow, and this is what we call as the current. Yes, the flow of electron, the direction of current is taken opposite to the direction of flow of electron. Remember, now three important formulas, three important concepts: conductivity. Now on what parameters does the conductivity depends? It is proportional to the number of electrons per unit volume, proportional to the charge of electron, proportional to the relaxation time. If relaxation time is greater, what do we mean by relaxation time is greater? Greater relaxation time means more time is required for the collision of electrons. That means conductivity would be better. Conductivity would be greater. Okay, conductivity would be better. That means conductivity is proportional to relaxation time, inversely proportional to mass. Resistivity is inverse of conductivity. Simply remember this. If you talk about the resistance, that depends upon length and inversely to the area. Proportionality is removed, you get rho L by A. What is rho? Rho is the resistivity of the material. Resistivity is a concept. What I'm saying concept, it's a constant. It depends upon the material. It's a materialistic property. It's a materialistic property. It depends only on the material. Okay, independent of the dimensions. Okay, yeah. So this is the resistance expression for the resistance. Remember this: Ohm's law, V equal to IR. Okay, the current is related to the drift velocity with this expression: I equals NEA VD. VD is the drift velocity, N is the number density, E is the charge, A is the area. Remember, drift velocity. How do we find out drift velocity? You can simply write, you have written the relation between current and drift velocity as I equal to NEA VD, and you can also say that V equals U plus AT. Let's say initially electron was at rest. Okay, so the final velocity is going to be acceleration. Acceleration is force, F equal to QE divided by mass into time. That's tau. So this is another expression. This is another expression in front of you. Okay, this is another expression in front of you. Getting the point? Yeah. So these are the expressions that we are going to use in the discussion of current. So please note them down quickly. Fast. Okay, very important. Okay, so here we go. Basically, what's the concept of current? What is the concept of current? If I talk about the current is simply the rate of flow of charge. What is current? Current is nothing but it's the rate of flow of charge. So definitely we can define current as the average current and the instantaneous current. These are the two types of current that we need to discuss: average as well as the instantaneous. So what is the average current? Average current is nothing but the total charge flowing in total amount of time t. What is the instantaneous current? Instantaneous current is nothing but dq by dt. Okay, remember this point. T is time. Okay, in that expression tau, that's not t, that's tau. Someone is asking what is t? But this is tau. Tau is called the relaxation time. This is tau. T-A-U, tau. Relaxation time. I hope that this point is absolutely clear. Okay, so this is the current. So what can you say? You can say that instantaneous current is dq divided by dt. So from here you can find out the expression for dq. dq is nothing but I dt. Integrate it, you get the total charge flowing in given amount of time. Okay, clear? Let's take the discussion ahead. Okay, let's do a simple question. based on this discussion. Simple, 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 simple. Which of the following relation is correct for the drift velocity? 20 seconds. 20 seconds. Time starts now. Quick. $20 seconds. 20 seconds. 3, 2, 1. And time up. Time up. Okay, listen. Listen. First of all, let's check the first expression. It looks correct. In the first, if you just have a glance at it, it looks correct. But this is not correct because I equals NEA VD. I equals NEA VD. So definitely the first expression is wrong. First expression is wrong. The next expression we need to check VD. V equal to U plus AT. V equal to U plus AT. Okay, we have seen V equal to U plus AT. U is 0. Acceleration is force divided by mass into tau. So can we write this expression? No. So this expression is again false. This is wrong. This expression is also wrong. Okay. Then what is this? What is this? We write J equal to E times of sigma. Don't worry. Let me tell you what is J, what is E, what is sigma. This is current density. Current density. What is sigma? Sigma is the charge sigma is the conductivity. Conductivity. Okay. E is the electric field. So only one expression is remaining. Just have a look at this. What is this? This is the definition of mobility. This is the definition of mobility. Okay. Prabhakar is asking, what about gravitation, oscillation and wave? Yes, thermo, oscillation, wave, gravitation, we'll take it tomorrow or day after tomorrow in a separate session. Okay. So yeah, remember the expression for mobility. Through this question, I'm explaining an important concept. So mobility, it's simply denoted by mu, and this is the ratio. This is nothing but the ratio of drift velocity. Drift velocity is to, simply see, this is mu. Drift velocity is to E. Okay. So this is going to be the expression. This is the correct expression. Just this is the correct expression. Okay. All of you over here. Another question that's coming in front of you. 4 alpha particles, 8 electrons are moving from left to right, and 4 proton from right to left through a cross sectional area per second. Find out the current. Fast. Quick. How many alpha particles? How many electrons? What has been given to you quickly? A, B, C, D, A, B, C, D, A, B, C, D. Let's draw left. Let's draw right. This is left. This is right. Left and this is right. Okay. 4 alpha particles are going from left to right. 4 alpha particles are going from left to right. 4 protons are going from right to left. This is proton, charge is plus E. Okay. And just this much. 8 electrons are moving from left to right. This is minus 8E. Going from left to right. So how much charge is being transferred? How much is the net charge that's being transferred, and in which direction? All of you. How much net charge is being transferred and in which direction? If you talk about the alpha particles, 4 alpha particles, what is the total charge of the alpha particles? 1 alpha particle corresponds to 2E. 8E is going right. Minus 8E is also going right. So these two get cancelled out. This and this gets cancelled out. Net charge only 4 proton. Net charge is due to 4 protons, which is how much? 4 plus E. 4 times E is coming from right to left. So what is going to be the current? Current is simply going to be the total charge 4 into 1.6 into 10 to the power minus 19 divided by the time, which is 1 second. So answer is going to be A. Simple. It was a very simple question, yes or no? It was a very simple question, yes or no? Another question coming in front of you. Which of the following is correct for Ohm's law? Which of the following is correct for Ohm's law? V equals to IR. Definitely yes, that's true. V equal to IR. All of you. First you respond. 10 seconds. Okay, 20 seconds. 20 seconds for this question. Fast. Cannot see your chat. Okay. Just a second. Yeah. All of you. Okay, time up. Quickly give your answers. See, we know that if you talk about the Ohm's law, V equals to IR, that's true. Another expression I gave, J equals E times of sigma. Sigma is 1 by rho, so J can be written as E times of 1 by rho. That means E can be written as sigma times of J. E can be written as sigma times of J. Okay. They're asking which is correct. So this option is correct. This option is correct. Okay, let's check this option B. Is the option B correct? Is the option B correct? Is the option B correct? All of you. If you write V equal to IR, V equals to I times of R, you write I equals NEAVD. Okay. You write I equals to NEAVD. Have a look at this term. Here you have I, you have M, L, N, E square tau A. So how can you relate the resistance? R equals to rho times of L by A. If you substitute the expression for rho, yes, this is also the expression for Ohm's law, because substitute this relation. The very first relation that I gave over here, just a second. Here we go. Yep. Substitute the expression for rho. You get the Ohm's law in the same form. Okay. That means A, B, and C, all the three options are exactly correct. All the three options are absolutely correct. Okay. That means A, B, and C all are absolutely correct. V equals I times of R, R equals to rho L by A. If you substitute the expression for rho, you're going to get this as the answer. That means this is all are correct. This is what? This is all are correct. So what is the answer? D is the answer. All are correct. Okay. Is this point clear? Okay. Let's take the discussion ahead. Here we go. Read this question. Two copper wires have mass ratio 2:1 and the ratio of their area is 1:2. Then the ratio of their resistance. How much time do you require for this question? 30 seconds. How much time do you require for this question? 30 seconds. 45 seconds. Let's say 45 seconds. I'm giving you 45 seconds for this question. 3, 2, 1, begin. Time starts now. Quick. Fast. Okay, okay, okay. Still no answer. Why so? Okay. Mixed answers. Mixed answers we are getting for this question. We are getting mixed responses for this question. Okay, time up, time up. What are they saying? Two copper wires having mass ratio of this much and the ratio of their area. Now you know R equals to rho times of L by A. R equals to rho times of L by A. You know that rho is a constant, that means R is proportional to L by A. If you multiply, see, if you multiply and divide by, if you multiply and divide by A, what do you get? If you multiply by area and divide by area, what do you get? You get the upper term as volume, and volume remains constant. Okay, volume remains constant. We know you're talking about two wires whose masses are being given to you and the ratio of the area has been given to you. You need to find out the ratio of resistance. Okay, listen. Focus, 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 focus. R equals to rho L by, definitely yes, we know. R equals to rho L by, rho is a constant, materialistic constant, it depends only upon the material. So if you're talking about two bodies whose masses have been given to you, m1 by m2, that has been given to you as 2 by 1. So what is mass? Mass equals to volume divided by the density. So can you write V1 by rho 1? Okay, just a second. Just a second. Density is mass upon volume. You can simply say volume into density. So what it's going to be? Rho 1 into V1 divided by rho 2 into V2. Yes or no? Definitely yes. Definitely yes. So if you substitute the data over here, what do you get? You get R1 divided by R2 equals to rho 1 V1 divided by rho 2 V2. Okay. Okay. And what can you say about the ratio of the areas? What can you say about the ratio of the areas? What can you say about the ratio of the areas that has been given to you? Volume is nothing but area into length. 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 Substitute it. Substitute it. Substitute. So what do you get? What do you get? You get the ratio A1 by A2. Okay. Mass ratio has been given to you. Simply how much it is? 2:1. So this is going to be the ratio of densities, 2:1, and this is 1:2. So the answer is going to be 1:1. L1, L2 we have taken as same. L1, L2 we have taken as same. All of you, tell me, is this point very clear? Quick. Let's come to the next question. Let's come to the next question. Before getting into the next question, let's have a look at another concept. Just a second. See, there's another term that's coming, what we call as the current density. What is current density? What is current density? It's simply the current crossing a given cross-sectional area, current through a given cross-sectional area. We denote current density as I by A. But tell me one thing, that do we know that area is a vector quantity? Or let's say that we give area the vector treatment because we know the direction of area which is perpendicular to the surface. Direction of area is perpendicular to the surface. We know this, yes or no? Definitely yes, we know. So what if I tilt this area? This is the current, this is the current. And what if I tilt this area something like this? So the area vector also changes. The direction of area vector is going to be this. The direction of area vector is going to be this. Definitely yes. Okay. Let's say the angle between the two surfaces is theta. So you're going to take some component of area and that component is going to be A cos of theta, yes or no? So J equals I by A cos theta. So you can write I equals JA cos of theta. Okay, remember this. JA cos of theta, that means J dot A. J dot A. I equals to J dot A. And another important expression for J is J equals to E sigma. Remember this, okay, all of you. This is very, very, very important. Important discussion. All of you, please note it down. बाबा रे लिख लीजिए ना भैया. Done? Okay, so here we go. If you talk about the power consumed, that's simply going to be P equal to VI. P equal to VI, basic formula revision quick, or V square by R or I square by R. Okay. If you talk about power consumption in series by bulbs connected in series. So what is going to be the expression? This is going to be the expression for series and this is going to be the expression for parallel. This is going to be the expression for series and this is going to be the expression for parallel. Remember this, okay? Remember this. Okay. Apart from this, if you talk about the time taken to boil the water through the heater coil, if the coils are connected in series and if the coils are connected in parallel, the time is going to be T1 plus T2 and T1 T2 upon T1 plus T2. Remember this, direct. Okay. Power is nothing but rate of heat flow, dH by dt or dq by dt. So you can simply write dH is nothing but P dt. You can integrate it. Okay. So this is the expression for heat. Okay. In front of you. So here we go. Okay. Now, if you talk about the concept of fuse wire, we know that basically why we use a fuse wire. Fuse wire is there in the situation because in case more than permissible amount of current enters the circuit, the fuse breaks and it saves the circuit. Okay. So made up of an alloy of tin and lead. I is proportional to R to the power 3 by T. Low melting point, low boiling point. Okay. And it is independent of the length. Remember it. High resistance. So now, if you move along the direction of current, try to understand along what direction the current flows. Along what direction of potential does the current flows? From higher to lower or from lower to higher? From higher to lower or from lower to higher? We know that the current flows from higher potential to the lower potential. So if this is A and this is B, this is higher potential, this is lower potential. So how do we write the expression? Let's say you are standing at this point. Bring your friend. Who is your friend? Call him. It's been long. He has not entered the discussion. Mr. Sontu. He is moving from A. He is crossing the resistance and he is reaching the point B. He is moving from A, crossing the resistance and reaching the point B. Okay. So, moving from A to B, how are we going to write the expression? VA minus IR equals to VB. Okay. This is how we write the expression. If you're moving along the direction of the current, potential always decreases. So onto moving from higher potential to lower potential, current has decreased. Same expression can be written this way. Are these both expressions same? Definitely yes. This and this both are same. So it's up to you. Whatever you want to write, you can write it. Okay. Remember this. If this is the battery, I am moving from P up till Q. So what am I going to write? Again call Sontu. No, this time call someone else. Call Sonti. Call Shinti. This is Shinti. Okay, Shinti is here. Going from P to Q. So this point is VP. From plus to minus. So minus. And you're going to Q. So this is VQ. This is how we write the expression. Tell me yes or no. Quick. VP minus E equal to VQ or VP minus VQ or simply VP minus VQ equal to E. I hope that this point is absolutely fine. Cool? Okay. Who wants to sit? Who wants to come in the discussion over here? Okay. See, similarly, if you go along the direction of current, now we are calling Mr. Okay, let's call Mr. Sunil. We are calling Mr. Sunil. Okay, this is Mr. Sunil. Have a look at the hairstyle of Sunil. Sunil is going from Q to P. So what is he going to write? VQ. Okay. -2 plus. Okay. VE. E. Okay. There is an internal resistance. Draw the internal resistance over here. Okay. Minus IR. Okay. Equal to. Okay. What? Okay. VP. This is the expression. In front of you. This is how we write the expression. I hope that the point is absolutely clear. Nadir Khan is saying, asking me to take rest. I will not take rest till the time your syllabus is finished, till the time you reach your desired college. Okay. So let's take the discussion ahead. You also don't have to take rest till that time. I hope that this discussion is absolutely fine. So here we go. When electric field is applied, average drift velocity of free electrons is of the order of this much. This is very small. Okay. This is very small. And the path of free electrons between the two consecutive collisions is a curve. That means this is one electron coming here, striking and going somewhere else. Two electrons coming, striking and going somewhere else. So just imagine that one electron striking the other and going and strike the third electron. Then that electron is striking someone else. Then that is striking someone else. Okay. So what are we saying? The electrons are continuously under random motion and they are moving in a particular direction. They're drifting in the particular direction. And this velocity, this speed is very slow. What will happen if you increase the temperature? If the temperature of a conductor is increased, definitely their collisions are going to increase. Isn't it? Their collisions are going to increase. Yes. And if the collisions are going to increase, their relaxation time is going to decrease. So the resistance is going to increase. Don't you think so? That there is going to be, the transfer of electron is going to be problematic if you increase the temperature. Isn't it? Yes. So metals have high positive temperature coefficient of resistance, whereas the semiconductors and insulators have a negative temperature coefficient of resistance. If you talk about metal, you increase the temperature, resistance increases. But about the semiconductor, that's opposite. Okay. Let's take the discussion ahead. Next question coming in front of you. Potentiometer, this is a bit earlier they are asking. Come to this question, okay? Do this question, all of you. VA minus VB, the potential difference between the point A and B. NEET 2016 phase 2. I am giving you 45 seconds for this question. Have a look at the circuit and give me the answer. Quick, all of you. Fast. Quick. Do this question. 10 seconds more. Fast. Go through the circuit. Okay. So I am solving this question. For you. Listen very carefully. What you need to find out? You need to find out VA minus VB. So someone, let's take someone from you who wants to come and sit in the situation, who wants to walk through the circuit. So we are taking, who wants to join the circuit? We are taking, we are taking Nadir Khan. Okay. We are taking MD Nadir Khan. So Nadir is standing over here. This is Nadir. Okay. Have a look at the hairstyle. 3 hairs, total 3 hair. So Nadir is moving from VA to VB. Nadir is moving from VA to VB. Okay. So while he is at A, the potential VA. If you are moving along the direction of current, I clearly said that along the direction of current, along the direction of current, what is going to happen? The potential is going to decrease because current flows from higher to lower potential. Yes. So this is going to be VA minus I into R. R is 2. Plus 2 minus. Plus 2 minus. This is going to be minus 3. Okay. Again along the direction of current. Minus I into R. R is 1 equal to VB. Oh. What it's going to be? I is 2. So 2, 3 and 4. 2, 3 and 4. 4, 3, 7, 7 to 9. This is 9. So 9 volt is the answer. 9 volt is the answer. 9 volt is the answer. I hope that this point is absolutely clear. I hope that this point is absolutely clear. Okay. Let's try one more circuit. Let's try one more circuit. Let me check a circuit. Okay. Just a second. Yeah, let's do this question. Let's do this question. This one. Do this question. Do this question. Power dissipated in the 9 ohm resistor in the circuit is 36 watt. The potential across the 2 ohm resistor is going to be what? How much time do you require for this question? How much time do you require for this question? I think only 30 seconds you will get. Only 30 seconds you will get for this question. Parallel combination, potential remains same. Parallel combination, potential remains same. Quick. Fast. Time up. Yes, definitely Himanshu, we will do. Don't worry. But focus on the questions. These questions are from NEET, JEE and every good exam we are taking in this session. So please focus and give the answer. Be participative. Okay. Very good. Very good. Shruti. Very good. Riya. Very good. Nadia. Very good. Amitabh. Good. Yes. So what is power? Power has been given to you as how much? Power has been given to you as 36. So we know that P equals to I square times of R, isn't it? P equals to I square times of R. Now the power in the 9 ohm resistor has been given to you as 36 watt. How much it has been given? It has been given to you as 36 watt. So this is going to be I square into R. How much is R? R is 9. Okay, so I is going to be 4 root over 4. That means 2. You need to find out the potential difference across the 2 ohm resistor. So if let's say this is I1, this has to be I2, isn't it? And this has to be I. This has to be I. Isn't it? So simply what you need to find out? You need to find out the value of potential drop across this particular capacitor, resistor. So how much is the current? How much is going to be the current? You can simply say V equal to IR. This is 2. If this is 2, I1 is 2. Okay. How much is going to be the current over here? How much is going to be I2? How much is going to be I2? You can write that I is going to be nothing but, or let's say I2 is going to be nothing but I times of R2 or R1 upon R1 plus R2. Isn't it? And you can say I1 is nothing but, remember this concept, very important discussion. This is current division formula. I1 is nothing but I times of R2 divided by R1 plus R2 because the current follows the least resistance path. Yes, we know. So I1 has been given to you as 2. I, you need to find out R2, that is 6 divided by 6 plus 9 is 15, isn't it? So I is going to be 30 divided by 6, that is 5. So if this is 5, what is going to be the potential? V equals to I times of R. That is simply going to be 10. Easy? Easy, 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 yes or no? Or how can you, sir, how can we find out the potential? How can we find out the current if we don't want to apply the current division formula? You can simply say that potential across 1 is equal to potential across 2 and V is equal to I1 R1. I1 into 9 equal to I2 into R2, that is 6. So from here you can find out R2, from here you can find out I2, and you can find out total I, whatever you like, whatever you like. Whichever method you like, you can simply apply and get the answer. Okay, is this point very clear? All of you, let's take the discussion ahead. Let's take the discussion ahead. Let's do some more questions on the circuit. Then we'll introduce a new concept. Just a second, let me find some more questions on the circuit. Okay. Yeah, try this question. Try this question. This is a good example. This is a good example. And this is a very simple example. No, not this one. This is a simple example. Anyways, do this. Find the current I1 in the given circuit. You need to find out the current I1 in the given circuit. I1, you need to find out in the given circuit. Okay. Think about it. I am giving you 45 seconds for this question. Plus 4, minus 1. 45 seconds. I1 you need to find out. I1 you need to find out. Quick. Observing your answers. I am observing your answers. Fast. Quick. Quick, very simple question this is. Don't worry, Shalini, just focus over here. You will get the questions. Banenge question. Fast. Time up. See. Have a look at the circuit. Okay, you need to find out I1. Okay. What can we do? There are more than one batteries. There are 2 batteries, okay? There's more than one battery in the situation. So in this situation, we need to figure out the potential of different points. This is the concept. So what to do? Let's take this point at 0 potential. Okay, that's fine. 0 potential. Okay. So if we, now who wants to come in the discussion? We are bringing Nadia. Okay. Nadia is over here. Nadia is going from this point to this point. Okay. She is moving from negative to positive, so potential is going to increase. That means the potential of this point is going to be plus 4 volt. Yes or no? Yes or no? Is this concept very clear? This point is having a potential of plus 4 volt. Now this point is going to have how much potential? Minus 2 plus. That means again plus 2. So this is plus 6 volt. Okay. Now tell me that what is the potential difference between these 2 points? 4 minus 0, 4. 4 minus 0, 4. Isn't it? Yes. Divided by I. This is going to give you current. I equal to V by R. 4 minus 0 divided by 1, that's 4. 4 ampere. Okay. The current over here, let's call it as I2. This is 4. Let's call it as I3. This is going to be 6 minus 0 divided by 1. This is 6. If this is I1, you can say I1 equals to I2 plus I3. I1 is equal to I2 plus I3. Okay. So this is nothing but 4 plus 6. This is nothing but 10. This is nothing but 10. Ta-da! Okay. Is this point absolutely clear, all of you? Point clear or not clear? Okay. Let's try one more question. Let's try one more question. I'm giving you one more question, okay? Based upon the loop. Based upon the loop. Now read this question. Read this question. What this question says, you need to find out the equivalent resistance between X and Y. You need to find out the equivalent resistance between X and Y. So basically what the concept of equivalent resistance is, what is the concept of R equivalent? We know that if you have this kind of combination, if you have series combination, okay, then what is going to happen? What is going to happen for series combination? The current passing through the circuit is going to remain same. The current passing through the circuit is going to remain same. This is R1, this is R2, this is R3. Let's say this is I. Okay. So you can say that the total potential drop is going to be V1 plus V2 dot 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 up till Vn. So R equivalent I is same, that gets cancelled out. This is nothing but R1 plus R2 plus R3 up till Rn. Okay, this is the concept. Okay. Now if you have parallel combination, in front of you, then what you're going to say? You are going to say that for this situation, the current that is coming in is going to get divided into the circuits I1, I2, I3 dot 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 up till In. I1, I2, I3 up till In. Definitely yes. So 1 upon R equivalent is going to be 1 upon R1 plus 1 upon R2 plus 1 upon R3 dot 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 1 upon Rn. Okay. Yeah. So now have a look at this question. Simple question this is. It's a very simple question. Read this question. How much time do we require for this question? I think 45 seconds would be sufficient. What do you say? Shall we begin? All of you? Okay, so here we go. 3, 2, 1. The time starts now. All of you. +4, -1. Keep on marking your answers. Keep on marking your answers. Quick. Okay. Quick. All of you. Okay. Finally, last 10 seconds. Last 10 seconds, all of you. 5, 4, 3, 2, 1, and time up. Now see, what you need to do in this situation? Let's say this is point X. So this is X, this is X, this is X. Okay. That's why let's call it as Z. If you talk about this resistor and this resistor, okay, resistor number 1, resistor number 2, they both are having a potential difference of how much? They are having a potential difference of XZ about them. Okay. So this is terminal number X. This is terminal number X. This is R. This is R. Let's call it as Z. Okay. Let's call it as Z. Listen. Let's call it as Z. Let's call it as Z. Okay. So this is R. This is R. And this is R. Okay. If you talk about this particular resistor and this resistor, XY and YZ. XY and YZ. That means there is a resistor between Y and Z. Let's call it as Y. And there is a resistance between X and Y. So this is the combination. This is the equivalent circuit. This is the equivalent circuit. This is the equivalent circuit in front of you. This is the equivalent circuit. So now tell me that how much is the equivalent of these two? This is R by 2 and this is R by 2 plus R. R by 2 plus R. This is in parallel with R. This is in parallel with R. So it is going to be R by 2 plus R. This is 3R by 2 plus R. 3R by 2 plus R. That means 5R by 2. 5R by 2. Oh, sorry, this is in parallel. So C1, C2, just a second. This is how much? This is R by 2 plus R. Okay. And this is in parallel with R. So R by 2 plus R, that's 3R by 2. 3R by 2 into R divided by 3r by 2 plus r. Arrange this, how much do we get? Arrange this, how much do we get? This is 3r square by 2 divided by 5r by 2. Okay, so this is nothing but 3r by 5. That means answer is C. Very good, very good. All of you have given the correct answer. Nice. Okay, A is not the answer. These two, this final and this are in parallel. So C equivalent for parallel is C1 C2 divided by C1 plus C2. We know this. Okay, I hope that this point is absolutely clear. Now we are taking the discussion ahead quickly. We have done a lot of questions on the circuit, and now we are going to begin with the devices. Let's check. The questions are a bit mixed. Okay, questions are being bit mixed, you know. Okay. Okay, so here we go. Read the question. All of you. Read the question. What the question says, the question is related to meter bridge. So basically, what is a meter bridge? Okay, let me tell you what is a meter bridge. Okay. Meter bridge, we are talking about an electrical instrument, electrical device, that's meter bridge. Okay. It works on the principle of Wheatstone bridge. So basically, what is Wheatstone bridge principle? Simply, if you have a circuit, something like this, try to understand. Okay, in which this is a resistance R1, another resistance R2, R3, R4. Okay, place a galvanometer in between. Okay. So if this is the circuit in front of you, and you have the balanced condition, if you talk about the balanced condition of Wheatstone bridge, then what's going to happen? R1 by R2 equals to R3 by R4. Then what? Then the potential across the terminals. Let's say this is A, this is B, this is C, and this is D. The potential across the terminal at the point A and at the point D is going to be same. Okay, it's going to be same, isn't it? So in this situation, the current through the galvanometer is going to be 0 for the balanced condition. Now we can use this principle. In a device, that's what we call as the Wheatstone, called the meter bridge. And what we do, we find out the value of the unknown resistance. Now see, let's imagine that if you have a circuit something like this, okay, the circuit that's given in front of you. Okay, this is the circuit, this is a wire, okay, this is a galvanometer, and this is the jockey. So what you're going to do, you're going to touch the jockey at different locations, okay, corresponding to the different length of the wire, you are going to get different resistances. Yes, that means if you touch the jockey at this location, let's say this is L1, so there is going to be certain amount of resistance associated with this wire. If this is L2, this is R2. Okay, this is L2, this is R2. Let's use a galvanometer over here. Okay, so this, where it has gone? Just a second. Yeah, here we are. Okay, here we are. Yeah. So in this situation, there are going to be different resistances corresponding to the length. Yes or no? Definitely yes. Yes or no? Yes. So what? So there is going to be a certain length. in the situation at which you are going to get zero deflection, at which you are going to get null deflection. And what is going to be the condition of null deflection? Let's say this is the known resistance X, this is the unknown resistance Y. So you can say X divided by R1 must be equal to Y divided by R2 for the balanced condition, okay. And what is R? R is equal to rho L by A. Now wire is same, so L and A for R1 and R2 are going to be same. So you can simply say X divided by L1 is equal to Y divided by L2. X divided by L1 equals to Y divided by L2. So now based upon the concept, you can do this question. Read the question. Okay, before this, let's try a basic question that's over here. First, do this question first, okay? For the balanced state of the meter bridge, find out the value of X. This is the value of X. This is 40 centimeter. This is 4. Only 20 seconds for this question. Only 20 seconds for this basic question. The time starts now. The time starts now. Quick. Quick, quick. Fast, all of you. Fast, all of you. And time up. Time up. Time up. Okay, so what's the answer? Ravi Verma, Ria, Royal Army, Ishika. Everyone give the answer. What are you going to write? You're simply going to write that 4 divided by 40 is X divided by 60. So what is it going to be? This is 10. This gets cancelled out. X equals to 6. That means the answer is D. Simple. The answer is D. Answer in front of you is going to be D. Okay. Now one more device that we have that works on the same concept is what we call as the potentiometer. Okay. So now just a second. So here we go. If you talk about the potentiometer, basically it has two circuits. One is what we call as the primary circuit and the other one is the secondary circuit. So let's say this is the primary circuit in front of you. Okay, this is the length L. And what are you doing? You're simply using battery, galvanometer, jockey. Okay. So at different locations, you are going to make the system balance, yes or no. So what you can say, you can compare the potential according to the length. You can compare the potentials with the length, isn't it? So if you are comparing the potential with the length, all of you, can you hear me? All of you, I'm going to give you the break at, let's say, we started at something about 8 now. So we'll have a break, might be at 10 or 10:15. Okay. Hello. Can you hear me? I'm asking you all. I think that the chat is a bit slow. So please keep on answering. Okay. I'm going to give you the break, but not right now. Okay. Might be after half an hour. Okay. So can you hear me? Please respond. Okay. That's cool. So the concept is that the potential gradient, potential per unit length, that remains constant. So what we are going to do, we are going to compare E with L. So for two different cells that you're going to use, primary circuit, secondary circuit, remove the battery E1, use the battery E2. That second battery is going to get balanced at some other point. So you can simply compare the EMFs of the two cell along with the length. E1 by E2 equals to L1 by L2. Okay. So here we go. Now there are some questions that I will leave as a homework for you. Okay. And now we are beginning with the concept of magnetic effect of current. Another question, another new chapter, another new conceptual part is coming in front of you. Magnetism, very important discussion. Okay. The point is that initially it was thought that the magnetism and the electricity are separate branches. Later on, people came to know that yes, they are related, and from one branch you can link the other. So we have studied the Coulomb's law, and what we have done in the Coulomb's law, we have found the value of electric field due to a charge. Now we have a current carrying wire. We know that due to a current carrying wire, there is some magnetic field in the vicinity. If this is a current carrying wire, if you bring a magnetic compass near it, so it shows certain amount of deflection, isn't it? That means there is magnetic field. There is magnetic field linked with the wire. with the current carrying wire. Yes. So you need to find out the magnetic field at the point P. For that we have the Biot-Savart law. For that what we have? We have the Biot-Savart law. So what the Biot-Savart law says? Biot-Savart law says that if you have a current carrying wire, you need to find out the magnetic field at any given point P. So the magnetic field due to this small current element, the magnetic field due to this small current element is going to be dependent upon current, length of the element, and inversely proportional to R square. Inversely proportional to R square. If you remove the proportionality, you get a constant mu naught upon 4 pi. You get a constant mu naught upon 4 pi. IDL sine theta divided by R square, because it also depends upon the angle. Okay, really sorry, it also depends upon the angle, sine theta. Okay, theta. So the point is, what is the direction? What is the direction? What is the direction? Direction of magnetic field is found by the unit vector. So you can say this is mu naught upon 4 pi I dl. This is going to be r cap. This is going to be r cap. So dl into r cap into sine theta, you can write it as dl cross r cap. dl into r cap into sine theta, a b sine theta, a cross b. A b sine theta, a cross b, definitely yes. Divided by the r square. Okay, that's fine. So you can say r cap, which is nothing but r divided by magnitude of r. So this is going to be the expression in front of you. This is going to be the vector form of Biot-Savart law. Now the constant that you see over here, this is mu naught upon 4 pi. This constant over here is mu naught upon 4 pi. And the value of mu naught upon 4 pi, remember, 10 to the power minus 7. Okay, 10 to the power minus 7. This is called permeability of the medium or of the free space. If you talk about mu naught, permeability of the free space, mu m, permeability of the medium. And how are the permeabilities related? They are related something like this. The way we related permittivity. Okay, is this point very clear? Okay. Simple question coming in front of you. Read the question. Dimension of magnetic field intensity. I am giving a question. I am giving the equation F equal to Q V cross B. F equal to Q V cross B. Okay, F equal to Q V B. This is the expression for the force. You need to find out the dimension of B. So how much time do you require? 20 seconds quickly. 3, 2, 1, begin. Only 20 seconds. Only 20 seconds. I am solving. You don't look over here. We can say B equals to F by QV. F is nothing but Newton. Newton is what? Newton is ml t minus 2 divided by charge. Charge is nothing but Coulomb. Coulomb is ampere into second, that is T. And what is V? V is LT minus 1. Isn't it? Isn't it? So what are you going to get? What are you going to get? You're going to get L gets cancelled out. L gets cancelled out. So this is M A minus 1. This is T minus 2. T minus 2. Do we have such option? M. Have we done something wrong? M. No, this one. MA minus 1, T minus 2. This is the answer. B is the answer in front of you, all of you. Okay, this is the answer. Let's take the discussion ahead. Next question in front of you is this. Sorry. The magnetic field dB due to a small current element at a distance R and element carrying current I is going to be 10 seconds for this question only. 10 seconds for this question. 10 seconds. Quick. Keep on marking plus 4 minus 1. Keep on marking plus 4 minus 1 quickly. Time up. What is going to be the answer? What is going to be the answer? If you talk about the expression, that is nothing but mu naught upon 4 pi. Mu naught upon 4 pi. I dl cross r cap. I dl cross r cap. What is r cap? R cap is r divided by. What is r cap? R cap is nothing but the r vector divided by the magnitude of r. So you can also write it as, if you substitute r cap over here, Listen, students, if you substitute r cap over here, it's going to be r divided by r cube. It's going to be r divided by r cube. That means amongst them, no, no, no. This is r vector. This is vector upon r cube. Yes, this is true. B is the correct answer. B is the correct answer. Okay. Venkatesan, what happened? What are you writing? Movie update? Should I block you? Don't do this. So important concepts we are discussing. Don't do these silly things, okay? Let's take the discussion ahead. Next question. Magnetic field at the center will be. This is the point P. Okay. This is the point P. Now see, before this, we need to understand the general form of Biot-Savart law. Before this, we need to understand the, just a second, where's the screen gone? Yeah. We need to understand the general formula for Biot-Savart law, okay, for finite or infinite wire. I am giving the general expression of magnetic field for finite current carrying wire, and we can generalize the discussion. If this is a current carrying wire, okay, let's say it is having some current I. Not a charged wire, this is a current carrying wire. Really sorry. This is a current carrying wire, and you need to talk about the magnetic field at the point P. You need to talk about the magnetic field at the point P. Okay. Let's say that the angles it makes with the axis are theta 1 and theta 2. Okay. Theta 1 and theta 2. All of you, theta 1 and theta 2 or alpha beta, whatever you want to write, you can write it. Okay. So the expression for the magnetic field for this finite wire is going to be mu naught upon 4 pi, whatever the separation is, this d, mu naught upon 4 pi d, mu naught I upon 4 pi d, bracket sine of theta 1 plus sine of theta 2. Okay, sine of theta 1 plus sine of theta 2. Is this point very clear? All of you. Now, if you talk about the infinite wire, if the wire is infinite, okay, that's fine. If the wire is infinite, then what's going to happen? Theta 1 equals to theta 2 equals to 90. So the magnetic field is going to be how much? 1 plus 1, 2. So this is going to be mu naught I divided by 2 pi d. I hope that this point is absolutely clear. Mu naught I by 2 pi d. Okay. If you talk about semi-infinite wire, one is 90, another is 0. Mu naught I by 4 pi d. Am I the only one who is understanding? Getting? All of you? This is a current carrying wire, and this is your friend. Who is your friend? Who is your friend? This is, who is this? This is Zuzu. Okay. Zuzu standing at point P. You need to find out the value of magnetic field at this particular point. Okay. So what is going to be the situation? That's going to be mu naught I by 4 pi d sine of theta 1 plus sine of theta 2. Angles you are taking from this point, let's say this angle is theta 1, this angle is theta 2. The angles are theta 1 and theta 2. Okay. Let's come back to the point. Infinite, this much, semi-infinite, one angle would be 90, another angle would be 0. Okay. So. Now you can give the answer for this question. One more second. What is going to be the direction? Let's talk about the direction also. If you have an infinite wire, if you have an infinite current carrying wire, that, let's say the current is I. Okay. So the direction of magnetic field in this region is inward like this, and in this region is outward. See, if you want to find out the direction of magnetic field, listen, if you want to find out the direction of magnetic field, this is the current carrying wire. Hold the wire something like this. Okay. Hold the wire like this. Okay. So this is the direction of magnetic field. That means if you are standing, if let's say this is your friend, who is your friend? This is Chintu, this is Chintu, this is Pintu. Okay, Chintu and Chinty. Okay, so if you talk about the direction of magnetic field at Mr. Chintu, it's going to be outward. It's going to be outward. If you talk about the direction of magnetic field at this point, this is going to be inward. So out, magnetic field is out, magnetic field is in. And what is going to be the value of magnetic field for infinite wire? That's mu naught I by 2 pi d. Now you can do the question definitely. Now you can definitely solve the question, all of you. Come to this question. The magnetic field at the center P, the magnetic field at the center P is going to be how much? Bring Zuzu. Where is Zuzu? This is Zuzu. He is standing at the point P. How much time do you require? Let's say 30 seconds for this question. 30 seconds or 45 seconds. Okay. But I want the correct answer. Correct answer. All of you. All of you, all of you, all of you. Fast. Answers. See, first of all, what's going to be the direction? What's going to be the direction due to the left wire? If you talk about the direction due to the left wire, that's inward. The direction due to the right wire, that's outward, isn't it? This is 1, this is 2. 1 and this is 2. Okay. So magnetic field due to 1 is in, due to 2 is out. So B net at that particular point is going to be nothing but B1 minus B2. That's going to be nothing but B1 minus B2. What is B? B is mu naught I divided by infinite wire 2 pi D. What is D? D is going to be 2.5. Okay. This is simply going to be I1 minus I2. Solve this expression. Solve this expression. Mu naught upon multiply 2 divide by 2. You get mu naught upon 4 pi. D is 5 by 2. D is 5 by 2. I1 minus I2 is again 2.5. That's 5 by 2. So how much do you get? This gets cancelled out. This gets cancelled out. This is 10 to the power minus 7. So the answer is going to be 2 into mu naught by 4 pi. That means mu naught by 2 pi. That means this. C. C is the answer. C is the answer. Okay. Is this one clear? It was a nice question. It was a nice question, but definitely it was simple. Not a tough question, but important concept. Okay. So here we go. 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 Come to the next question. Two straight long conductors A, O, B. This is one conductor. Let's color them. Okay, conductor number 1. This is conductor number 1. And COD, conductor number 2. Or DOC, whatever it is. Okay. Okay, that's fine. Okay, so what are they doing? They are carrying current. In what directions are they carrying current? It has been shown in front of you. I1, I2 are the currents. In the 2, the magnitude of magnetic induction, at the point P at a distance D from the point O in a direction perpendicular to the plane. Where is the point? They are saying that the magnetic induction at a point P at a distance D from the point O in a direction perpendicular to the plane. That means you need to come out of the plane. Okay. So if I draw the plane, try to understand, try to visualize in 3D. Okay, let's say this is the plane. Where is the plane? Plane. How can we observe the plane? Let's say this is the plane. This is the plane. Okay, this is the plane. And on this plane, see, this is the plane. And on this plane, There's wire number 1, something like this, wire number 2. You are out of the plane. You are out of the plane at this point. One current is over here, another current is over here. So can we find out the directions? Can we find out the directions? Let's see. This is wire number 1, somewhat over here. Wire number 2, somewhat over here. Okay. I1, I2. I1, I2. If you talk about I1, you're above the plane. So the direction is going to be where? I1. This pen is I1. And I'm at this point P. Okay. This is me standing out of the plane. This is me. Okay. KK. This is me standing out of the plane. I am standing out of the plane. So where's the direction of current? This is the direction of current. So the magnetic field is going to be inward, inside the plane. Magnetic field due to the other wire, L cross B, is going to be perpendicular to the previous one. Simply, the magnetic field B1 and B2 are going to be perpendicular because the current carrying wires are perpendicular. Since the current carrying wires are perpendicular, their magnetic fields are also going to be perpendicular. So you need to find out the B net. That's simply going to be what? That's going to be root over B1 square plus B2 square. Solve this and get the answer. Solve this and get the answer. All of you solve this and get the answer. Clearly, it is visible that the answer is going to be C. Isn't it? Answer is going to be C. Okay. Let's take the discussion ahead. Next discussion is circular loop. Now see, this is a circular loop. This is the current carrying circular loop. Okay. Current carrying circular loop. Okay, that's fine. So what is going to be the direction of magnetic field due to this circular loop? Imagine that this is a loop. Imagine in front of you, wherever you are sitting, just tilt to your right and look at the front wall. Okay. And imagine a big circle. Just rotate your hands clockwise. Okay. Curl your fingers along the direction of current. Thumb is going to give you the direction of magnetic field. Curl your fingers along the direction of current. Thumb gives you the direction of magnetic field. Getting what I'm saying, all of you? Oh, are you getting what I'm saying, all of you? Is this point very clear? Curl your fingers along the direction. The thumb gives you the magnetic field. Okay, thumb gives you the direction of magnetic field. Curl your fingers, something like this. And what's going to be the expression? The expression for the magnetic field, remember the expression, that's going to be mu naught I R square divided by, in the previous expression in case of electric field, there was no 2 in the denominator, but here we have 2 times of R square plus X square to the power 3 by 2. 3 by 2. Okay, that's fine. And if you substitute X equal to 0, you get the magnetic field at the center. Of a current carrying coil. That's going to be how much? Simply substitute X equal to 0. This is what? This is mu naught I divided by 2R. 99% students get confused in the expression for the magnetic field at the center and the magnetic field due to current carrying wire. Remember the difference. In case of current carrying wire, what are we saying? If this is an infinite current carrying wire, okay, infinitely long current carrying wire, so the magnetic field is nothing but mu naught I divided by 2R. Okay, sorry, 2 pi R. Mu naught I by 2 pi R. And what's going to be the magnetic field due to this loop, current carrying loop? Okay, let's say you're talking at the center, so the magnetic field is going to be mu naught I divided by 2R. Okay, very important, very important. Okay, very important discussion. Okay, so I hope that you're going to remember this discussion. So now what if we talk about half loop? Sir, now what if we talk about half loop? Okay, that means semicircular loop. Let's say this is a semicircular current carrying loop. This is carrying current something like this. Okay, this is the current carrying wire and this is the situation. So in this situation also there is going to be magnetic field. Okay, but how much? This is going to be half of the total. What is total? The magnetic field due to the loop. So what is the magnetic field due to the loop? The magnetic field due to the loop the magnetic field due to the loop is mu naught I divided by 2R. Okay. So sir, what if you take the segment which is making some angle theta? What if you take the angle theta? So we have to compare. We have to compare with what? With the total value. We have to compare with the total value. That means B dash is going to be unitary method. Unitary method. B times of theta by 2 pi. B times of theta by 2 pi. That means B dash is going to be mu naught I by 4 pi r into theta. This is going to be the expression. Okay, this is going to be the expression for arc. This is going to be the expression for arc. Okay, I hope that this point is absolutely clear. Very, 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 very important discussion. Okay, all of you, please note these things. 100% I can give in written that questions are going to be asked from this discussion. JEE, NEET, CUET, whatever exam you talk about. Okay, so this is very important discussion from every single examination point of view. So another conceptual question coming in front of you, another nice question, another beautiful question coming in front of you is this. Read the question, what it says. Read the question, all of you. A straight conductor carrying a current I splits into two parts. Splits into two parts. Yes, I1 and I2. Okay, that's fine. So in this situation, what are you having? Let's say this is the current coming. This is the current entering. Current entering is I. Okay. Let's say this is one resistance. Let's say this is one resistance, and this is another resistance in front of you. Okay, this is I1, this is I2, this is R1, this is R2. There is wire, so there is resistance now. There is wire, so there is resistance now. Definitely yes. Isn't it? So if you talk about the direction, of magnetic field due to I1, that's inside. If you talk about the direction of magnetic field due to I2, that's outside. Isn't it? Oh, Chitrali is saying, a question. You have mugged this question up. Don't do that. Okay. Although it's a symmetric situation, you directly know the result. But the point is that what's going to be the magnetic field? What's going to be the magnetic field due to this segment? If I talk about the magnetic field due to segment number 1, that's going to be B, total magnetic field times of theta by 2 pi. How much is theta? Theta is 270 degree. 270 degree can be written as 3 pi by 2. 270 degree can be written as 3 pi by 2 divided by 2 pi. Okay. This is the expression for B1. Similarly, the expression for B2. B2 is going to be B times of, B means the magnetic field due to this complete circle, times of theta pi by 2 divided by 2 pi. But the question arises, let's say this is B1, let's say this is B2. What is B? B itself depends upon current. What is B? B is mu naught I by 2R. So B1 is mu naught I1 by 2R and B2 is mu naught I2 by 2R. Listen very carefully. Current is going to, listen. Current is going to get divided in the ratio of the resistances. Yes or no? Agree? Think. Orally. We will solve this question orally. Current is going to get divided in the ratio of resistance. Yes or no? How many of you agree? Greater the resistance, lesser the current. Yes or no? Definitely yes. So if the resistance of the first part is greater, the current is going to be lesser. Yes or no? Lesser current, and the magnetic field is inside. Greater current, magnetic field is outside. But the magnetic field also depends upon the area. Okay. Overall, when you calculate this, the value of B1 and B2 is going to come equal and opposite for the two cases. The value of B1 and B2 is going to be equal and opposite, because the current is going to get divided in such a ratio that these are going to cancel out each other, and the net net magnetic field is going to be 0. And the net magnetic field in this situation is going to be 0. Remember this discussion directly. Okay. Remember, let's take the discussion ahead. Here we go. Charge Q is uniformly spread over a thin ring. This is a very beautiful concept. Very important concept. Very beautiful concept this is. Okay, this is being asked in NEET, AIMS, okay, and as well as in JEE. It has been a PYQ of every good examination. Charge Q is uniformly spread over a thin ring. Charge Q is uniformly spread over a thin ring. This is a thin ring and this is a charge Q. This over here is a charge Q. Okay. The ring rotates about its axis with a uniform frequency f, the magnitude of magnetic induction at the center of the ring. Now see what is happening. The ring is moving. The ring is rotating. The ring is moving. So the charge is moving. Don't you think that if there is a flow of charge, don't you think that if there is a flow of charge, there is current in the situation? Isn't it? And where is the magnetic field? Where is the magnetic field? What have they said about the magnetic field? Sorry, there is a current carrying wire. Imagine that this system, if it rotates with some frequency, is it equivalent to a current carrying? Is it equivalent to a current carrying wire? Yes or no? Yes or no? First of all, give me the answer. Is this system equivalent to a current carrying wire? Is this system equivalent to a current carrying wire? All of you. Yes or no? If yes, what is going to be the current? Current is simply charge flowing per unit time. Charge upon time, that means Q into F. What is the magnetic field induction at the center? That's mu naught I divided by 2 times of R. What is I? I is nothing but, what is I? I is nothing but Q into F divided by 2R. This is the value of magnetic field. This is the value of magnetic field at the center. This is the value of magnetic field at the center. Listen, everyone. Charged ring, make the ring rotate. Charge is moving if the ring is moving. If this is my hand and my hand is charged, I am moving my hand like this. Don't you think that charge is moving? Oh, charge moving, charge is moving. So there is going to be current in the situation. And this is moving with what frequency? It is moving with F frequency. What is frequency? Frequency is 1 upon time period. Yes or no? So what is current? Current is Q by T. Current is simply Q by T. That means Q into F. Nikita, Subhansh, Subhakshan Das, and everyone. Is this point very clear? Done? So what's going to be the answer? This is going to be the answer. That means the answer is B. Okay. So I hope that the discussion is absolutely clear. Now the next point that's coming in front of you, if a long current carrying wire or carrying a steady current is bent into a circular loop, okay, this is a wire, okay, if you bend this wire into a loop of n turns, okay, then the magnetic field, remember one thing, total length is going to remain constant, total length is going to remain same, okay, this is 2 pi r, these are n times of 2 pi r, okay. What is magnetic field? That's mu naught times of n into I. In this situation, in the first situation, there is current through one loop, and in the second situation, there is current through n loops. In the second situation, there is current through n number of loops. Yes or no? So the total magnetic field is going to depend upon n, and there is a n involved in current also. So this is going to be n squared times of B. Very important discussion. Okay, direct concepts that you need to remember. Remember the discussion. Okay, so here we go. Another question coming in front of you. The distance from the center of a ring where the magnetic field is B naught by 27, where B naught is the magnetic field at the center. So you know that B naught magnetic field at the center, mu naught I divided by 2R. What is the magnetic field at some distance? B dash, B dash. How much you need B dash to be? That's mu naught by 27. That's B naught by 27, and that's going to be mu naught I R square by 2 times of R square plus X square to the power 3 by 2. Isn't it? To the power 3 by 2. So just substitute it, solve it. This is a homework for you. Simple, just substitute it, calculate and solve it. This is the homework for you. Okay, so let's take the discussion ahead. Now what we are talking the magnetic field due to a hollow cylinder. If this is a hollow current carrying cylinder, the whole current is through the outer surface. If the cylinder is hollow, the whole current is through the outer surface, isn't it? There is no current inside. That means if you talk about this bottle, or if you talk about this dabba, this is the box, the current is only through the surface. If I put my hand inside, there is no current. Current is only through the surface. Yes. If I touch the surface, I feel the current. If I get inside, no current. Okay. So what we say that the current inside is 0. Okay, that's fine. So according to the Ampere circuital law, what it says that integral of B dot dl equal to mu naught times of I enclosed. So if I enclosed is 0, magnetic field inside is 0. If you talk about the magnetic field at some outer point, let's say this is out and you are standing at this point, okay, so what is going to be the magnetic field? The whole current you are going to consider to be passing through the center. The whole current you are going to consider to be passing through the center. Okay, the total current you are going to consider to be passing through the center itself. Okay, that's fine. So the magnetic field is mu naught I by 2 pi r. Simple. If you talk about the solid cylinder, okay, then what's going to happen for the solid cylinder? This is the situation of a solid cylinder. Okay, throughout the system there is current. Okay, something like this. So if you talk about the magnetic field at any point inside the cylinder, let's say you are standing at this point. Okay, so the magnetic field at any point inside the cylinder is this much. Just remember it's proportional to R. Same thing that we have seen. फिर से आ गया ये बेशरम. बता दें. Just a second. Okay. Yeah. So what I was saying that this situation is exactly same as that of the solid shell, solid sphere. Okay. So B out is going to be, if you come out, that makes no difference. It is going to be exactly the same situation that you consider the current to be passing through the center. Okay. So another important discussion. Come to the question. Read the question. What it says: cylindrical conductor of radius r carrying a current. Plot the graph of magnetic field with the distance from the center. Okay, cylindrical conductor. Only 10 seconds for this question. Okay, 3, 2, 1, begin. 10 seconds for this question. All of you get started. This is a hollow cylinder. Okay, hollow. Quick. Time up. If you talk about the inner region, so when you are in the inner region, magnetic field is 0. When you come out, the magnetic field varies inversely to R. So this is going to be the expression. This over here is going to be the expression in front of you. This is the graph in front of you. Okay. Let's take the discussion further. Another important discussion is the solenoid. So what is basically a solenoid? Solenoid is an arrangement of infinitely long wires, a lot of wires together. A YD. We are talking about hollow cylinder. We are talking about hollow cylinder. See, I have written hollow over there. Listen, students, I have written hollow. I am talking about hollow cylinder. Okay, if you talk about solid cylinder, This is true for solid. This is true for hollow. Okay, they have not mentioned. So let's remove hollow from here. This is correct for solid. This is correct for solid. That is correct for hollow. Okay, clear? Is this point clear? They have not mentioned, so we have mentioned it. Okay, let's take the discussion ahead. Okay, so what is solenoid? Solenoid is an arrangement of infinite long wires. Arrangement is such that the diameter of the system is lesser than the length of the solenoid. Okay, so what are the important terms that we need to understand? First of all, n, small n. Small n is nothing but the number of turns acting per unit length. Small n is nothing but the number of turns acting per unit length. Okay, what is going to be the magnetic field at any point inside? Before getting into the value of magnetic field, just try to understand it. If this is the system, okay, you need to find out the magnetic field inside. Take a curl, okay, of your fingers. Curl your fingers, something like this. Okay, something like this. Just curl your fingers. This is going to give the direction of magnetic field. That means magnetic field is inside. Okay, and how much it is? Remember, B equals to mu naught Ni. N is the number of turns per unit length. If you talk about the magnetic field at the end of a long solenoid, it's simply half that of the magnetic field inside. Now, if I turn this system, what is going to be? If I tilt this system, if I join this system, this becomes a toroid and it looks something like this. Okay, from one side you are sending the current, from one side the current enters, okay, it goes and comes back. The magnetic field is only going to be in this region, in this white region. Okay, only inside this region there is going to be magnetic field, there is going to be presence of magnetic field, and it's how much? It's this much. If you talk about the length, what is n? N is the number of turns per unit length. And what is length? Length is 2 pi r. Now the question arises that sir, there is R1. Okay, there is R1 and there is R2. So which radius are you going to take, R1 or R2? So we take the mean radius. Just remember the discussion. Okay. Yeah, we are taking the break. But just after some time, we'll finish this concept and then we'll take the break. Okay. Might be in next 10 minutes. Okay. Just in next 10 minutes. All of you. Read the question. Two toroids 1 and 2 have total number of turns this and this. Average radii also have been given. Carry the same current. The ratio of magnetic field 10 seconds. Only 10 seconds for this question. Fast. Only 10 seconds for this question. Quick. Time up. What is the magnetic field due to a toroid? Simply mu naught Ni. What is N? N is the number of turns per unit length. 2 pi r. R is the mean radius that has been given to you. Okay. So just substitute and compare clearly. 200, 100. 200, 100. Okay. 200 and 100. That means if we compare 2:1 and this is also 2:1, that means answer is going to be same. If you take, okay, if you just divide them, the ratio is going to get divided. The ratio is simply going to get 1:1. Okay. Because the data is given in such a way. Okay. Let's take the discussion ahead. Here we go. This is a very nice conceptual question. Very nice conceptual question. Okay. So read the question. What it says. Which of the field patterns given below is valid for electric as well as for magnetic field? This is a very nice conceptual question. Let's see how many of you can do this. So I'm giving you 20 seconds. If you know the question, you will do. There's no need of taking much time in this question. Timer is not coming. Anyways, you start. Give the answer. Oh, what happened? 20 seconds for this question. Quick, all of you. Begin. A, B, C, D, A, B, C, D, A, B, C, D. Okay. Let's see. Finally, time up. Okay, 20 seconds should be sufficient for this question. Now, if this is a charge, this is true for a positive charge, but this kind of field cannot be for magnetic field. Magnetic field cannot be represented by this diagram. See, electric field, possible. Magnetic field of this pattern, not possible. Electric field of this pattern, possible. Magnetic field, not possible. If you talk about this situation, magnetic field possible, magnetic field possible, but see, let's say if this is a positive charge, this is a negative charge. Okay, no, not a magnetic field is also not positive for this one. See, because the lines are getting out from here and they are getting out from here, coming in, getting out. So this is absurd. This is completely absurd. This is absurd. Okay, so this makes no sense. This makes no sense. This is wrong. This is very important. This point is very important. Try to understand, because we know that this is the pattern of magnetic field. Yes, this is the pattern of magnetic field. We know if there is a wire, current carrying wire, this is the magnetic field. If you have changing magnetic field, there is going to be presence of induced electric field, and this is the direction of induced electric field. This is a very important concept of EMI, the concept of induced electric field. This is the concept of induced electric field. Yes, this happens. We'll be studying this in the next chapter, EMI. Okay, so C is the answer. Please note it down. This is a very beautiful question, very nice conceptual question. Okay, after this, the next point is the Ampere circuital law. Ampere circuital law, what this law says, it simply says that integral of B dot dl, the line integral of magnetic field, is going to be mu naught times of I enclosed. That means if you have n number of wires, okay, and these are the directions of current, take a loop, something like this. You have taken the loop something like this, I1, I2, I3, I4. So which currents are you going to include inside the expression I1, I2 and I3? How you are going to include for this situation? I1 minus I2 plus I3. Okay, I1 minus I2 plus I3. Okay, so what are the important points? What are the important points for the situation? Closed line integral, not flux, always valid. This, see, in lot of books it has been written that Ampere circuital law is only valid for symmetric figures. No, it is valid everywhere. But if you apply this law to symmetric situations, you can easily get the answer. Is there some difference between the two statements? Law is only valid for symmetric figures. Law is valid everywhere, but if you apply for symmetric figure, you get the answer easily. This is what the point is. Okay. This is what the point is. So we are talking about the closed line integral. Okay. We are not discussing about the flux in this situation. Always valid, but not always useful. Valid always, but useful only in symmetric. Okay, symmetric figures. Magnetic field due to all current sources. Current is only due to the enclosed. See, I enclosed is only the current that is enclosed inside the figure, inside the loop. Okay, is this point very clear? But the magnetic field in this situation is due to all the wires, same as that of the Gauss's law. All wires. Okay, same as Gauss's law, Okay, remember this. I hope that this point is clear. Very, very, very important discussion. Okay, that means if you talk about the magnetic field, this is going to be due to 1, 2, 3, 4, but the current is going to be only due to 1, 2 and 3. This is what the discussion says. Okay. Okay. Next point, the magnetic force. We know that if we talk about the properties of a charge, on the basis of its motion, then what we can say? We can say that if the charge is at rest, if it is moving with constant velocity, and if the charge is accelerated, okay, if the charge is at rest, it generates only electric field. Along with the electric field, there is going to be presence of magnetic field. Okay, and accelerated charge, electromagnetic radiations, electromagnetic waves. Now what we are saying, we are saying that if there is a charge, imagine that there is a charge which is moving, q charge is moving, so definitely there is going to be some magnetic field linked with this charge. There is going to be some magnetic field linked with this charge. Yes or no? Definitely yes. And what if this charge enters, a region of magnetic field? Let's say this is the region of external magnetic field. This is the region of external magnetic field. Okay, this is the magnetic field due to the charge, and this is the external magnetic field. Don't you think that there is going to be a fight between the two magnetic fields? Isn't it? There is going to be interaction of the two magnetic fields, and there is a force acting on the charge due to its velocity. That is F equals to Q V cross B. F equals to Q V cross B. Remember the discussion? V cross B. That means F equals to Q V B sine theta. Q V B sine theta. So if the angle theta is 0, there is going to be no force acting on the charge. There is going to be no force acting on the charge. See, if this is the magnetic field, and let's say that the charge is moving along the direction of magnetic field, so the force is 0 because the theta is 0. Okay, that's fine. If the magnetic field is inside the plane, something like this, magnetic field is inside the plane B. Okay, this is the direction V. Okay, this is the charge Q. This is the charge Q moving with some velocity V. So there is going to be a force acting V cross B in the upward direction. Okay, in the upward direction. Okay, so what is going to be the force? F is equals to QVB. Now the point is that what's going to be the motion? The moment this particle enters, it's going to curve, it's going to turn. Okay, it's going to turn. Now what if a charge is moving with some velocity V, and suddenly completely in every possible direction you are applying a magnetic field? Let's say this is the magnetic field. Suddenly that you turn on, you have a source of magnetic field. Try to understand, you have a source of magnetic field and you turn on the magnetic field. So there is going to be a force acting on this charge particle, and this is going to move in a complete circle. And what are you going to write? And what are you going to write in this situation? You are going to write that if the particle is moving in a circle, that means if theta equals to 90, the centripetal force is going to be provided by the magnetic force. What is the centripetal force? That is Q, that is mv square by r. mv square by r equals to qv cross b. Okay, that is qv cross b. So v gets cancelled out. So what is going to be the expression for r? What is going to be the expression for r? R equals to mv by qb. Okay, mv by qb. Now in this situation, if you talk about the work done, since force and velocity both are perpendicular, the work done is going to be 0. Power is F dot V, that's also going to be 0. Kinetic energy is constant because the speed is constant. Okay, very important discussion. Please note it down. Very important. Please note it down, very important. So force is perpendicular to velocity and the magnetic field. Okay, force is perpendicular to velocity and magnetic field, V cross B. If this is V and magnetic field is, let's say, upward, so V cross B inside is going to be the force. Okay. Yeah, so some simple questions coming in front of you. Go through this question, read this question. If a positive charge is moving as shown in the figure, then it will get deflected due to the magnetic field towards. If this is a positive charge moving with velocity V, quickly, 10 seconds. Yes, I am giving the break, don't worry. Don't worry. So this is V. They are asking positive charge moving as shown, deflected due to the magnetic field. Where is the magnetic field? Magnetic field is in the y direction. Where is the magnetic field? In the y direction. So V cross B. if this is B in the Y direction, so V cross B, this is Z. This is Z, isn't it? This is Z. So the answer is going to be Z. Answer is going to be Z. Hey, how Y? Who is saying B? How B? Oh, 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 oh. E is going to be the answer. Okay, anyways. Next question. Charge is moving in electromagnetic field without deviation. Okay. E is not equal to 0, B is not equal to 0. E is 0, B is not equal to 0. What is the situation? Let's think. Without deviation. Think about it. Let's think about the first situation. No electric field, no magnetic field. It's going to move with constant velocity. First option is correct. No electric field, no magnetic field, no external force. It is moving with same velocity. No electric field, but there is magnetic field. No electric field, but there is magnetic field. So, in the second situation, if this is the charge moving with some velocity v, let's say the magnetic field is along the direction of v. So, the magnetic force QV cross B is going to be 0. And there is no electric field. Yeah, this is also possible. Next case. Oh, sorry. This is the C case. Okay. This is the C case. C case is correct. I just saw that B is not equal to 0, really sorry. This is magnetic field. In the situation, but it's along the direction. Okay. E is 0. In the next situation, B is 0, but there is E. B is 0, but there is E. B is 0, but there is E. So this is not possible. They are asking in which charge moving electric without deviation, then which of the following without deviation may be possible. This is also possible. If B is there, but it's along the direction of the velocity. Okay. Yeah. So this is possible. This is also possible. A is also possible. So A and C are possible. Let's check B. Just a second. Let's check B option. Magnetic field is non-zero. Electric field is 0. Magnetic field is 0. Electric field is non-zero. Magnetic field is 0, but there is some electric field. So let's say this is the electric field. This is the electric field. Okay. And this is the charged particle. So this is going to be the force. It's going to be in straight direction. It is going to be in the straight direction. Okay. So it's not going to deviate. So this is true. That means all are true. So the answer is D. Okay. The answer is D. D is the answer. Okay. So now we are having a break. We are having the dinner break. Okay. We'll be meeting after 20 minutes and we will be covering EMI, AC, EM waves, okay, and ray optics in this break. Okay, to be done. Then after that we'll have one more break and we'll cover wave optics, modern physics, and semiconductor. Okay, so see you all after the break quickly. Yes, to all of you. Done with the panchayat? What all you are saying in the chat? Let's see. These students are about to write the examination, NEET examination in 2 days. Okay. So let's see what discussion people are having in the chat. Very nice, very nice, very nice. Done with the all of your discussions. Shall we begin with the session? Let's come back to the point. Let's get started. Let's resume the discussion from where we have left. Okay, so here we are. We were discussing the motion of charged particle in presence of magnetic field, isn't it? We were discussing the motion of charged particle in presence of magnetic field. So if we talk about the motion of a charged particle when the magnetic field is perpendicular to the system. Listen, all of you. If we talk about the direction of magnetic field when the charged particle is moving perpendicular to the system, this is the magnetic field. This over here is the magnetic field. And if the charged particle is entering, where the charged particle is going to get deviated? Tell me quickly, all of you. Can you hear me? Am I audible? All of you, am I visible? Nadia, Chitrali, Niharika, and everyone else in the chat, can you hear me? Hello, 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 hello. Am I audible? Am I perfectly visible? All of you, please respond quickly, or else you're going to get blocked. Anbu, Meet. Okay. If I am audible, tell me that what's going to be the direction. Yeah, now I can see your chat. If I'm audible and visible properly, please tell me quickly that what's going to be the direction of force acting on this charged particle if it enters the magnetic field. Let's say this is the direction of magnetic field, which is inward. This is the charge. When the charged particle enters the magnetic field, so V cross B, F equals to Q, V cross B, there is going to be a force acting in a direction something like this. This is the direction of force, yes or no? This is going to be the direction of force. Santosh, Manoj, Aspirant, Ajit, Ria, check about the direction, See, now what we are saying, V cross B, the direction is upward. How do you find out the direction? Open your fingers in the direction of V, close them around the direction of B. Okay? So what? If we talk about the centripetal force that is provided by the magnetic force, that means mv square by r. mv square by r equals to q v cross b, isn't it? Definitely yes. This v gets cancelled out. From here you can find out the expression for r. That's mv by qb. Yes or no? mv by qb. Yes or no? Definitely yes. What is mv? mv is p. What is mv? mv is momentum p. What is the relation between momentum and the kinetic energy? P is equal to root over 2 ke m. P is equals to root over 2 ke m. And what is ke? What can you write about ke? Tell me quickly. What can you say about ke? That's qe. How? If you talk about a particle, if you talk about a charged particle, let's say this is the charge q, and this charged particle is accelerated through a potential difference v. This charged particle is accelerated through a potential difference delta v. So what is going to be the work done? That's q delta v. And this work done is going to get converted into kinetic energy, yes or no? So can we say that if r is nothing but p divided by qb, P is root over 2 KEM. P is root over 2 KE. KE is Q delta V M. Okay. So this is the expression in front of you. Okay. Remember this discussion? I hope that this point is absolutely clear. Okay, let's take the discussion ahead. So what we have written, this is the expression. What is going to be the time period? What is going to be the time period? That's simply 2 pi r divided by v. 2 pi r divided by v. Okay. So 2 pi r is mv by qb divided by qb. Okay, that means it's independent of r. Does not depend upon the speed and the radius. Okay, and the radius. Okay. Let's take the discussion ahead. Let's take the discussion ahead. There's a question coming in front of you. Charged particle moves through a magnetic field. All of you, quickly read the question. Charged particle moves through a magnetic field in a direction perpendicular to it. In a direction perpendicular to it. Then what's going to happen? What's going to happen? A, B, C, D. 20 seconds. Quickly. Every question corresponds to +4 - 1. 20 seconds for this question. Give the answer in 20 seconds. Don't just sit and waste your time. If you are attending the session, be involved in the session and try to give the answer in minimum amount of time. Okay. So quickly, what's the answer? What's the answer? Charge particle moving through magnetic field which is perpendicular. Let's say this is the magnetic field. So there is going to be a force acting on the particle due to which it is going to tilt. It's going to curve, take a turn, isn't it? We have seen the circular motion. We know that the speed remains same, kinetic energy remains same. So work done is 0, power is 0. All these points you should know regarding the motion. Okay, so A is the answer. Next question. Ionized hydrogen atoms and alpha particles with the same momentum enters perpendicular constant magnetic field B. The ratio of their radii of hydrogen is to the alpha particle. Quickly, again 20 seconds for this question. Again 20 seconds for this question. Another simple question in front of you. Quickly. 20 seconds, quick. What is given same? Momentum has been given same. So it's going to depend only upon the charge. R, time up, equals to mv divided by qb. Now mv is p, okay, divided by qb. So you can say that, what you can say, you can simply say that RH divided by R alpha is going to be charge of hydrogen divided by the charge of the alpha particle. Is this point absolutely clear? So what's going to be the ratio of the charges? What's going to be simply the ratio of the charges? We know that you are talking about, oh sorry, this is inverse ratio. So this is going to be Q alpha upon Q. Okay. Q alpha upon QH. So what is going to be the charge? Twice. That means it's going to be 2:1. Simple, 2:1. Okay. Let's take the discussion ahead. Another question coming in front of you is this. Read the question. Proton and alpha particle enters a uniform magnetic field perpendicular to with the same speed. Proton takes 20 microseconds to make 5 revolutions. Then the periodic time for alpha particle, that means in short, you need to compare the time periods. You need to compare the time periods. Okay. Read the question. I am giving you 45 seconds for this question. Be quick. The time starts now. Be quick, all of you. Be quick. Simply, what you need to do, listen. Simply what you need to do, that's 2 pi r, okay, divided by the v. And you know that what is r? R is equals to mv by qb. Okay. So what has been given to you? They are entering with the same speed. That means v is same. Proton takes 20 microseconds to make 5 revolutions. So for 1 revolution, it's going to take 20 by 5 microseconds. Okay, this is the time for 1 revolution. That means time period 1 has been given. Time period of 1 has been given. Time period for proton has been given. T for 1, time period for proton has been given. You need to compare the time period for 2. So simply you can find out the time periods from here. T1 by T2 is going to depend upon these factors. Okay, so simply you can find this. This is a homework for you. Do this question. Okay, we are taking the discussion. All of you do this. We are taking the discussion ahead. And here we go. Here we go. Here we go. Here we go. The next concept coming in front of you. the charge projected at some angle theta from the magnetic field. This is very important. This is very important discussion. Now try to understand. If you have a magnetic field along this direction, okay, and you are projecting the particle at some angle theta, isn't it? This is B. I am reducing the whole discussion, okay? I am reducing the whole discussion into two directions. One is X, another is Y. So if you talk about the X component of the velocity, that is going to be V cos of theta, okay? This is going to be V cos of theta. If you talk about the Y direction of velocity, that is going to be V sine of theta. Now the point is that V cos theta is along the direction of B. V cos theta is along the direction of magnetic field, yes or no? And V sine theta is perpendicular to the direction of magnetic field, yes or no? Quickly. So the particle, if the particle is having the direction along the magnetic field, no force is going to act on the particle due to V cos theta. Oh, anyone wants to get blocked? Please tell me quickly. I will block you. Royal Army girl, what are you doing? You want to get blocked? You want Mar? Tell me. You don't want to study? Last chance, okay? I'll block you. Listen now carefully. If the particle is moving with V cos theta, there is no force acting along the X direction. That means you can say that the force along the X direction is zero. The velocity along the X direction remains constant, okay? And there is going to be a force along the Y direction due to V sine theta. And how much is going to be that force? That is simply going to be Q V cross B. Now which is V? What V? V is the, what is V? V is the V sine theta. Okay? Vy. Okay? That means this is Q V cross B. Vy is V sine theta. So due to V sine theta, what is the direction of force? V cross B. This thumb is going to give you the direction. That means listen all of you. Inward is the force, and due to V cos theta, it is going to move with constant velocity. So this is going to be the path. The path is going to be helix. Okay? Everywhere in the discussion, simply substitute V as V cos theta. That means R, what is going to be R? mv sine theta by qb. Instead of V, this is V sine theta. That's it. Time period is going to be same. Now I'm going to define another term. That's what we call as pitch. What do we call as pitch? Listen, what is pitch? Pitch is the linear distance that is traveled in one complete time period. What do we mean by this? See, this is an important term. That's why I'm telling you pitch. Try to understand. Linear distance traveled, linear distance covered in one time period t. That means in one time period, how much linear distance has been covered by the particle. Okay. So this is going to be the pitch. Let's denote it by x or p, whatever you want to say, write it. X or p denoted by anything, I don't mind. So particle is moving with constant velocity along the x direction, isn't it? That means v cos of theta into time period. What is the time period? Time period is same 2 pi m by qb. This is nothing but 2 pi m divided by qb. So this is going to be the pitch. Okay, this is going to be the expression for the pitch. Is this point very clear? Pitch. If you want to physically know what is pitch, see, if this is the cap of the bottle, if I rotate this cap, okay, 360 degree, how much linear distance this cap moves, isn't it? It moves up, it goes down. So in 360 degree, how much it gets up, that's what we call as the pitch. Okay, so this is the expression for pitch. Remember. important. I hope that this point is absolutely clear. Let's take the discussion ahead. Okay. Let's take the discussion ahead. Read the question. All of you, read the question. Simple question. What is it saying? A charge having E by M equal to 10 to the power 8. Specific charges to mass ratio 10 to the power 8 coulomb per kg. Moving with a speed V has been given to you as 3 into 10 to the power 5 meter per second. Enters into a uniform magnetic field. V has been given to you. How much? 0.3 Tesla. Okay. At an angle. How much angle? 30 degree. That's fine. So what? With the direction of field, the radius of the curvature is going to be how much? The radius of the curvature. Quickly. Only 30 seconds you are going to get. Only 30 seconds you are going to get for this question. Quick. Quick. Not even 30 seconds. Let's start solving. This is a very simple question. Okay. So simply what's being said? R equals to mv sine theta divided by qb. Okay. So q is to m has been given to you. They are talking about the E by m has been given 10 to the power 8. So m by e is 10 to the power minus 8. Okay, into v. What is v? That's 3 into 10 to the power 5. Okay, into sine theta, sine 30. Sine 30 is 1 by 2. Okay, divided by, time up, divided by b. How much is b? 0.3. Okay, so arrange this, calculate this, you get the answer. Simple. Okay, it was a very simple question. Coming to the next question. There's a solution in front of you. Force on a wire. Force on a wire. Force on a wire. Listen. Just a second. So here we go. Let's talk one more candidate deserving. That's it. Okay. Yeah. So here we go. Listen. If you talk about force on a current carrying wire placed in a magnetic field, so definitely there is going to be a force. First of all, is there going to be a force on a wire placed in a magnetic field? Think that if this is a wire which is carrying some current and you place this wire in a magnetic field, yes, there is going to be a force. Why? Because there is going to be a magnetic field due to this wire itself. There is going to be a magnetic field due to this wire itself. And what is going to be that force? The force is going to be IL cross B. F equals to IL cross B. F equals to IL cross B. Remember this thing, okay? IL cross B. This is going to be the expression for the force, okay? Now, force 0 on closed loop, force between the parallel wire per unit length. Now see what we are saying. If we talk about two wires, listen. Let's have two discussions. Okay. This is basically a current carrying loop. Listen. Very important discussion. Very important comparison I am giving you. This is basically a current carrying loop. This is a current carrying loop placed in a perpendicular magnetic field. Okay. Something like this. And on the other hand, we have one more system. What system? These are two wires. These are the two wires placed parallel to each other. Okay. Parallel wires. Parallel current carrying wires. Okay. Let's say this is I1. Let's say this is I2. First of all, let's talk about the direction. Directionality. Okay. If you look at the first situation over there, current. There is current. Okay, there is current in the situation. Yes. Is there going to be a force on the loop? Let's think of it. If this is a small element, this is going to be the direction of current element. Isn't it? Current element, yes. Take a small element. Okay. So L cross B, we are talking about the small element I, L cross B. So take DL cross B, L cross B, L cross B, L cross B, L cross B, everywhere, if you talk about the force, L cross B, L cross B, L cross B, L cross B. Very, very, very important discussion. Okay. So the net force on this whole wire is going to be 0. F net on this current carrying wire placed in a magnetic field is going to be 0, but there is going to be a stress in the situation. Very important discussion, because this whole wire wants to get expanded. Yes, it wants to get expand. Very beautiful concept this is. Okay. So F you have written I L cross B. That's cool. That's fine. Yeah. Now, if you have two wires, who want to sit on the wires? Let's say Sumit and Ajit. Okay. Sumit is standing on the wire number 1. Something like this. Hold the wire. Okay. This is Mr. Sumit and this is Mr. Ajit. Okay. Ajit standing over here. Sumit standing over there. These are the two students, Mr. Ajit and Mr. Sumit. Okay. Something like this. Yeah. So the point is that is there going to be a force on Ajit due to Sumit and on Sumit due to Ajit? Let's check. First of all, if I talk about the force on second due to 1, force on 2 due to 1, force on 2 due to 1. Okay. Force on the second wire due to the first wire. Let's check. Is there magnetic field due to wire number 1? Yes, there is magnetic field due to the wire number 1. Yes, there is magnetic field due to the wire number 1. Yes, there is magnetic field due to the wire number 1. What is the direction of that magnetic field? That is inward. That magnetic field is inward. That magnetic field is inward. The magnetic field over here is B inward. Okay. Magnetic field is inward. Okay. Yes. So what is going to be the force? F equals to I. I due to whom? I due to whom? I due to itself. Current in the 2. L cross B. B of 1. B of 1. I L B1. Similarly, and what is going to be the direction? What is going to be the direction? What is going to be the direction? Listen. Okay, listen. Nadia is standing and observing the situation. This is Miss Nadia standing over here. Nadia standing over here, observing the situation. So, Nadia, tell me that what is the direction of force on 2 due to 1? That's I L cross B. That's I L cross B. L cross B. B is inside. So this is the direction of force. This is the direction of force. That's cool. Okay. This is the direction of force. Similarly, if you find out the force over here, that's going to be in the opposite direction. That means the two wires which are carrying current in the same direction, parallel current carrying wire, they are going to have the force. How much? This much. This much is going to be the force. This much is going to be the force. Mu naught. This is basically force acting per unit length. This is mu naught I1, I2 divided by 2 pi into the separation between the two. 2 pi into the separation between the two. Okay. Remember this discussion. Okay. So here we go. Here we go. Here we go. Here we go. Okay. Please note it down. Note it down. This is very important discussion. Have you written this? All of you? Done with this? Okay. Let's take the discussion ahead. Read the question. Read the question. A circular coil ABCD carrying a current I is placed in a uniform magnetic field. This is carrying a current I. It is placed in a uniform magnetic field. The magnetic force on this segment AB is F. Then the force on the remaining segment. Okay. Let's say this is the direction of magnetic field. This is the direction of magnetic field. I have given you the direction of magnetic field. Okay. I have given you the direction of magnetic field. Now say, tell me the answer. 20 seconds. All of you, quick. Quick. What is going to be the answer? We know that the whole situation, the force is going to be equal opposite in every direction due to every element. We know this. Yes, we know. Do we know this? Definitely, yes, we know. So can we say that if this is segment number 1, and this hole is segment number 2. So the total force F1 plus F2 equals to 0, isn't it? You want to find out the force due to the second segment, the force due to the first segment. If that is F plus F2 is going to be 0, that means answer is going to be simply A. Answer is going to be simply A. Yes or no? Very nice. Very good. Very good. Very good. Another question in front of you. Read the question. This is the next question. A uniform conducting wire ABC, a uniform conducting wire ABC has a mass of 10 gram. Okay. ABC has a mass of 10 gram. Mass has been given to you. So what are they saying? What are they saying? Kept in a magnetic field, the acceleration of the wire will be acceleration of the wire. First of all, this is the direction of current. Okay. So IL cross B. What is L? What is L? This is initial point. This is final point. Just a second. What is L? First of all, option number A, L is 4. Option number B, L is 5. Option number C, L is 3. Option number D is that we are mad and we don't know. So these are the 4 options for length. First of all, the effective length. Tell me what is the effective length? What is the effective length in the situation? What is the effective length in the situation? What is the effective length? First of all, tell me what's the effective length in the situation. Quick. You're starting from A and reaching C and reaching C. So, yeah, effective length is this much. Dear students, effective length is this much. This is 3. Remember this concept. We always talk about the initial and the final points. The effective length is always between the initial and the final points. Okay, remember this. So effective length is 3. This is the first point that you should know. Then only you can solve the question. And now force is equals to I, L effective cross B. Now L and B are 90 degree to each other. So you can find out the force. I is how much? I is how much? I is 2. L is 3. B is 2. So this is 4 into 3, 12. So this is the force. So what is going to be the acceleration? Force upon mass. Force upon mass. That means 1.2. That means 12 divided by 10 grams. That means 10 to the power minus 3. That means C is going to be the answer. C is going to be the answer. C is going to be the answer. Okay. Let's take the discussion ahead. Let's take the discussion ahead, and here we go. Okay, here we go. Read the next question quickly. Read the next question quickly. What the question says: an arrangement of 3 parallel straight wires placed perpendicular to the plane of paper carrying same current I along the same direction. Magnitude of force acting per unit length is going to be how much? Oh, what is the system? What is the system? What is the system? What is the system? Magnitude of force acting per unit on the wire B. See, this is A. Now who wants to sit on wire A? This is wire A and this is dot. Dot means outside. This is wire C and this is dot. Dot means outside. Okay. So the direction of force. Listen. Shh. Karan, you want to sleep? Then go and sleep. The direction of force on C due to A. L is out. L cross B is left. Is left. Direction of force on the wire B due to A is left. L cross B. L, this is L, outside. Cross B. Okay, this is the force per unit length on the wire B due to the wire C. So what is going to be the resultant? That's going to be root over, let's call it as F1 square plus F2 square, and the magnitude is going to be same. That means it's simply going to be root 2 times of the expression for F. Root 2 times of the expression for F. And what used to be the expression for F? That's simply, this is the expression. Okay, there is a 2 in the division. So this is going to be the answer. This is going to be the answer. Okay. All of you. The next question. Quickly. Conducting loop of current I placed in a uniform magnetic field. The loop will have a tendency. We have discussed this. Sir, last गलत किया है. NTA ने आंसर 2 दिया था. Which one, Sumit? Which one? Just a second. This one. This one or this one? This is absolutely correct. My dear, this is absolutely correct because the mass has been given as grams and the answer is in meter per second square. Okay, the answer has been in meter. Sumit Sharma, I'm talking to you. And if you're talking about this one, this is still root 2 times of F. What is F? F is mu naught I1 I2 divided by 2 pi d. Right now we have seen this expression. Over here. This force acting per unit length, mu naught I1 I2 upon 2 pi d. This. Isn't it? Yes. So the resultant is going to be root 2 times. Why? Because there are two forces at 90 degree. Okay. Yes. Is this point cool? No, Sumit. उससे पहले वाला, you're talking about this one na. See, you're talking about this one. Okay, please check it once again. This is going to be the correct answer. This is going to be the answer if the units was kg. Okay. If the unit was kg. Yeah. Let's take oh, that's gram. Okay. Let's take the discussion ahead. Here we go. Give the answer for this question. Quickly. Give the answer for this question, all of you. Conducting loop carrying current I. What is it going to do? Definitely it's going to expand. We know that there is a force acting in the outward direction on every element. L cross B, 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 L cross B. Every particular element is going to expand. Okay. So let's take the discussion ahead. Next point coming in front of you, next concept coming in front of you is the magnetic moment. Magnetic moment is simply the product of I and A. It's a vector quantity and its unit is going to be ampere meter square. Okay. So M equals to I cross A. Okay. Vector quantity. Now. Where is it used? Where this concept is used? Okay. If we talk about the torque, so if you remember the discussion that we had in the electric field, if you remember the relation that we had in the electrostatics, that was PE sine theta. Okay. For electro, I'm writing it over here. I'm comparing it with the electrostatics. Tau equals to PE sine of theta. Instead of P, dipole moment, you have magnetic moment. Okay. Magnetic dipole moment. Magnetic moment. Okay. Instead of E, you have B. Okay, that's fine. Same situation. Similarly, you can discuss about the potential energy. At 0 degree, there is a stable equilibrium. See, we know that what is basically the concept of potential energy. U equals to, what do you write over there? There you write minus PE cos of theta, isn't it? There what we used to write? Minus of PE cos theta. So what is going to be U over here? U over here is minus of M B cos of theta. Okay, minus of MB cos of theta. So the work done by the external force, if you are doing some work, you are the external force, you are doing some work, then what's going to happen? That work is going to get stored in the form of potential energy. That work is going to get stored in the form of potential energy. Okay. Okay. So this is external. And if you talk about the work done by the magnetic force, mg, this is magnetic. Okay, magnetic force, that's minus times of delta U. Remember this. Okay, that's minus times of delta U. Okay, what is delta U? Initial minus final. Written, all of you. Let's come to the next question. Read the question. What the question says: a current carrying loop in a magnetic field. A current carrying loop in a magnetic field is going to do what? What it can do? 10 seconds, quickly. 10 seconds. Get started. Quickly. Can be in equilibrium if two orientations, both the equilibrium states are unstable. Let's see. Can be in equilibrium in two orientations. One is stable while the other is unstable. Experiences a torque, whether the field is uniform or non-uniform. Can be in equilibrium in one orientation. So what is going to be the answer? They are saying that it can be in equilibrium in two orientations and both are going to be unstable. This is wrong. Okay, this is absolutely wrong. It can be in equilibrium in two orientations in which one of them is going to be stable, another one is going to be unstable. Yes, that's true. Okay, same situation we have discussed in the concept of electric dipole when we placed it in external magnetic electric field. Experiences a torque when the field is uniform or non-uniform in all orientations. No, not in all orientations. Can be in equilibrium in one orientation. Wrong. So the only answer is B. The only answer is going to be B. Okay. Yeah. So let's take the discussion further. Just a second. See, the next concept that's coming in front of you, is the moving coil galvanometer. See, basically, what a moving coil galvanometer is, just try to understand. You have two horseshoe magnets, okay, and you have a system on which there is coiling being done, okay, and this coiling system, coils, okay, are connected. These are loops, okay, closely wound loops, okay, wound over a particular system, and this is a pointer. So what happens when there is magnetic field over here? So definitely this loop is going to experience a force. There is going to be a torque in the situation, and due to the torque there is going to be deviation in the coil. There is going to be deviation in the pointer. Okay, this system is what you call as a moving coil galvanometer. Now what is the concept over here? Greater the torque, greater is going to be the deviation. Greater the torque, greater is going to be the deviation. Yes or no? So what is the torque? Tau equals to Bani, B-A-N-I, or simply N-B-A-I or N-I-A-B. Okay, just remember it this way. If the proportionality is removed, there comes a constant times the theta. Theta is the deviation. Now we define two terms: current sensitivity, deflection per unit current, and voltage sensitivity, deflection per unit voltage. Okay, so this is deflection per unit current. This is NBA by C. Deflection per unit voltage, NBA by CR, because I equals V by R. Just remember this expression. Okay, this is very important. Let's come to the question based upon the concept. Read the question, all of you. What this question says: current sensitivity has been given to you, voltage sensitivity has been given to you, resistance you need to find out. So you know the expression for current sensitivity and voltage sensitivity clearly. If you just remember it. If you divide both of them, what do you get? You get I, you get R. Divide them, you are going to get R. Okay, so simply this is going to be the ratio of current sensitivity is to the voltage sensitivity. Okay, simple. So that means 5 divided by 20. That means 5 divided by that's current sensitivity. This is milliampere. Okay, this is milliampere. That means 10 to the power minus 3 ampere divided by this is okay. This is fine. This is going to be how much? This is 4, and this is 1000 divided by 4. That means 250. This is going to be the answer. Okay, is this point clear? Let's take the discussion ahead. Last question of the unit, last question of the topic. In a moving coil galvanometer, a current I produces a deflection theta. Then in a moving coil galvanometer, current I produces a deflection theta. Then current is proportional to what? Tan theta, theta, root theta. Quickly, simple, we know that greater the current, greater is going to be the torque, greater is going to be the deflection theta, because we know that tau equals to Bani, B-A-N-I or N-I-A-B, okay, one and the same thing. And this is proportional to theta. So I is proportional to theta. Very simple. Let's take the discussion ahead quickly. We are discussing the magnetism and matter. Now this is a very theoretical topic, so I will be directly giving you the important crux of the unit, or else we will not be able to reach up till the modern physics. Okay, so let's take the discussion ahead, and here we go. We are talking about the magnetism and matter. So first of all, What is the basic difference? What is the basic difference between a magnet and a charge? That the magnetic monopoles never exist. Remember one thing, magnetic monopoles never exist. What is the meaning of magnetic monopole? Individual north and individual south. You are never going to get individual north. No matter, let's say if you have a magnet, something like this. Okay, so this is north, this is south. Divide the magnet into two halves. Still it is having north and south. Again divide it into two halves. Keep on dividing it. Okay, in the end also you are going to get, no matter how much you divide, even at the molecular level, the magnetic domain consists of a north and a south. Okay, so magnetic pole strength is simply treated as that of a charge. There we used to talk about charge, here we are going to talk about magnetic pole strength, and it is proportional to the area of cross section. Remember this basic discussion. Next point, magnetic monopoles do not exist. Very, very, very important point. Okay. Next point, magnetic moment. Okay, magnetic dipole moment is proportional to the volume. Okay, it's a vector quantity. Unit is I into A, that means ampere into meter square. Yes or no? Definitely yes. Direction is from south to north. Similarly, we had from negative to positive in case of the electrical dipole, isn't it? Yes. If you talk about the value of magnetic field due to the system on the axis, okay, if you're talking about the magnetic field on the axis, and this is okay, at some r, position r, so this is going to be mu naught upon 4 pi 2m by r cube, just exactly same. Okay, just exactly same as that we had over there. What it used to be for axis, 2 kp by r cube. Instead of k we have mu naught upon 4 pi. Okay, instead of p we have m. Okay, rest everything is same. Remember this, the direction is from negative to positive over there, and here we have from north to south. Okay, so if we talk about cutting of a magnet, so if you cut along the axis, if you cut it along the length, okay, if you cut it perpendicular, in both the situations the strength is going to get reduced by m by 2. Okay, m by 2. Okay. So read the question what it says. Which of the following arrangement of the bar magnets in different configuration, each magnet has dipole moment m, which configuration has the highest net dipole moment? Which of the following has highest net dipole moment? Think about it. Direction is from south to north. Here it is going to be 0. South to north. Okay, south to north. 10 seconds for this question now. 10 seconds for this question. Quickly. ABCD. What it's going to be? Quickly. Time up. Let's see. Riya is saying C because angle is 0. Okay. Nadia is saying C. Reason? Chitrali, in the option B, it is 0. Clearly that's 0. Samija is saying C. Very good. Yes, that's cool. That's fine. The answer over here is going to be C. Yes, that's the correct answer. You're saying correct. So they are asking about the net dipole moment for each of the situation. It's going to be C in this situation. Okay. So let's take the discussion ahead. Now this is a very beautiful question that was asked in NEET 2021. NEET 2013, sorry, not 21. Okay. Magnet of length L, this is the length L, okay, has been bent in the form. New magnetic moment in the situation is going to be how much as compared to the previous one, okay. So just remember the expression for m dash. See, let's say that the m is initial dipole moment, initial magnetic moment. So this is going to be m times of 2r sine of theta by 2. Remember this expression, m times of 2r sine of theta by 2, okay. Theta has been given to you, okay. Yes, what you need to find out, you need to find out the expression that's relating r with L. So what you can do, simply this is theta equals to arc upon radius, okay. So theta is how much? Theta is pi by 3 equals to L divided by r. So use this expression quickly, fast. What is initial magnetic moment? Let's say initial magnetic moment, that's going to be m times of L, okay, that's fine. In this situation, what it's going to be? M times of 2r. What is r? R can be 3L by pi, 3L by pi, okay, 3L by pi. And what is sine 30? Sine 30 is 1 by 2. So what is the expression going to be? This 2 gets cancelled out. So this is nothing but m dash is m into L, that's m. So m into 3 by pi, m into 3 by pi. Quickly, that means answer number D. Have a look at this, okay. So I hope that this point is absolutely clear. Let's take the discussion ahead, and here we go. Have a look at this question. What are they asking? Two identical bar magnets are fixed with their centers at the distance d. This is center number 1, center number 2. Separation has been given to you as d, okay. A stationary charge q is placed at the point P. There is a charge q, okay, there is a charge q over here. Charge q you have placed, okay. The force on the charge, tell me one thing, what's going to be the force on that charge? How much is going to be the force on that charge? If you talk about the dipole moment, simply this is the direction. You are talking at the center. If you talk at the center, equal opposite, that gets cancelled out. So the answer is going to be 0. Okay. If we talk about the properties of magnetic field lines, first of all, the direction is always from north to south. Let's say this is north, this is south. So what's going to be the directionality? Outside from north, inside towards the south, okay. So this is going to be the representation. If you talk about the direction of magnetic field line inside the magnet, that's from south to north. They form closed loops, yes, we know. They never intersect, yes, we know that they never intersect, or else there would be two directions at that particular location for the force, which is not possible. It comes out and goes in at any angle. If you talk about the entrance and exit of the magnetic field line, at every given angle this is happening. While in the electric field was always perpendicular. To the conductor, okay. Yes, remember this point. So let's take the discussion further. Field line density represent the magnetic field strength. Field line density, greater the field line density is, greater the magnetic field lines, greater is going to be, just a second, let's block this fellow. Yes. Okay, that's cool. Yeah, so let's take the discussion ahead. Here we go. If you talk about the torque, we know that tau equal to P sin theta, mb sin theta, that means m cross b. This is what we have already seen. Work done by the external goes into the potential energy. Work done by the magnetic field is minus times of potential energy. Okay. If you talk about this is for the torque, this is for the potential energy, mb cos theta minus m cross m dot b, and the time period is 2 point root of I by mb. So here we go. Come to the question. Read the question. A bar magnet is hung from a thin cotton thread in a uniform horizontal magnetic field and is in equilibrium state. The energy required to rotate it by 60 degree is W. Now the torque required to keep the magnet. Now the torque required to keep the magnet in the new position. They are asking about the torque. Okay. Required to keep the magnet. The energy required to rotate by 60 degree is W. Okay. Energy required to rotate by 60 degree is W. So first of all, let's find out the expression for energy. This is W. We know that the potential energy delta U equal to W equal to U final minus U initial, isn't it? What is going to be what is going to be U final? Simply minus of M B cos 60 minus of M B cos 0, isn't it? Minus of M B cos 0. So how much it's going to be? This is going to be W equal to minus M B cos 60 is 1 by 2 minus of minus M B cos 0. That's simply plus M B. Okay. So this is how much? This is work done equals to MB by 2. Okay. Work done equals to MB by 2. This is the first expression in front of you for the work done. That's cool. Okay. This is cool. Now what? They are talking about the torque. So are we aware about the expression for the torque? Are we aware about the expression for the torque? What is tau? Tau is nothing but M B sine of theta. What is theta? 60. So this is going to be how much? This is going to be MB sine 60 is root 3 divided by 2. So what is MB by 2? That is W. So answer is root 3 times of W. Answer is root 3 times of W. Okay. Another good question it was. Another nice question it was. Okay. So I'm writing important over this question because it was a really nice concept. Okay. So here we go. Let's take the discussion further. Okay. Just a second. Oh. Yeah. Oh, yeah. So here we are. The discussion on electromagnetic induction. Basically, another very important topic, because if we do not understand electromagnetic induction, we won't be able to understand the AC. So what basically the concept of electromagnetic induction is, let's try to understand. The first concept that's coming in front of us is the concept of magnetic flux. It's the concept of magnetic flux. Now, similarly, the way we have understood the electric flux, we have the magnetic flux, the magnetic field lines crossing a given region. So this flux is going to depend upon the magnetic field, upon the area and the orientation. Okay, as well as the orientation. That means phi is going to be B dot A. Okay, it's a scalar quantity. It is a scalar quantity. Unit is going to be Weber. Either call it a Weber or you call it as Tesla meter square. Okay. 1 Weber equal to 10 to the power 8 Maxwell or Gauss centimeter square. These are all the same units for the flux. Okay. Yeah. So there's a very simple question coming in front of you. Read the question. A circular disc of radius has been given, is placed in a uniform magnetic field of induction. B has been given in such a way that the axis makes 60 degree with B. The magnetic flux linked with the axis. You need to find out the flux linked with the axis. So what is going to be flux? Simply phi equals to B A cos theta. 20 seconds, calculate it quickly. 20 seconds, calculate it quickly. Fast, all of you. let's say this is the magnetic field, this is the area, this is 60 degrees. Substitute the data, get the answer. Okay, substitute the data and get the answer. Now we are talking about the Lenz's law. Just a second, we are talking about the Lenz's law. Now see what basically the Lenz's law says. Try to understand. This is Lenz's law, L-E-N-Z. Just a second. Okay, just a second. So Lenz's law, basically it is something like whatever you are going to do, the system is going to do the opposite. Whatever you do, the system is going to do the opposite. Now what it means, see, there are some kids who do exactly the opposite what the parents say. If parents are saying that sleep, they say no, we don't want to sleep. If parents are saying that wake up, no, we don't want to wake up. Parents are saying that go there, they say no, we don't want to go there. If parents are saying that don't go there, no, we want to go there. Some kids, they are always opposing, whatever the parents are saying. Similarly, in this situation, you can relate the logic that I have given. Just see. What the point is? Point is that Lenz's law, it is based upon the energy conservation. What it gives you the direction of the current and EMF. Yes, the direction of induced current. The direction of induced current is given by this law. And what it says, it is such that it opposes any change in the flux. It opposes any change in the flux. Okay. That means what happens? What happens? If there is a flux generated in the situation, think it this way. If you have a loop, okay, think, listen all of you, important. If let's say this is a magnet, this is north, this is south. Okay, so what are you doing? You are taking the magnet near this coil. If you are taking the magnet closer to this coil, something like this, if you are taking the magnet closer to this coil, something like this, what are you doing? You are increasing the magnetic field lines. That means the flux is increasing, isn't it? The flux is increasing. So what the induced current or the induced EMF wants to do, it wants to reduce the flux. Whatever you do, the system is going to do the opposite. Whatever you do, the system is going to do the opposite. Remember this point. So if you are bringing this magnet closer to this system, there is going to be an induced EMF in the coil. Okay, and that's going to oppose. What? It's going to oppose this particular magnet which is coming close. So it is going to generate current in such direction that there is a north pole. Okay, and what is basically a north pole? This is the north pole. Okay, that means the current has to be along anti-clockwise direction. So if someone observes from here, let's say Vishal is standing over here. This is Vishal. This is Mr. Vishal standing over here. Okay, and Vishal is observing, so he is going to say that in what direction the current is, it's in anti-clockwise direction. Okay, this is the utility of Lenz's law. If you take the system away, if you take the magnet away, this system wants to stop the magnet from going away. So it is going to pull the magnet by generating a south over here. That means clockwise current would be if you take the magnet in the opposite direction. Oh, are you all awake? Or you're sleeping? Quickly, Arya, Shwet, Sumit, Ajit, Vishal. Quick. Yeah. So this is the discussion regarding the Lenz's law. Now see, if we have some cases, if let's say magnetic field is outward. Okay, this is the magnetic field and this is decreasing. the outward magnetic field is decreasing through a loop. Try to understand. This is a loop. Okay, this is the loop. This is the loop. This is the loop. Try to understand. This is the loop. And the magnetic field is outward and the magnetic field is decreasing. Magnetic field is outward and it's decreasing. So what the system wants to do, it wants to oppose the decreasing magnetic field. So system will do what? It will generate the EMF in such a direction that this outward magnetic field is supported. That means the current should be in such a direction that outward magnetic field you get. So how are you going to get outward magnetic field? This is how you are going to get the outward magnetic field. So this is going to be the direction of current. Is this point very clear? Is this point very clear? Is this first point very clear? Therefore, current is going to be in the anti-clockwise direction. Getting the point? Are you getting the point? Very important discussion this is. Okay. Yes. Okay. So rest all discussion you can imagine like this. You can simply find out like this. Okay. So here we go. Let's take the discussion ahead. Here's a question for you quickly. What the question says: an electron moves on a straight wire XY. Okay. This is the path XY. What is the electron doing? Electron is moving along this line. The ABCD is a coil adjacent to the path of electron. What will be the direction of current, if any, induced in the coil? Okay. So option says no current is there. Direction has been given ABCD, ADCB. The current will reverse its direction as the electron goes past the coil. Think about it. Think about it, all of you. Yeah, the electron is passing like this. If the electron is moving like this, definitely there is going to be current in this direction. You can say that there is current in this direction, but this is not a uniform current. The current, okay, in the situation is varying, something like this. Okay, so there is going to be presence of magnetic field. Something like this. There is going to be a magnetic field cross. That means magnetic field is going to be like this. Okay. As the electron moves, the magnetic field first increases, then it decreases. The magnetic field increases, then it decreases, isn't it? Just a second. Log this. Okay, fine. Yeah. Yes. So what is going to be the answer? Definitely the current will reverse its direction in this situation because flux is first increasing, then it's decreasing. Okay. So the direction of current in the loop is also going to reverse. Okay. So let's take the discussion further. This is a beautiful question. No, not this one. First, I'm giving one question. This one. Okay. A metallic ring is held horizontally and a bar magnet, this is the bar magnet. Okay. This is the bar magnet. What is this bar magnet doing? You have dropped this bar magnet, so it falls something like this. It crosses the ring and goes down. Okay. So during this motion, what's going to happen? This is north and this is south. North and this is south. Quickly. Quick. Saptarishi Samantha is asking why current is varying in that situation. Because in that situation, charge is moving. This is electron. This is coming. And this is the loop. Imagine this is the loop. Okay. Let's say that this is the loop. See, this is the loop. And this is the electron which is coming. Initially, there is no current. If electron is coming, there is presence of current in the situation. There will be magnetic field. electron passes, again the magnetic field is decreasing. Isn't it? Getting the point? All of you? The point? Yeah, so that was the answer to your question, Samantha. Now come to this question. What this question says: if a magnet is dropped, something like this, and this is a ring, then what's going to happen? Regarding the G? Okay, 10 seconds, quick. 10 seconds, only 10 seconds. Think about it. If you think, okay, if it clicks, then it's okay, or else you cannot solve this question. Okay, you just have to think about it. What is going to happen? Just think about the Lenz's law. Just think about the Lenz's law. Time up, time up, time up. Now see what the Lenz's law says. It says that whatever you are doing, the system will do the opposite. Whatever you are doing, the system is going to do the opposite. So if the magnet is coming down, definitely the magnetic field lines are increasing. The magnetic field lines are increasing. So the flux initially is increasing in the first situation. The flux is increasing. So what this system is going to do, system is going to oppose the increasing flux. That means system is going to generate a magnetic field in the opposite direction, and due to that the acceleration of this system, of this bar magnet, is going to decrease. Initially it was G, so it is going to be lesser than G in the first situation. It is going to be lesser than G in the first situation. When the bar magnet crosses the loop, this is north, this is south. Okay, so again in this situation, if the south is moving away, whatever you do, the system will do the opposite. Lenz's law. Okay, whatever you're doing, the system is going to do the opposite, isn't it? So if the magnet is going down, this system wants to oppose the downward motion of the magnet. So it's going to attract the magnet by generating north over here, so it can attract. So definitely the acceleration in the second situation also is less than G. So what you can say that the total acceleration is going to be less than G. It's going to be less than G always. Is the answer. Is this point very clear? Is this point very clear? Okay, that's cool. So let's take the discussion ahead. Faraday's law. What is Faraday's law? We are going to study. It's the consequence of conservation of energy. Okay. So what the Faraday's law says, Mr. Faraday said that the EMF generated in a situation, in a system, is nothing but it's proportional to the rate of change of flux. I'm writing it in words. It's proportional to what? It's proportional to the rate of change of flux. Why is this negative sign? Negative sign is because of the Lenz's law. We now know this. Okay. So you can say that EMF is nothing but the average EMF is nothing but minus of delta phi by delta t. If you talk about the instantaneous EMF, that's nothing but minus of d phi, the differentiation, by dt. Okay, you can say what is I? I is nothing but E divided by R. And what is E? E is equals to minus of d phi by dt. Okay, divided by R. That's fine. Okay, that's cool. What can you write about I? I can be written as dq by dt. Yes, definitely it can be written as dq. Okay, dq divided by dt. So this is minus of 1 by R d phi by dt. Okay, so this dt gets cancelled out. So this is the expression that relates the charge and the flux. Very important expression. Okay, very important expression. I hope that this discussion is absolutely clear. Okay, is this point clear? So do this question now. One question that we have left over here, you can do it now. I think I have left a question. Where I have left a question? Yeah, this question. Quick. 800 turns of a coil of effective area. See, number of turns have been given to you. Area has been given to you, kept perpendicular. That means angle has been given to you. Magnetic field has been given to you when the plane of the coil is rotated by 90 degrees around any axis in this much amount of time. What you need to find out? EMF induced in the coil. Okay. This is the area. This is the magnetic field. This is the magnetic field. Okay. And if this is the magnetic field, this is the area vector n cap. What are you doing? You are placing the loop in such a way that the area vector is at 90 degree to the magnetic field. And the time required, this is initial, this is final. The time required for this situation, for this transition is how much? The time required for this transition is 0.1 second. 0.1 second. Okay, 0.1 second. So what you need to find out? You need to find out the EMF induced. EMF equals to delta phi by T. Simply delta phi by T. Now, flux in the second situation is 0. In the first situation is NBA. Cos 0 is 1. Divided by time and calculate the answer. Okay, divided by time and calculate the answer. I'm leaving this for you. Simply divided by time and calculate the answer. Let's take the discussion ahead. The next question, a direct relation. The next question, a direct relation between charge and the flux. We have seen this. Okay, right now we have derived this. So not wasting time on this. Let's come to the next point. A coil of resistance 400 ohm placed in a magnetic field such that the flux varies something like this. Phi equals to 50 E square plus 4. The current you need to find. So EMF is equals to minus of d phi by dt. Okay, we are talking about the magnitude of EMF. Differentiate it. What do you get? You get 100 T. You get 100 T. This is EMF. So what is I? I equals to E by R. You need to find it T equal to 2 seconds. So this is 200 divided by R. R is 400. So 1 by 2. That means 0.5 ampere is the answer. Simple. Simple. Yes or no? Okay, that's cool. Let's take the discussion ahead. All of you getting the answers or not? Tell me. Now this question you have to do. Okay. Read the question. I'll give you a time of might be 30 seconds. Would be sufficient. I want the answer from you people. Only limited students are giving the answer. Lakshya, Nitish, Sumit, Minesh. What rest of you are doing? All of you quickly. Quick. Yes, Sumit, we will check. Don't worry. First, do the question that I have given. Do this. Chitrali. Everyone, I am talking to everyone. All of you. Be present in the chat. Give the answers. All of you. Ayush. Time starts now. 30 seconds for this question. Quick. 30 seconds for this question. Rectangular, square, circular and elliptical loop all are in xy plane are moving out of a uniform magnetic field, okay, with a constant velocity. Rectangle, circular, elliptical loop moving out with some velocity from a region of uniform magnetic field. This is V, this is V, this is V. The magnetic field is directed along the negative Z. Okay, let's say that the inside direction is negative Z. Okay, X, Y, Z. Okay, that's fine. Induced EMF during the passage of these loops out of the field region will not remain same for everyone. It's not going to remain same. For all of them, it's not going to remain same. Okay. For all three of them, it's not going to remain same because the flux is changing. For all three of them. So for all three of them, it's not going to remain constant. Okay. Yups. Okay. Yeah. So another important discussion that we are going to do is the motional EMF. Or the Hall effect. Now see, if this is a circuit, this is a rod that you are moving along this circuit. What is here? You have magnetic field. Let's say this is the direction of magnetic field, inward magnetic field, something like this. Okay, inward magnetic field, something like this. If you're moving the system, definitely the flux linked with this area, the flux linked with this region is going to change. Yes or no? Yes or no? Definitely the flux is going to change. So if the flux is going to change, there is going to be an EMF. Yes, yes. You are moving it with constant velocity v. So remember the expression for EMF, that's BLV. Okay, that's BLV. So if this is EMF, what is going to be the current in the system? That's E by R. E by R. E is BLV by R. Okay. Remember the expression for the force, that's going to be B square L square V by R. Power P equals to F dot V. So multiply the expression for force by V. So this is the expression for power. Okay. Okay. Is this point clear? Let's take the discussion ahead. Very important discussion. Okay. So here we go. Yeah. Now see. What if you rotate a rod in a magnetic field? Try to understand. Let's say if you are rotating a rod with omega. This is a charged rod that you're rotating with omega. Okay, something like this. You're rotating it with omega in this situation. So how much EMF is going to get developed across the ends of the rod? How much EMF is going to get developed? See, if you rotate this rod, don't you think that every given point is going to have velocity along this direction? There is magnetic field inside. So what is going to be the direction of force on a charged particle? V cross B. If you talk about the direction of force acting on a charged particle, so it's going to be V cross B. It's going to be V cross B. It's going to be V cross B. If you talk about negatively charged particle, Astha is saying, I think ये पहले से record हो रखी है. No, Astha, you're thinking wrong. If this is a negatively charged particle, the force is going to be in the opposite direction. If you are talking about a negatively charged particle, the force is going to be in the opposite direction. That means if you talk about the electron, this is going to be the force. That means this is negative, this is positive. Okay, so this is how the charge is going to separate. Isn't it? All of you in the chat. So how much EMF is going to be there in the situation? That's half B omega L square. Half B omega L square. Okay, getting the point? Yes. Very important discussion. After this, if you talk about a rod which is moving with different velocity at the two ends, V1, V2. So remember, this is going to be the expression. Okay. Okay. So let's try a question. Do this. NEET 2016 phase 2. Okay, NEET 2016 phase 2. Okay. Read the question. Hello Bharat. Hello all of you. वीडियो काफी फास्ट चल रही थी, तो she thought and it's recorded. फास्ट तो करनी पड़ेगी ना, because still we have ray optics. After this, AC, ray optics, wave optics, modern physics. A lot of discussion we have. Quickly do this question. Read this question first of all. What this question says. Uniform magnetic field is restricted within a region of radius r. Okay, this is the region of radius r. The magnetic field changes at this rate in the loop number 1. This is the loop number 1. Okay, this is the loop number 1, and the magnetic field is changing in this much region. Okay, that's fine. Loop 1 of radius r greater than r encloses the region r of loop 2 of radius r is outside the region of magnetic field. What are they asking? They are simply asking about the EMF. So is there any flux that's changing? Is there any flux that's changing from the loop 2? Definitely no. Is there any flux that's changing from the loop 2? Definitely no. So the EMF through the loop 2 is going to be 0. EMF through the loop 2 is going to be 0. Okay, that means answer is going to be either C or B. Either C or B. If you talk about the flux change through loop 1, now the point is that how much area is exposed with the change in field. How much area is involved with the change in flux. Listen, how much area is involved? The red area or the yellow area? The red area or the yellow area? How much area is involved? The red area or the yellow area? Definitely the smaller area, yellow area. That means it's going to be this much. The answer is D. The answer is going to be what? That's going to be D. Okay, so let's take the discussion ahead. Simple discussion it was. Okay, so read the question. Another simple question coming in front of you. The total charge induced in a conducting loop when it is moved in magnetic field depends upon what? Rate of change of magnetic flux, initial flux, total change in magnetic flux, final magnetic flux. Definitely depends upon the total change in the magnetic flux, because they are talking about the charge. So delta Q equals to delta phi by R. Have we seen this? Have we seen this expression? Have we seen this expression? Definitely yes, we have derived this expression. Cool. So let's take the discussion ahead. Another question coming in front of you. In which of the following devices the eddy current effect is not used? Not used. Okay. So electric heater, yes, by changing the magnetic field, there is generation of reversal in the direction of the flux. So heating is there. So yes, heater is the device in which the eddy current is used. Induction furnace, magnetic brake, electromagnet. This is the answer. Okay. In these all three of them, the concept of eddy current is used. So the answer is going to be D. Answer is going to be D. Okay. Oh, sorry, electric heat. Sorry. Electric heater it is. It's not magnetic heater. Sorry. A is going to be the answer. Electric. I didn't read the word electric heater it is. Okay. So the answer is no concept of magnetism is used in electric heater. Electric heater they are asking. This is electric heater. Okay. This is the resistance and current passes through the resistance. So P equals to VI. Okay. I square R. This much amount of energy is liberated. Okay. This much heating is done. Answer is A. Answer is going to be A. Okay. All of you, not C, not D. Is this point clear? Some people are saying C. Magnetic braking, no. In magnetic braking, the braking is done due to the eddy current. What is Sumit saying? Sumit has not given the answer. All of you send the answer. Got it? Okay. Next question again based on the eddy current. So eddy currents are produced when? Plus 4 minus 1, quick. Again a PYQ. ABCD, simple question. A metal is kept in varying magnetic field. A metal is kept in steady magnetic field. Circular coil is placed in a magnetic field. Current is passed through a circular coil. So basically, what is eddy current? What is eddy current? Simply the eddy current is the current produced due to the reversal of the direction of magnetic field. That means if the magnetic field is varying, there is going to be presence of eddy current. That means the answer is going to be A. Simple. Okay. So here we go. Yeah. So after this, another concept of AC generator. Okay. Basically, If you talk about the AC generator, just remember first of all that due to the varying flux, there is EMF generated, time varying flux, okay, d phi by dt, d phi by dt, what is phi? What is phi? Phi equals to B A N I, okay, B A N I by dt. Okay, so this expression can be written, BAN times of sine omega t. Okay, BANI sine omega t. Okay, inductor. If you talk about the inductor, basically what inductor is, what inductor does. Just a second, this is EMF, na? So no. This has to be omega. Sorry. See, write the expression something like this. Write the expression phi equals to B A cos of theta. Okay, phi equals to B A cos of theta. Substitute it over there. NBA cos theta. Okay, NBA cos theta. So d phi by dt is going to be the differential. Okay, d by dt of NBA cos theta, and let's say that theta is omega t. Okay, theta is omega t. So take NBA outside. Take NBA outside. This is d by dt. This is d by dt of cos omega t. Okay. So if you differentiate this, what do you get? If you differentiate this, minus NBA, omega comes out. This is sine omega t. Okay. And there is a negative, this gets positive. So this is the EMF. Okay. This is the EMF. Okay. Is this point clear? Important discussion. Okay. EMF corresponding to the AC generator. Okay. Now you're talking about inductor. Basically what inductor is? It's a system of n number of coils which are placed closely. Isn't it? So according to Lenz's law, you know that every time the current passes through the coil, the flux is going to get changed in the neighboring coil. Yes or no? The flux is going to get changed in the neighboring coil, and the inductor doesn't like it. Inductor doesn't like all this. Okay. Inductor hates the change in flux. Inductor hates. Okay. So let's say he is inductor. Let's say this fellow, he is inductor. So inductor is very pissed off if the flux changes. So he hates what? He hates the change in flux. Inductor hates the change in flux. Okay. Remember the expression for the flux. What is it? It's phi equals to Li. EMF equals to minus of L di by dt. L mu naught n square Al. Remember this expression for the self inductance. Remember the expression for the self inductance. Okay. It depends upon n square. N is number of turns per unit length. Okay. Okay. E is half Li square. E is half Li square, the energy. Okay. Let's take the discussion ahead. Now see, I'm giving you a comparison. Very important comparison between the magnetism and electrostatics. Okay. The comparison between magnetic field parameters and the electric field parameters. Okay. So if you talk about the energy density, that's half magnetic energy density, half mu naught B square. What it is? It's half mu naught B square. If you talk about the electrical energy density, we remember what it is, UE. That's half epsilon naught E square. So remember, always I'm giving you a thumb rule. Listen, students, listen, thumb rule. Whenever you are comparing electric and magnetic fields or any parameter of magnetism and electricity, simply replace epsilon naught by 1 upon mu naught. Getting what I'm saying? Yes or no? Hello, all of you, where are you? What I'm saying, if you are comparing electricity and magnetism, electric field, magnetic field, any parameter, replace epsilon naught by 1 by mu naught. That means this is epsilon naught, replace it by 1 by mu naught, you get the magnetic field density. Oh, where is everyone? Am I not getting the chat, or you're not answering, all of you? If we talk about, okay, this is important. This is important. Remember this. Okay, cool. That's nice. After this, if you talk about the combination, the equivalent, if you talk about the equivalent combination of the inductors, that's going to be simply L1 plus L2 and L1 L2 upon L1 plus L2 in the series and in the parallel combinations. Okay, these are going to be the results of the series and parallel combination. Now there is another important term that we need to discuss and basically try to understand what actually it is. Let's say this is one loop, I am drawing it with white color, okay, and there is another loop inside it that I am drawing with the yellow color. Just think about it, okay, think about it. If current passes through the inner system, okay, if current passes through the inner system, definitely there is going to be current in the inner coil, so there is going to be a magnetic field in the inner coil, and this is going to be the magnetic field that has developed. Imagine initially there was no magnetic field, but now since you have sent current in the inner coil, there is a magnetic field linked with the whole system, and there is going to be a change in flux. What you have done? You have sent a current in the inner system, in the inner coil, and due to this what has happened? Flux has changed, okay, with outer coil. Oh, the flux has changed with the outer coil. That means by sending the current in the inner coil, by changing the flux of one coil of the inner coil, you are developing a change in flux in the outer coil. That means you are developing an EMF in the outer coil. This phenomena is what we call as the mutual inductance, and this is the coefficient of mutual inductance that you need to remember as it is. Okay. Apart from this, remember the reciprocity theorem. Equivalent inductance is going to be L1 plus L2 plus minus 2m. What is m? This is m. Okay, root over L1 plus L2. Just remember this. Okay, let's take the discussion ahead. I'm giving you a question. Try this question. All of you. Try this question. Two coils of self-inductance, this and this. Every concept would be clear. Just read the question and try this. रे सिंह, आप ऐसे इंग्लिश कंटिन्यूस कैसे बोलते हो? हमसे बीच में हिंदी शब्द निकल जाए। मेरे साथ भी होता है ऐसा। Especially if someone irritates, then by default English out of by default the Hindi comes out. Okay, then you have to think, oh no, this is an English channel, so we have to show anger also in English. So read this question anyways. These are L1, L2. Simply what you need to find out, mutual inductance between the coils, M equals to root over L1, L2. So what's going to be the answer? D is going to be the answer. D is going to be the answer. Okay. So let's take the discussion ahead. Now what we are beginning with? We are beginning with the concept of alternating current. Okay. So just give me 2 minutes. I'm bringing some water. Just wait for 2 minutes. Okay, all of you. Yeah. So we are back after the break. Hmm. All of you there? All of you? Yeah. Yeah, we will do ray and wave optics just after this. This is a very short topic. See, AC is actually a very short topic, and there are some concepts that need to be discussed right now. Okay, because back to back questions are being asked from these concepts. The first concept that I'm talking about, it's this. See, if someone asks you that what kind of current do you measure from the galvanometer, or what kind of current the galvanometer is going to measure, it's going to detect only the unidirectional DC current. Remember this. Okay, then what kind of current is going to be then what device are you going to use in order to measure the AC current? It's going to be a hot wire ammeter. Remember that hot wire ammeter can measure both AC as well as DC current. Hot wire ammeter can measure both AC as well as DC current. Okay, but if you talk about the DC current, if you talk about the moving coil galvanometer, it can measure only the DC current. Okay, remember this. Average value of current is going to be integral I dt divided by integral dt. Okay, RMS value, root mean square value, integral I square dt divided by integral dt. If in a question they have given you value of current and voltage, so by default, if nothing is mentioned, take them as the RMS values. Yes, very good, Ayan. Very good, Ayan. By default, take them as the RMS values. Okay, let's say you have a system in which current has been given I equal to I naught sine of omega t. So what is I naught? I naught is the maximum value. What is I naught? I naught is the maximum value of the current. Okay, so what's going to be the RMS value? If this is the maximum value, what is going to be the RMS value? That's going to be I naught divided by root 2. Okay, that's going to be what? That's going to be I naught divided by root 2. Yes. So RMS. Basically, we talk about the RMS value. So this is only measured by the devices, and this is what the reading. Okay, if reading has been given to you, then by default you have to take it as the RMS value. Yeah, so read the question what it says. Two cables of copper are of equal lengths. One of them has a single wire of area of cross section A, while the other has 10 wires of areas of cross section A by 10 each. Okay, A by 10 each. So what are they asking? Give their suitability for transporting AC and DC. Okay, so remember the concept that if you talk about single strand, that means single wire. So single strand is used for DC, while if you want to transfer AC, you need multiple strands. Okay, so if you talk about the transferring of wire, you might have seen that there are n number of small wires inside that big wire. Okay, so remember that multiple strands for AC, single strand for DC. Okay, a very important concept, these basic concept. Okay, I'm very sure that questions are going to be asked from these concepts, these 2-3 concepts that I said now. That every concept during the session which I emphasized on, and I said that this is very important. Okay, so there is a very high probability that you might see question from these concepts. Okay, yeah. So anyway, just remember this basic table that I'm giving you. Okay, if you talk about any sinusoidal function, might be sine, might be cos. Okay, no matter what sinusoidal function you take, if you talk about a sinusoidal function for a complete curve, for a complete cycle, plus, minus, plus, okay, 0 to 2 pi, 0 to 2 pi. Okay, then for this complete cycle, the average value plus minus going to be 0. Yes or no? Definitely yes. Sinusoidal AC, square AC. Okay, no matter what is square AC. This is the square AC. This is sinusoidal AC. This is square AC. Okay, and this is triangular AC. This is triangular AC, something like this. Okay, so for sinusoidal AC 0, triangular 0, square 0. Okay, if you talk about the average value for sinusoidal, this is 2 I naught by pi. This is 2 I naught by pi. Yes. Yeah, this is very important discussion. It has been given in NCERT also. In every coaching material, it has been present because it is very important. So for square, this is going to be I naught. Okay, simply I naught. And for triangular, it's going to be I naught by 2. Okay, because the area half base into height. RMS value I naught by root 2. I naught by root 3. Okay, remember this. Remember this discussion. Okay, fine. After this, if we talk about the different circuits, okay, so let's try to analyze the different circuits that we are going to see. First, we are going to talk about the pure resistive circuit, then pure capacitive circuit, pure inductive circuit. Okay, after that, the combination of L and R. After that, the combination of C and R, that means RC circuit, and then L C circuit, and then series LCR circuit. Okay, so quickly, last question A. Which question A? Which question is going to be A? Let's check. Last question. This one. No. For DC, we use single strand only. Remember this, Sumit. A hoga. In which one? In which one are you saying? In which one are you saying A? Where? A, B, C, D. I have not given a question over here. Which question are you asking, dear Sumit? Anyways, you tell me later on. Let's continue with the discussion. Whatever the doubts you're having, I'll be addressing it after the session. Okay, I'll be waiting for some time. Don't worry. Let's come back to the discussion. What I was saying that how can you remember all the circuits together? How can you remember all the circuits? See, if you talk about a pure resistive circuit, okay? If you talk about a pure resistive circuit, so what is going to be a resistive circuit? This is a resistance and this is the source of alternating current that you have applied over here. Okay, so this is the current in the circuit. This is the current flowing in the circuit at any instant I. So what are you going to write? What are you going to write? You are going to write E minus IR equal to 0. That means E equals to IR. E is what? What is E? E is E naught sine of omega t. E naught sine of omega t. Yes or no? E is what? E is E naught sine of omega t. And what is I? I is E by R. That means E naught sine omega t divided by R. Okay, E naught sine omega t divided by R. So what is E naught by R? This is I naught. So remember, for purely resistive circuit, or for a pure circuit, I and R are in phase. I and R, or simply I and V, sorry, are in phase. Okay, I and V are in phase. Okay, that's cool. So if you talk about a capacitive circuit, if you talk about a purely capacitive circuit, then the phase difference between I and V is pi by 2. Okay, who leads? Voltage leads. Remember, who leads? Voltage leads for a purely capacitive circuit. How? If this is a capacitive circuit, this is the source of alternating EMF. This is C. This is C. Okay, E minus V. What is V? Q equal to CV. V equals to Q by C equals to 0. So from here, if you find, you get the expression something like this. This is I. This is going to be V. V is leading the current. What you have written? You have written for the purely capacitive circuit, listen, all of you, for the purely capacitive circuit, voltage is lagging the current. And for purely inductive circuit, voltage is leading the current. Okay, so sorry, here we are going to change it. This is voltage is lagging the current, or simply you can draw the circuit. You can redraw the circuit something like this. Voltage is lagging. This is V, this is I. Remember, if this is I, okay, for a resistive circuit, this is V. Okay, you are talking for a capacitive circuit. For a capacitive circuit, V is lagging. For inductive circuit, V is leading. For purely inductive circuit, V is leading. Resistive, capacitive, inductive. What happened? Yadav boy, why are you spamming so much? Don't spam. You have to cover a lot of discussion right now. Yadav boy, कुछ नहीं आता तो पढ़ाई करो ना चुपचाप. स्पैमिंग क्यों कर रहे हो? ब्लॉक करूं क्या अभी? Don't do this. Okay, listen. Resistive, capacitive, inductive. Okay. So what we are saying, if this is a purely capacitive circuit, who is lagging, who is leading? Simply remember this table that I've given over here. For a capacitive circuit, current is leading. For a purely inductive circuit, voltage is leading. Okay. Now, if you talk about RL circuit, this is R, this is L. Okay. Phase differences between 0 to 90. Power factor R by Z is between 0 to 1. Impedance, that means net resistance. You can say net resistance. Okay. What is the net resistance? What is the impedance? That is root over R square plus, if you're talking about capacitive circuit, you are going to say XC square. If you're talking about inductive circuit, it is root over R square plus XL square. Okay. And what are XL and XC? XL is the inductive reactance, that means the resistance or the hindrance offered by inductor. XC is omega C, that means the hindrance offered by the capacitive circuit, by the capacitor. Okay. अरे इतनी एंजाइटी लेके कहां जाओगे? शांति से पढ़ो ना चुपचाप. See? Okay, remember this. So if you talk about RC circuit, this is root over R square plus XC square. What is XL? What is XC? Let's have a discussion upon XL and XC. See, just a second. What is XL? What is XC? XC is omega 1 by omega C. XC is 1 by omega C. Okay. If you talk about inductor circuit, if you talk about the inductive circuit, XL is simply omega L. Okay. What is omega? Omega is 2 pi F. So 1 upon 2 pi FC. This is the hindrance offered by the capacitor. This is the hindrance offered by an inductor. Okay. That's 2 pi FL. This is XL. Okay. So if we compare, listen, if we compare the behavior of capacitor and inductor, okay, for AC and for DC, listen very carefully, important discussion I'm giving. So you are saying that what is XC? XC is 1 upon omega C, isn't it? 1 by omega C. Omega is 2 pi F. XL is omega L. That means if you talk about AC circuit, XC is inversely proportional to frequency. That means greater the frequency, lesser is going to be the hindrance, lesser is going to be the capacitive reactance. If you talk about DC, for DC frequency is 0. So if you apply a capacitor to a DC circuit, frequency is 0, XC is going to be infinite. Okay, the hindrance is going to be infinite. Yes. After this, if you talk about this XL, so XL, that means inductive reactance is proportional to what? It's proportional to the frequency. Okay. So if you talk about AC, it's proportional to F, but for DC, we know for DC, frequency is 0. For DC, frequency is 0. So XL is going to be 0. That means it's going to behave as a wire, and this is going to behave as an open circuit. Okay, important discussion. Okay, this is going to behave as a wire, and this is going to behave as an open circuit. So if you plot a graph, okay, let's say you plot a graph for pure capacitive circuit, okay, so you can say that XC is inversely proportional to frequency. If you plot a graph for inductive circuit, XL is proportional to the frequency. XL is proportional to the frequency. Write this down. This point is very important. Okay, important discussion. Is this point clear? Now see, if I talk about combination of circuits, let's say we are talking about the LCR circuit, okay? So combining the three discussions that we had, regarding the resistive, inductive and capacitive circuits, we can say if we are talking about the resistive circuit, so I and V are in same phase. We know this, isn't it? If you talk about a capacitive circuit, then who leads? The current leads. So this is going to be VC. I said now this is VC. Oh, who is this? Let's block him. Okay. Yeah. Now listen. If this is VC, this is VL. Okay, this is VL. So what is going to be the net? What is going to be the net circuit, the net phasor diagram? You can say that the net resistance, that's what we call as the impedance. That's going to be Z. And what is going to be Z? Z is going to be root over R square. This is R square plus. Now you can write XL minus XC the whole square. Okay, XL minus XC the whole square. Okay. Wait. Yeah. So battery was over. All of you. Now can you hear me? All of you. Now am I audible? Yeah. So what I was saying that when the current is going to be maximum, when the current will be maximum, tell me. When the current is going to be maximum, when this factor is going to be minimum. That means when XL is equals to XC, that means omega L is equals to 1 upon omega C, isn't it? That means omega is equal to 1 by root over LC. This is what we call as the resonance frequency. This is what we call as the resonance frequency. Okay. Okay. Is this point clear? Yeah. So now listen very carefully. This is an important graph that I am giving you. Very important graph. So have a look over here. What we have written? We have written that what is the condition of resonance? Resonance condition is XL is equals to XC. That means omega is equal to 1 upon root over LC. That means omega is nothing but 2 pi f. Omega is nothing but 2 pi f. So f equals to 1 upon 2 pi root over LC. Root over LC. Okay. Okay. In this situation, VL, that means the potential drop across. Yeah, the boy. Why you're doing this? Okay, bye. Yeah. So listen. So you can say that potential drop across both of them is going to be same. Definitely yes. So what is omega? Omega we have written root over LC. Okay. Z minimum, the minimum resistance is going to be in the resonance condition. That's why that's equal to R cos phi, which is R by Z equals to this much. Okay. 0. V net is equal to VR. Okay. Now listen. If you talk about this portion of the graph, if you talk about left portion of the graph, okay, so you know that Z is nothing but root over R square plus XL minus XC the whole square. Okay, XL minus XC the whole square. Okay, that means if you talk about this particular portion, if you talk about the left portion, this portion is going to be the capacitive portion. Capacitive. This portion of the graph is going to be the inductive portion. Okay, because if you have a look at the situation, definitely if this factor is going to dominate, okay, you are going to be on the right hand side. If XC dominates, you're going to be on the left hand side. Okay. Okay. दोबारा कौन आ गया? यादव boy. You have blocked him, na? I blocked this man, but don't worry. Yeah, come back to the point. So. Come to the question. Read the question, what it says. A circuit when connected to an AC source of 12 volt gives a current of 0.2 ampere. The same circuit is connected to the DC source of 12 volt gives a current of 0.4 ampere. 0.4 ampere. So what is going to happen? What is going to happen? Quickly. What's going to happen? Quick. Fast. Circuit connected to AC source gives you 12 volt. Okay. So let's say this is the circuit connected to the AC source. Okay. This is the AC source. Gives you a current of I equals to 0.2 ampere. Okay. 0.2 ampere. Same circuit is connected to the DC source of 12 volt. Same circuit is connected to the DC source of 12 volt. Gives you a current of 0.4 ampere. Gives you the current of 0.4 ampere. So what can be that particular situation? What is going to happen in that situation? All of you. What circuit is it going to be? If you talk about the circuit, what circuit it can be? Just think about the series. Just think about the series LR circuit. Okay. Think about the series LR circuit. So it's going to be this. Okay. All of you do this. Next question. 40 millifarad capacitor is connected to 200 volt 50 hertz AC supply, the RMS value. RMS value is going to be what? RMS value. RMS value, what it's going to be? I equals to V divided by R. What is R? R is XC. So what is V? What is V? V is how much? V has been given to you as how much? That's 200 divided by XC. XC is what? XC is 1 upon omega C. Substitute and calculate. Substitute this and calculate. Quickly, how much do you get? Quickly, this value that has been given to you, definitely it's going to be RMS value. Fast. So how much it's going to give you? If you substitute, this is 200 into omega. Omega is 2 pi F 50 into C. That's been given to you as 40 milli. That means 1, 2, 3. 1, 2, 3. Okay, so this is going to be how much? This is going to be how much? This is going to be 10 into 2 into 4. Just calculate this. How much do you get? 40 into 5, 200 into 4,000. Okay. 5, 1, 2, 3, 1, 2, 3. 20, 20 into 20 into 2 divided by, that's millifarad, that's hertz, that's RMS. Okay. So quickly calculate this. Calculate. How much current are you getting? How much current are you getting in the situation? Substitute and calculate. Okay. 200 volts into 2 pi into 50 into 40 into 10 to the power minus 3. So this is the answer. Okay. Calculate and get the answer. Let's come to the next question. Series LCR circuit is connected to an AC voltage source. When L is removed from the circuit, the phase difference between the current and the voltage is pi by 3. Okay. Instead, C is removed from the circuit, the phase difference is again pi by 3. Phase difference is again pi by 3. Okay. Between current and voltage. Okay. The power factor of the circuit is going to be, 45 seconds for this question. NEET 2020 latest question, plus 4 minus 1 quickly. Plus 4 minus 1. Be fast. All of you be fast. Quick. What is the question saying? Power factor you need to find out. Power factor you need to find out in this situation. Okay. What has been given to you? What data has been given to you? They are clearly saying that for LCR circuit, let's say this is LCR circuit. Okay. If L is removed, if you remove L, then what's going to happen? If you remove L, then the current and voltage are 60 degree out of phase. Okay, this is C, this is I. Okay, VC and I, time up. This is pi by 3. Okay, if C is removed, okay, again they are 60 degree out of phase, but we know that this is VL and this is I. Something like this. Okay, this is pi by 3. So this is the situation in front of you. This is the situation in front of you. Okay. So now what they are asking, if instead of C, what happens if this is removed? If V is removed, then you need to find out the power factor. Okay, so what is going to be the power factor? Power factor is going to be cos phi. Simply you know that for this situation, since the angle is same, power factor you need to find out. That's going to be how much? That's going to be 1. Why 1? Because if you compare these two graphs, I, VC and 60 degree, VL, I and 60 degree, this proves that VL equals to VC, isn't it? It proves that VL equals to VC. No. Why 1 by 2? VL and VC are same. What if VL and VC are same? Then phi equals to 0. If phi equals to 0, power factor is cos phi, that is equal to 1. This is going to be the answer. Phi equals to 0, that means cos phi equal to 1. See, if you have removed L, this is VC, this is I. Okay, so what is the phase relation? 60 degree. Similarly, if you remove C, this is VL, this is I. What is the phase relation? Again 60 degree. So what is the relation between VL and VC? Both are going to be same, isn't it? VL equal to VC. So you can say that for this situation, phi is equal to 0. Phi is equal to 0. If phi is equal to 0, cos phi equal to 1. Simple, isn't it? Cos phi equals to R divided by Z. Okay, and Z is going to be equal to R itself now, because XL equal to XC. Oh, getting or not? All of you getting what I'm saying? How many of you got the correct answer? Irshad, Sumit, Ray, Chitrali. Are you getting what I'm speaking for so long? Or just sitting and chilling? That this man will say what he has to say. Let's sit and enjoy. Getting what I'm saying? Why is it 0? Why phi is 0? Okay, this is cos phi, na? What is cos phi? Cos phi is R by Z. Z is equal to R. Z equal to root over R square plus XL minus XC the whole square. XL is equal to XC. Yes. This is the answer. Let's take the discussion further. Another question coming in front of you. A coil of self-inductance L is connected in series with a bulb B and an AC source of brightness and an AC source, sorry. The brightness of the bulb decreases when? The brightness of the bulb decreases when? This is NCERT, solved illustration. This is NCERT, solved example. Okay. What are they saying? This is basically an inductor. Okay. And the situation is connected to a bulb in series. Okay. Connected to a bulb in series. Let's say here you have a bulb. Here you have a bulb. You have a bulb over here. Okay. Something like this. Okay, that's fine. Now what is happening? If you insert a rod within this system, then what's going to happen? Think over it. All of you listen. You are going to say that what is XL? XL is equals to omega L. XL is equals to omega L, isn't it? And we know that this L depends upon N. This L depends upon L. So this factor is going to increase. XL is going to increase. In the situation, XL is going to increase. Okay. XL is going to increase. And if XL increases, if the XL increases, definitely current decreases. If current decreases, then definitely the brightness of the bulb is going to decrease if you insert an iron rod within the coil. Why? Because then XL is going to increase if you insert an iron coil. Why? You can say L is going to increase. Okay. Next question. Quickly. A small signal V equal to V naught sin omega t is applicable across an ideal capacitor C. So what happens? Capacitor. Current is in phase with voltage? No, definitely no. Current leads the voltage by 180? No, definitely no. Current lags the voltage by 90 degree? No. Capacitor, voltage, current. So current leads. So this is also wrong. Now, over a full cycle, the capacitor C does not consume any energy from the voltage source. Yes. Okay. Is this point clear? What is Irshad saying? 2. In this situation, 2. Where 2? Where? What are you saying? This na? So we have said 2 na? B. Okay, you were also saying the same thing. Okay, let's take the discussion ahead. I thought that you were saying something else. Let's take the discussion ahead. Here we go. This is a simple question that I'm giving as a homework to you. Okay. So now here we go. Yeah. Another important discussion that's coming in front of you is regarding the quality factor. okay, is regarding the quality factor. Now see, we have discussed the condition of resonance. Okay. So basically the point is that if you want to check the quality of the resonance, then what we are going to say? It is determined by a quantity, by a parameter, that's Q factor. What is Q factor? Q factor is omega naught divided by the bandwidth. Now what is bandwidth? This is the bandwidth. In front of you. Now try to understand that if you have two signals, okay, this is signal number one, this is signal number two, signal number one, signal number two. So which is a better signal? Which is a better one? Oh, again, some spammer has blocked it. Yeah, listen. So which is going to be better? This is delta. This is delta omega 1 and this is delta omega 2. So clearly the bandwidth in the second is going to be lesser. So you have so you have sharp resonance in the second situation. Yes or no? That means if you have two radios, okay, let's say this is your radio, this is Sontu's radio, and this is Montu's radio. This is Sontu, this is Montu. Okay, both are listening signals, both are listening radio from these two signals. So who is going to listen better songs? So let's say this, if this is the situation, what this is going to do, this is going to catch a long range of frequencies. So it might be possible that 2-3 songs are mixing. You are listening one song, another song is coming, and then you're not going to get a proper song in this situation. Okay, if you listen song with this particular pattern, you're going to get a sharp song. Okay, you're going to get a proper, audio from this particular situation. That means the Q factor is inversely proportional to the bandwidth. Definitely yes. So you write it as VL divided by VR. That means it's simply inversely proportional to R. Remember the expression 1 by R root over L by C. Okay, very important discussion. Okay, is this point clear? Okay, let's take the discussion ahead. Okay, read the question. What this question says: which of the following combination should be selected for better tuning of an LCR circuit? Better tuning means Q should be high. If Q should be high, R should be low, L should be high, C should be low, R should be high, R should be low, L should be high, C should be low. That means answer should be C. Yes or no? Quickly, all of you. Is this point very clear? Is this particular point very clear, all of you? Okay. Let's take the discussion further. What is a transformer? Transformer is simply a device which is used to step up or step down the value of the input potential at the output. Okay. You're going to either step up or step down the values of potential using this particular device. So how it works? Simply remember that it works on the Faraday's principle, that if there is flux change, EMF is going to be linked, and what it says, E equals to minus of d phi by dt, and we know that what is phi? Phi is nothing but B dot A, and if there are n turns, it's NBA. That means phi is dependent upon number of turns. So can you say that E is dependent upon number of turns, and can you say that E1 upon E2 or V1 upon V2 is going to be N1 upon N2? Just remember this basic discussion. Okay, very important. From here you can also find out the relation for current. So this is the discussion for the transformer, all of you. Let's take the discussion ahead. And here we go. Okay, so we are beginning with the concepts of electromagnetic waves. We are beginning with the concepts of EM waves. Okay, after this we will have a short break and we'll be beginning with the ray optics and wave optics. Yeah, so just a second. Hmm. Hmm. So basically what the discussion is, we know that electromagnetic waves are generated when you have an oscillating charge, when you have an accelerated charge. So if a charge is accelerated or is it oscillating, if the charge is oscillating, then what it does, it radiates energy, isn't it? Yes, we know it radiates energy. And the electromagnetic wave, how is it propagating? It has two components, the electric component, yes, the magnetic component, yes, and both the electric and magnetic component are mutually perpendicular to each other, and the energy is moving perpendicular to the direction of propagation of both of them. This is electric component, this is magnetic component. Electric, electric, magnetic, electric, magnetic, electric, magnetic, and the energy is moving this direction, something like this. Okay, yes, remember this. Now there's a very beautiful concept that's coming in front of you. It's the concept of displacement current. What's the concept? It's the concept of displacement current. Okay, displacement current. Now the thing is that, let's say if you have a parallel plate capacitor and you have an AC source, you have what kind of source? You have an AC source. Okay, so definitely at every given instant, the charge at the plates of the capacitor is going to change. That means the electric field in the situation, electric field in the situation is going to be what? Electric field in the situation is going to be what? It's going to be variable. Yes or no? Yes, na? Yes, it's going to be variable. So there is a variable electric field between the plates of the capacitor. Now the point is, Sumit is saying, sir, after 3 hours live stream will close automatically. Why it will close automatically? No, it will not happen. किसी बातें कर रहा है? अपने आप ही बंद हो जाएगी. See, if this is the current, if you place a magnetic needle over here, if you place a compass over here, there is going to be a deflection because there is current and there is a magnetic field due to that current. Yes or no? Yes or no? Yes. If you place the magnetic needle over here, yes, there is going to be a deflection because still there is a current. But if you place the compass over here and you get deflection, so now tell me that where is current in this situation? Do we have current between the plates of the capacitor? No. Do we have a wire between the plates? Now you're getting the current. Then how are you getting the current? That's what the point is. That's what the point is. So here comes the concept of displacement. Yes. Okay. And this current is generated due to the changing electric field. Why? Why? Because the changing electric field induces what? Changing electric field induces what? It induces changing magnetic field. Yes. And due to this, what happens? Due to this, the magnetic flux changes. Due to this, the magnetic flux changes. And if the magnetic flux changes, then what happens? If the magnetic flux changes, then what happens? Then EMF is induced. Why? Because induced EMF is minus of d phi by dt. Which phi? Phi E or phi B? Phi B. Yes. Yes, definitely. And if there is current, there is resistance, there is going to be a current. If there is EMF, there is going to be a current. And what current is it? This is displacement current. Okay. This is displacement current. Is this very clear? What is happening in the situation? Is this point very clear? Okay. Okay. So what is going to be the expression for the displacement current? What is going to be the expression for displacement current? At any given instant, you can say in the capacitor, let's say the charge in the capacitor is how much? That's Q. The charge over there in the capacitor is Q. You can write Q equals to CV. You can write Q equals to CV. Okay, you can write Q equals to CV. If you differentiate it, dq by dt, okay, equals to what? If you differentiate it, dq by dt is going to be what? It's going to be C times of dv by dt, or simply dE by dt. Whatever you want to write, you can write it. Okay, makes no difference. Okay, makes no difference. So what is going to be dv by dt? What is going to be dv by dt, or simply dE by dt? You know that this is going to be dq by dt. This is going to be dq by dt. That is nothing but I equals to C times of I equals to C times of dv by dt, isn't it? C times of dv or dE by dt. Okay, okay, okay. And what is E? E is nothing but minus of d phi by dt. E is nothing but minus of d phi by dt. So what is the cause? What is the cause of this displacement current? All of you, are you there? Are you there? All of you? Hello, 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 hello. Listening? Yeah, so the point is that the displacement current, what actually it is? It is the current in the situation due to the changing flux, changing magnetic field, changing electric field. So the IE is nothing but epsilon naught times of d phi by dt, okay? Simply, what you can write about phi E? What you can write about phi E? This is nothing but epsilon A times of dE by dt or dV by dt, one and the same thing, okay? C is what? C is epsilon naught A by D. C is epsilon naught A by D. Write it D, write it L. L is the separation between the plates. That makes no difference. Okay, remember the expression. Remember the expression. Is this point very clear? Let's take the discussion further. Is this point very clear? Remember this discussion. And remember one more thing. That for the stable system, we take I displacement equal to I conduction. What is the conduction current? The normal current that flows through the wire. The current over here inside the plates of the capacitor, that's displacement current. The current in the wire, that's conduction current. Current between the plates, that's displacement current. Okay. Harshit is saying BMC yaad hai ki nahi? Okay, Harshit was with BMC. Very nice. Good, Harshit. Okay, let's come back to the point. So there's a question coming in front of you. There is a question coming in front of you from NEET 2019. Read the question. Parallel plate capacitor 20 microfarad being charged by a voltage whose source potential is 3 volt per second. Conduction current through the connecting wires and the displacement current. You need to find out IC and ID. Definitely IC and ID are going to be same. So directly you can mark the answer as C. No need to waste time in this question. Okay, IC is going to be ID, conduction current is going to be equal to displacement current. Now some expressions. I clearly said that if you are comparing electrostatics and capacitance, if you are comparing electrostatics and magnetism, listen, every single formula. If I talk about, listen, all of you listen. If I talk about the energy densities, okay, if I talk about the मैथ्स लवर इज सेइंग नींद आ रही है तो जाके सो जाओ ना, कौन रोक रहा है तुमको? जिसको पढ़ना है वो पढ़ो, जिसको सोना है वो सो, कोई दिक्कत वाली बात नहीं है. Listen all of you. If you want to go and sleep, just go and sleep. If you want to study, then quietly study. We are going to complete the syllabus, then only we are going to end the class, okay? No matter how much time it takes. Yes, okay, see. So electrostatic energy density, that's half epsilon naught E square. If you talk about magnetic energy density, right now I said that if you are comparing electrostatics and magnetism, electricity and magnetism, epsilon naught gets replaced by 1 upon mu naught. Yes or no? Epsilon naught is going to get replaced by 1 by mu naught. Okay, remember this. After this, average electrostatic energy density is 1 by 2 epsilon naught E square. Average magnetic energy density is 1 by 4 mu naught into B naught square. Okay, is this point clear? Energy density in EM waves is simply B naught by mu naught. Okay, total energy density. We have added these two. We have added the two. Okay, average energy density in EM waves half epsilon naught E square. Okay, let's take the discussion ahead. Let's take the discussion ahead. Now see, another important point in EM waves is the pointing vector. So what is basically pointing vector? Try to understand. These are the x, y and the z axes. These are the x, y and the z axes. Okay, x, y and z. So this is the energy that's transferring along the x-axis. Okay, that's fine. Okay, electric field. Let's say this is the magnetic field. This is the direction of the magnetic field. Okay, this is the direction of the electric field. Listen, all of you. So the direction of energy, is perpendicular to both of them. If this is electric oscillation direction of electric field vector, if this is the direction in which electric field vector is oscillating, this is the direction in which magnetic field vector is oscillating, energy is perpendicular to both of them, and it's represented by a vector. That means c, the speed of that wave is going to be along E cross B. Remember, and this is the pointing vector. E naught cross B naught divided by 2 mu naught. Remember, okay? Very nice, Harshit. Very happy for you. One of my ex-student, I used to teach him in the offline classes. So Harshit Vasisht, he is presently studying at AIMS Bhubaneswar. I've taught him in one of the offline coachings in Indore. Yeah, all of you, let's take the discussion ahead. Here we go. Read the question. Light with an average flux of 20 watt per meter square. Now read if you don't know what basically this flux is, what actually this quantity is. So this is watt per centimeter square. So what is going to be watt? What is power? Power is energy per unit time, and this is area. So what is this quantity? This quantity is intensity, energy per unit area per unit time. That means how much energy is falling on a given area, in a given amount of time. Okay, getting the point? So remember this point. So area has been given to you, the energy received by the surface in a span of 1 minute. That means if the time is 60 seconds, okay, then for this situation, what is going to be the energy? So you can simply say energy is intensity, that means flux, into, just a second. Time is nothing but energy divided by intensity into area. Substitute with proper units. Okay, over here, calculate it, what you're going to get. Energy. Okay, how much has been given to you? Energy received. You need to find out E. That's going to be T into I into A. Okay, T into I into A. How much time? 1 minute. How much intensity? 20 watt per centimeter square. That means 10 to the power minus 4. 20 divided by 10 to the power minus 4 into area is 20 centimeter square. So again it gets cancelled. 20 into 20. Substitute it like this. Okay, this is going to be the answer. That means it's going to be C. Okay, C. This is going to be the answer. Let's take the discussion ahead. Next question coming in front of you. The ratio of contribution made by the electric and magnetic field component to the intensity of an electromagnetic wave. That means what's the component of electric and magnetic field? It is equal. Okay, it is 1:1, because the energy density, average energy density of the magnetic field, average energy density of the electric field is same. Okay, remember this. Next question coming in front of you. For a transparent medium, relative permittivity and relative permeability are epsilon r and mu r. Okay, so you know that the speed of light is 1 by root over mu naught into epsilon naught. Okay, speed of light in any given medium can be written as speed of light in any given medium can be written as 1 by root over mu m into epsilon m, and we know that mu r is mu m divided by mu naught. Mu m divided by mu naught. Okay, mu r, epsilon r is epsilon m divided by epsilon naught. Okay, so you can substitute the value over here, and what do you get? Substitute the value over here, and what do you get? You get root over mu m is mu naught into mu r into epsilon m is epsilon naught into epsilon r. This is V. Okay, so 1 by mu naught epsilon naught is going to be C. Oh, all of you. 1 by mu naught epsilon naught is going to be C, and this is mu r epsilon r. Very important relation. Okay, direct formula can also be asked, so you need to remember this expression the way I have derived it. Okay, substitute the data and get the answer. All of you, quickly substitute the data and get the answer. Now I'm leaving it for you. Everything I have done, 3 into 10 to the power 8 mu r epsilon r, everything has been given. Substitute and find the answer. Okay, next question. An EM wave is propagating in a medium with a velocity. What is the direction given to you? Velocity is I cap. Okay, that's I cap. That's cool. The instantaneous oscillating electric field is along the y-axis. Instantaneous oscillating electric field is along the y-axis. Okay, that's along j cap. That's along the j cap. That's fine. So the direction of oscillating magnetic field, is going to be where? What's going to be the direction of oscillating magnetic field? Let's find it out. We know that the Poynting vector is given by E cross B. So this is E cross B. Where should be B? So that the thumb gives you C. This is C, na? This is the direction of propagation of the wave. This is the direction of energy, isn't it? So E cross B, where should I cross this finger so that the thumb gives me the direction of the energy? This is over here, E cross B. That means this is plus Z. Okay, plus Z direction. Simple but important. Simple as well as important. Okay. Is this point very clear? Let's take the discussion ahead. The next question coming in front of you. In an electromagnetic wave, okay, this is a very simple question. You need to do this homework. Okay, let's take the discussion ahead. Another question that's coming in front of you. Try this question. Out of the following options, which can be used to produce electromagnetic wave? How do we produce electromagnetic waves? We know chargeless particle, no. Charge moving with constant velocity, no. Magnetic field is produced. Stationary charge, electric field is produced. Accelerating charge. So B is going to be the answer. Okay, let's take the discussion. Here we go. An electromagnetic wave of frequency has been given to you. Okay, passes through dielectric medium with relative permittivity. Then what happens now? See, I'm giving you a thumb rule. I'm giving you a general rule. If a wave, any wave passes, very important point this is, note, if any wave passes from one medium to another, then what happens? Then frequency, phase and color do not change. Rest everything changes. Frequency, phase and color do not change. Rest everything changes. Lambda changes. Yeah, very good, Ria. A lot of you remember the thumb rule. Okay, Very nice, very nice, very nice, very nice, very nice. Good. So frequency, phase and color do not change, and rest everything is going to change. So frequency is unchanged. Lambda is going to change because the speed definitely is going to change. Okay, speed is going to change because the relative permittivity has been given to you. Relative permittivity has been given to you. So you can find out lambda. You can find out lambda. Lambda is going to change. The frequency is not going to change. Remember, this rule is applicable everywhere. Okay, not just about this electromagnetic wave or optics. Everywhere it's applicable. The ratio of amplitude of magnetic is to the amplitude of electric field gives you what? That gives you C equals to E by B. Remember, E equals to BC. E equal to BC. So they are asking you about the magnetic is to electric field. That means B by E. That is going to be 1 by C. So reciprocal of the speed of light in vacuum. Simple. Okay. Is this point very clear? So let's take the discussion ahead. So I think we are done with the discussion. Sufficient discussion has been done. Now we are just a second. Just a second. Yeah. So here we are. We are about to begin a new chapter, that's ray optics. So we will begin the discussion of ray optics after the break. So this is a break of 10 minutes. Okay. This is a break. Okay. Of 10 to 15 minutes. Let's say 15 minutes break. And after this break, what we are going to do? After this break, what we are going to do? We are going to cover ray optics, wave optics, dual nature, atom, nuclei, and semiconductor. Okay. The major portion is this topic. The amount of time that's going to be consumed in ray optics and the amount of time that's going to be consumed in all of them is going to be same. Okay. So we will meet after 15 minutes. Okay. So all of you drink water, drink coffee, whatever you want to do. Okay. 15 minutes break sharp. Okay. So have a look at the time. It's nearly 1:40. So 1:55. 1:55. Okay. 1:55. Let's say nearly 2. Okay. Nearly 2. So all of you have some water. Okay. Have some tea, have some food, and come back. Okay. Because we are going to finish the whole syllabus today, no matter how much time it's going to take. Hello, 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 hello. Can you hear me, all of you? Can you hear me, all of you? Audible? Yeah. So here we go. Let's begin the discussion of ray optics. Let's begin the discussion of ray optics. Another very important discussion that we need to have. Now see what the discussion from where we are beginning the discussion. Let's say you have a source of green light. Okay. You have a source of green light, something like this. Okay. So what is the question? What is the question saying? Listen, what the concept says, that the observer will sense. The observer is going to sense what? The observer is going to sense what? If you are observing from here, that means if there is a medium change, this is medium 1 and this is medium 2. This is medium 1 and medium 2. So you know that due to change in medium, what three properties do not change? Give me that general thumb rule. Frequency, phase and color do not change, isn't it? Yeah, Shalini, definitely you will get the notes on the app. Okay, notes will be available on the PW app. You can simply download and download the app and download the notes. Okay. So if the medium is changed, the frequency, phase and color are not going to change. That means the observer is going to observe green color only. It's as simple as that. Okay. After this, the next question, which balloon will burst first? Okay, which balloon is going to burst first? Let's say you have a red balloon, and you have a green balloon. Okay, you have a green balloon and you are giving a source, of green light. Okay, listen, you are giving which light? You are sending green light. Then in this situation, which balloon is going to burst first? Tell me quickly. Red, green, both at the same time. Now, why this question is given? Because it involves another very important concept of ray optics, another very concept of optics, that how do we observe anything? If you can see me, that's because of the reflection that's taking place, isn't it? So if someone can observe green balloon, that's because the green light is reflected from that green balloon. So it is going to reflect the green light. It is going to do what? It's going to reflect the green light. It's going to reflect green. And what it's going to do? Why is it red? Because it's going to reflect red. So it's going to absorb the green. So it's going to absorb the green light. And if it absorbs the green light, then definitely its temperature is going to increase and it's going to burst. Okay. No, someone is saying at the same time. Definitely no, at the same time. A is the answer. Is this point very clear? All of you quickly. Yeah. So here we go. Reflection. What is the reflection? Reflection is simply the bouncing back of light through a shiny surface. If this is a plain shiny surface, okay, polished over here, something like this, and let's say this is the normal, this is the normal, okay, that's fine. Incident light, reflected light. Okay, angle of incidence, angle of reflection. Angle of incidence equals to angle of reflection, and the incident, reflected and normal, all three lie in the same plane, isn't it? We know this. Do we know this? Definitely yes. After this, if you talk about the deviation from a plane mirror, just remember that if this is a plane mirror, if this over here is a plane mirror in front of you, let's draw the normal to the mirror. This is the normal to the mirror. This is the normal to the mirror. So if this is the incident light, okay, and if this is the reflected light, let's say this is the angle of incidence I, angle of reflection R. Okay, so I and R are same. Light wanted to go along this red line, but it is going through this line, incident, reflected. So this is the angle of deviation delta. This is the angle of deviation delta. So what is going to be delta? Delta is going to be, what is going to be the delta? See, what is going to be delta? That's 180, minus 2i. That means 2 pi minus 2i. Okay, because I and R are same. Okay, oh sorry, 180 is pi. Pi minus 2i. Pi minus 2i. Remember, this is delta. Simple. Let's take the discussion ahead. Again, a spammer is there. Let's block this spammer. Here we go. Just a second. Yes. Yes. Okay. So this is the deviation. Okay. This is the deviation delta. So there's a simple question coming in front of you quickly. We have to speed up fast, all of you. You need to find out the deviation. So what is going to be the deviation? This is the incoming light and this is the reflected light. So delta is simply going to be, this is 60, this is 60. So what is going to be delta? That's going to be 180 minus 2 into 60. That means 180 minus 120. The answer is going to be 60 degree. Okay, this is the delta. This is the delta. Let's take the discussion ahead. So here we go. You need to find out the angle alpha. You need to find out the angle alpha over here. Incident light. This is the reflected light. Okay. So if this is 10. Listen. Drop a normal. All of you quickly. If this is 10, this is normal. This is how much, and this is how much. Just think about this. Okay, just think about this. This is 90. You know that this is 90. So can you say that 2i, I and I, can you say that 2i is going to be 90 plus 10? Just a second. Drop a normal, something like this. This is the normal. Okay, this is the normal. Incident ray, reflected ray. That's fine. Angle of incidence, the angle between normal and incident ray. Angle of reflection, the angle between normal and the reflected ray. Isn't it? Yes or no? Definitely yes. So how much is going to be this particular angle? This is 90. This is 90. This is 90. And this is 10. Okay, so 100. 90 plus 10 is what? Is nothing but I plus R. And I and R are same. I and R are same. So you can say that I plus R is 90 plus 10. That means 2 times of I is 90 plus 10. That means 100. That means I is equal to 50. R equals to 50. R is equal to 50. R is also equal to 50. So you can find out this angle. Can you find out this particular angle over here? Quickly do this. This is 90. Okay, this is 90. Figure has been given to you. This has been, this is striking at such an angle that it's passing something like this. You simply need to find out the value of alpha. So what is it going to be? How much is it going to be? This angle R is 50. Okay, and this again is 90. Listen, this again is 90. This angle is 90. This much angle is 50. So this is going to be 40. So if you have a look at this triangle, this is alpha, this is 90. Okay, and what this angle is going to be? This is 40. So how much is alpha? Tell me. How much is alpha? Alpha is 50. Is this point very clear? Very nice. Okay, let's take the discussion ahead quickly. So what it says that for a given incident ray, if plane mirror is rotated through an angle theta, the image is rotated, the reflected ray is rotated through 2 theta. That means if this is the mirror, this is incident ray, this is reflected ray. Tilt the angle by theta. The reflected ray is going to change by 2 theta in the same direction. For a given mirror, if the incident ray rotated through an angle theta, then the reflected ray rotates to theta in the same direction. See, if this is the mirror, and this is the normal, okay, this is the incident ray, this is the reflected ray. Okay, if you tilt the incident ray by an angle theta, okay, the reflected is also going to get tilted, but if you move the incident ray clockwise, the reflected is going to move anti-clockwise. Okay, is this point very clear? Remember this in the opposite sense. If mirror is rotated in its own plane, then no effect of reflection. If this is the mirror, this is the light coming and going, rotate the mirror like this. That makes no difference. At all. Okay. So this is a simple question that's coming in front of you, giving it as homework. Simply what you're doing, you need to rotate the mirror. You need to find out the change in the reflected ray. Okay. Now this is a nice question from NEET 2017, a nice PYQ. This is a nice question, important. Okay, so read the question. What it says, we'll do this question. A beam of light from a source L is incident normally on a plane mirror, fixed mirror. Okay, this is a plane fixed mirror. Okay, that's cool. Okay, and this is a source, L. Incident light is something like this, striking on the mirror. Okay, the beam is reflected back at the same spot, something like this. When the mirror is rotated by a small angle theta, mirror is rotated by small angle theta. Listen, all of you, mirror is tilted by how much angle? Arya, Newton, Kanha, Kamlesh, Bhavani, Chitrali, give the answer quickly. If you tilt the mirror by some angle theta, let's say this is the mirror, rotated by how much angle? Theta. So we know that by how much angle the reflected ray is going to get tilted. It's going to get tilted by 2 theta, isn't it? It's going to get deviated by, the reflected ray is going to get deviated by 2 theta. Yes or no? Do we know this? Definitely yes. So if this separation is x, let's call this separation to be y. Okay, let's call this separation to be y. Okay, that's cool, that's fine. What you need to find out? The angle. You need to find out the angle. So you can say tan of 2 theta, okay, is going to be opposite divided by the base. For small angle, tan theta is equal to theta. So you can write simply 2 theta is equals to y by x. That means theta equals to y by 2x. That means D is the answer. Is this point absolutely clear? It was a nice question. All of you, how many of you got the same answer? No one has given the same answer. All of you are saying as B. Oh, ho. All of you are saying as B. This is what you're going to do in the NEET examination. ऐसा करोगे NEET में? Silly mistake. Simply, if you rotate the mirror, the image is rotated by 2 theta. This is x, this is y. So tan theta is equals to opposite upon base. Y by 2x. For smaller angle, tan theta is equal to theta. So this is the answer. Simple. Let's take the discussion ahead. Deviation from 2 mirrors does not depend upon the angle of incidence. This is very important. Listen, this is very important point. Okay. If these are 2 mirrors, very interesting. If these are 2 mirrors, no matter at what angle do you make the light incident on any of the mirror. If the light is striking any of the mirror at some angle of incidence theta, let's say angle of incidence I. The angle between the mirrors is theta. Okay, So what is the light going to do? It's first of all, it's going to do what? It's going to reflect over here. Okay, then drop a normal. It's going to get reflected again. So the total deviation we are talking about. What we are talking about? We are talking about the total deviation caused by the 2 mirrors. Mirror number 1 and the mirror number 2. That deviation is independent. Independent of the angle of incidence, and this is the formula for the deviation. Okay, this is the formula for the deviation. It simply depends between the angle between the mirrors. Okay, independent of I. Remember this discussion. Let's take the discussion ahead. Here we go. Image formation due to a plane mirror. So what we are talking about? Real object. Basically, what is a real object? An object from which actually the light rays are emerging. Okay, that means diverging rays. If this is a point object, actually light rays should come out from this point object. Okay, then this is what we call as the real object. Yes, definitely yes. Virtual object. What is virtual object? If the rays are converging, that means let's say this is the mirror. See, this is the mirror. Okay, this is real object. So what happens from the real object? Rays are coming out, striking and going back. Okay, going back. So this is what? This is virtual image. This is what? This is the virtual image. Okay, that's cool. But what about the virtual object? Let's say, for example, just to understand the concept, if this is a lens, okay. or let's take this kind of lens. Just a second. Just a second. Okay. Take a mirror only. Don't take a lens. Okay. Let's say these are the incident rays. Okay. So the image is going to be formed at this point. This is I. So if you extend them, you get the virtual object. That means what can we conclude? We can say, what can we conclude? We can say that for real object there is going to be virtual image, and for virtual object there is going to be real image. Okay, for a plane mirror. Remember this basic discussion. Okay. Real image converging, virtual image diverging. Focal length of a plane mirror is infinite. On converging a part of mirror, no change in the size of the image, but the brightness is changed. It can form real image of virtual object and virtual image of real object. That's what I have said. Real image, virtual object, virtual image, real object. Okay. Okay. Getting? Object and image are at the same distance from the mirror. Okay. Let's say this is the mirror. Okay, that's fine. So I'm standing over here. Who is standing over here? This is KK. Okay. I'm standing like this. So what is going to happen? What is going to be the image? The image is going to be at the same distance. And if this is KK, this is going to be something like this, isn't it? Laterally inverted. Yes or no? Definitely yes. Let's take the discussion ahead. Here we go. Now this is a very important point. The minimum size of the mirror fixed at wall of the room, in which observer at the center of the room can sense the full image of the wall behind him. Okay. That means if this is basically the mirror, and what are they saying? Minimum size of the mirror fixed at one wall of the room, in which observer at the center of the room can see his full image. Okay. Behind that particular wall. Remember, it's going to be h by 3. Okay, not h by 2. This is going to be h by 3. After this, image formed due to thick glass. Clearly, I am saying image formed due to thick glass is due to multiple reflection, in which the second image is the brightest. Plane mirror can form inverted image of real object. Image due to plane mirror as laterally inverted. What is lateral inversion? If this is K, it is going to be like this. Okay, if this is K, it's going to be like this. Remember the discussion. Okay, so here we go. Simple question coming in front of you. Read the question, all of you. 6 feet tall. What happened? Yeah. Read the question. A thick mirror. Okay. What is it saying? A thick mirror shows a number of images of the filament of an electric bulb, which is going to be brightest. Right now we have seen what is going to be brightest. The second one is going to be the brightest. Okay. After this, a tall man of 6 feet height wants to see his full image. Then the required minimum length of the mirror. That's going to be what? Simply, they are asking about the mirror which is placed in front of a man. This is the mirror, and let's say this is the man standing over here. So the simple concept that you are going to send a ray from the top. Okay, that's going to come on the eye. Second is going to come on the eye. You can find h dash. That means height of the mirror is going to be h by 2. Okay, that means 3 feet. Okay, that's going to be 3 feet. Okay. After this, if you talk about the image formation due to two plane mirrors, this is mirror number 2. This is mirror number 1. Just remember the factor. Just have a look at the factor of 360 by theta. Now, if this factor is even, the number of images, just reduce the number of image by 1. 360 by theta minus 1. When n is even. If n is odd, but the position is symmetric, that means you have kept it exactly in between the two mirrors. You have placed the object exactly in between the two mirrors. That means it is symmetric. Okay. So for symmetric situation, again subtracted by minus 1. Remember this. Okay. If it is odd and it is asymmetric. Okay. It is asymmetric. And it is non-symmetric. That means asymmetric. Okay. So simply it's 360 by theta. Okay, and 360 by theta if it is fraction. Remember this. Okay, so take the lesser integer. So let's take the discussion ahead. Now another important application, the clock system. Okay, let's say this is a clock. This is 12, 1, 2, 3, 4, 5, 6 and so on. Okay, 3, 6, 9. So if this is the time, with the hour, minute and second hand, hour, minute and second hand. Okay, listen. See, any one of you who wants to go and sleep can simply go and sleep. I'm going to finish the session. I'm going to complete the session. Okay, so it's up to you that how much sincere you are, how much questions you want to practice. I am going to deliver the 100% that I have. Okay, every single numerical, every single concept I'm going to discuss today itself. So what? So remember that for the image, like the image is going to be something like this, no? Image is going to be something like this. The time is 11 minus h is to 59 minus m is to 60 minus s. Remember this general rule. Remember this thumb rule, okay? So based upon this, try this question. Based upon this, try this question. Simply what are they saying? This is 4, 25, 37. So 11 minus 4 hours, okay? 11 minus 4 hours. And what we have written? We have written 59 minus m. 59 minus m, that means 25, and 60 minus 37. So what's going to be the answer? What's going to be the answer? This is going to be the answer. Okay, C is going to be the answer. Remember this point. After this, what? If only hour bond is given, then the image is simply 12 minus h hours. Remember this. Okay. Object is moving, mirror is at rest. Let's say this is the mirror. Let's say this is the mirror. Okay, fine. This is the mirror in front of you. Okay, that's fine. This is the object. Object can move either in this direction, okay, or the object can move parallel to the mirror, or the object can move parallel to the mirror. Okay, this is the object, this is the image. Okay, velocity of object, velocity of image, velocity of object, velocity of image. So what can we conclude? We can simply conclude that velocity of image is minus times the velocity of object, something like this. This is the velocity of object in the right, image is coming towards the left. Okay, if I am running towards the right, my image is running towards the left with the same speed. Okay, in the opposite direction, with the same speed in the opposite direction. Remember, velocity of image with respect to object is minus 2 times the velocity of object with respect to ground. That means if someone is observing from the ground, okay, this is Sontu, this is Montu, and this is Shinti. Shinti is observing the situation. So velocity of image with respect to object, relative concept, that's going to be twice the velocity of object with respect to the ground. Okay, simple. Here we go. If we talk about the sign conventions, so we take the sign conventions based upon the direction of incident light. Okay, so incident light is along this direction. If you measure along the direction of incident light, it's taken as positive. If you measure opposite to the direction of incident light, that's taken as negative. Above the principal axis, this is principal axis, it's positive. Below the principal axis, negative. Okay, remember this. If you talk about concave mirror, so focal length is along left direction. Incident light is along right. Incident focal length. So focal length for concave is going to be negative. If you talk for convex mirror, this is focal length and this is positive because this is incident light. Basic discussion, but remember that the only mistake that you can do, the only mistake that you're going to do in ray optics is about the sign convention. So just remember this. Object negative because you are measuring opposite to the direction. F positive, V positive. Okay, M equals to V by U. Here we go. Read the question what it says. The question says that an object is at 20 centimeter from a concave mirror of focal length 10 centimeter. The nature of the image is, what the question says, U has been given to you. This is concave mirror, very simple. All of you be quick, be quick, 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 quick. Oh, again, this spammer came. I don't know from where he's coming again and again. Just yeah. So here we go. Tell me the answer. What's going to be the answer? This is the concave mirror. This is the concave mirror. What has been said? That object is 20 centimeter in front of the mirror. U is given as how much? Minus 20. Focal length is how much? Focal length is minus 10 because it's concave mirror, centimeter. So what is going to be the image? What is going to be the image? This is F and this is U. Okay, it's placed at basically C. So the image is going to be formed at the same location of the same size but inverted. So real and inverted. That's what they are asking. That's what they are asking. Okay. So here we go. Let's take the discussion ahead. Here we go. Now see, what is magnification? Magnification is simply the ratio of height of the image is to height of the object. So what do you write? You write that's V by U. Okay, that's V by U. Okay, remember this. Here we go. Yeah. So read the question. What the question says. A concave mirror is half dipped in water. Focal length of portion of mirror in air is F. This is a concave lens. Sorry, concave mirror. This is a concave mirror. This is a concave mirror. And what you have did, you have half dipped the concave mirror. Half dipped the concave mirror into water. Now tell me, just think about it. It's a nice concept, okay? It's a nice concept. Think about it. What's going to happen with the focal length? Is it going to increase? Is it going to decrease? Is it going to remain same? You have dipped half of the portion into water. So for this situation, what is going to happen? What is going to happen for this situation? Is the focal length going to change? Is the focal length going to change? How the focal length is going to change? Definitely it's not going to change. It's a mirror, it's not a lens. Okay, so simply F1 is going to be equal to F2. Lot of students were saying that it's going to change, but no, definitely it's not going to change. Okay, remember this. Now see, after this, if we talk about the Newton's formula, we are going to talk about the Newton's formula two times. One in lens and another in mirror. So first of all, we are seeing for the mirror. If you talk about a spherical mirror, let's say this is a spherical mirror. Let's say this over here is a spherical mirror. This is a spherical mirror. Okay, this is the focal length, and you are measuring the object and the image. Let's say this is the object distance measured from the focal length. This is X. Okay, so the image is formed. Let's say that the image, this is F, this is C. Okay, image is formed over here, and you are measuring the image distance from the focal length. That's why what I'm saying, object distance and image distance. Object distance and image distance you are measuring from the focal length. Okay, so if you are measuring from the focal length, then what is going to be the relation for F? What is going to be the relation for F? Newton's formula, that's going to be root over X into Y. Root over X into Y. Okay, is this point clear? Now the same discussion we'll be seeing in case of the lenses. Now what about refraction? Another phenomena that's coming whenever light comes and enters a new medium. What is basically light? Electromagnetic radiation. So we know that the speed of light depends upon the medium. Isn't it? C equal to 1 by root over epsilon naught mu naught. We have seen this. Yes, definitely yes. If you talk about the speed of light in any given medium, so that's going to be how much? That's going to be C divided by 1 by root over mu r epsilon r. Just now we have seen this in the previous session. Before the break we have seen this. Yes. So we know that the speed of light is dependent upon the medium. If the medium changes, then what happens? Then frequency, phase and color. Frequency, phase and color change or not change? Do not change. Lambda is going to change. at least 10 times in the same session I've said this statement, isn't it? Frequency, phase and color not going to change, lambda change, V change, rest every parameter is going to change, isn't it? So what happens? Due to the relative change in the optical density of the medium. Let's say this is the incident light. Let's say striking this medium, and here we have change in the optical densities. So what is going to happen? The light is going to suffer a change in its path. The light is going to suffer a change in its path. Okay. Incident, refracted, angle of incidence, angle of refraction. Okay. So remember, mu1 times of sin I equals to mu2 times of sin R. This is what we call as the Snell's law. Okay. Now what if you place an object inside a medium? Let's say this is a medium. What is this medium? This is mu. This is any given medium of refractive index mu. Okay. This is any given medium of refractive index mu, and there is an object placed over here. So the ray which goes perpendicular to the surface goes as it is, but the ray which strikes the surface is going to face refraction. Definitely yes. Angle of incidence, angle of refraction. So the person who is going to observe from here, what is he going to observe? He is going to observe an apparent image. So this is the real image. This is the apparent image, isn't it? This is the actual depth. Let's call it as D. This is the apparent depth. Let's call it as D dash. Okay, let's call it as D dash. So what is going to be the apparent depth? That's simply going to be D times of 1 by mu. Okay, apparent depth is going to be D divided by mu. If we compare the triangles, we can simply find this. Okay, IR, this whole angle is going to be R, this angle is I, this angle is going to be I. Compare the triangles, you're going to find this relation. So what is going to be the shift? D minus D dash. D minus D dash. This is going to be the shift. This is going to be the shift. X. D minus D dash. Okay. Shift is going to be D minus D dash, which is D by mu. So simply shift is going to be D bracket 1 minus 1 by mu. Okay. Please maintain a good, record of these concepts and these, these formulas. These are very important. Very, 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 very important. Okay. So let's take the discussion ahead. Here we go. Okay. Another very important concept that's coming in front of you is the concept of TIR, is the concept of total internal reflection. So when it happens, TIR occurs when you are talking about a change from denser medium to rarer medium. That means the object is placed in the denser medium. If the object is placed in the denser medium, then this phenomena is going to be observed. Okay, so this is the object, okay. If this is the object, normal, what happens basically, if you send the ray at some angle of incidence, definitely what it's going to do, it's going to get refracted at certain amount of angle R. This is I, this is R. If you increase the angle of incidence, the angle of refraction is going to change, and at a particular angle, you are going to observe that the ray is not refracted, it's simply grazed. It's just gone exactly touching the surface. This point is what we call as the critical angle. This angle of incidence is what we call as the critical angle. That means the angle for which the angle of refraction is 90 degree. The angle of incidence for which the angle of refraction is 90 degree is what we call as the critical angle. Okay. So for this situation, this is mu, and let's say the mu2, that is 1. So mu1 is mu. Simply apply the expression mu1 times of sin I. Mu1 times of sin I is theta c, equal to mu2 times of sin R is 1. Okay, mu2 times of sin 90, that's 1. So sin of theta c equals to 1 by mu. Important discussion. Okay. Important discussion. One of the most important discussions of optics. One of the most important discussions of optics. So based on this, let's try a simple numerical. Let's try a question based upon this. Read the question, what it says. All of you. +4 -1. Good morning, all of you. Very good morning, very good morning, very good morning, all of you. So, what's going to be the minimum diameter of the disc? What the question says, a small bulb is placed at a depth of 2√7 meter in water. See, this is water. How much is the depth? How much depth has been given? This is the depth D that has been given, 2√7 meter. 2√7 meter. Okay. Floating opaque disc is there. There's a floating opaque disc. Okay. Over the bulb, so that the bulb is not visible. You need to hide the bulb. That means, let's say if this is the bulb, if this is the bulb, this is the normal, this is the normal. This is the point at which the light is grazed. That means after this point, there will be TIR. That means after this point, light is anyways going to be in the same medium. So the disc should be at least this big. The disc should be at least this big. Getting the point? Getting the point? This should be the size of the disc, so that it can stop all the rays which are going out. Okay. So this angle over here is theta C, critical angle. This R is equal to 90, condition of grazing emergence. This is theta C. This is theta C. Okay. Simply find out theta C. Simply find out theta C. What you can say? You can simply say that sine theta C, sine of theta C equals to 1 by mu. Okay, that's fine. So from here you find out the value of theta C. And if you find out the value of angle, or simply if you find out the value of sine theta C, what is sine? Sine is perpendicular upon hypotenuse, isn't it? You have the value of D, you have the value of base, you have the value of base. Okay. So you have tan theta, which is nothing but equal to D divided by, let's call it as R. Let's call it as R. Okay. So from here, what you can do, all of you listen. From here, what you can do, you can simply find out the value of R. Find out the value of theta. You have found out the value of theta from here, isn't it? Theta you have found. If sine theta you have found, you can find tan theta. What is tan theta? Tan theta is sine theta divided by cos theta. Sine theta divided by cos theta. What is cos theta? Cos theta is root over 1 minus sine square theta. Okay. Substitute the value of sine theta over here. Find the value of tan theta. Substitute D by R. Find R. And you need to find diameter. So diameter, just calculate it. The answer is going to be 12. Calculate it. Okay. The remaining is a task for you. After this, another important discussion. The refraction at spherical surfaces. Basically, we have these two types of spherical surfaces. Spherical surface number 1 and spherical surface number 2. Okay, and spherical surface number 2. Okay, this is surface number 1, this is surface number 2. Let's say the object is placed over here. Object, image. Okay, object, somewhere over there, image would be formed. Now students get confused. Listen, students get a lot of confusion. Sir, that rarer object is placed in the rarer medium, image is formed in the denser medium, or what such situation is this? What we need to remember? Just one formula you need to remember. Just one formula you need to remember, and every single question can be done. Listen, mu1, mu2. Okay, just remember one expression that I'm giving you. Mu2 by V minus mu1 by U equals to mu2 minus mu1 by R. This is the universal rule that I'm giving you, provided you apply this properly. Okay, everywhere applicable. I am not giving you 10 different formulas that this formula for this case, this formula for that case. No, nothing like that. Mu2 is the refractive index of the medium. It's the refractive index of the medium in which light is going, okay, in the very simple language, the refractive index of the medium in which the light is going. Mu1, the refractive index of the medium from which light is coming, okay. R simply the radius of curvature of that particular surface. Another note that you need to remember, U, V and R should be with sign convention. Okay, don't do this silly mistake. U, V and R should be with some proper sign conventions. Okay, so let's try a simple question based on this. A concave spherical surface of radius of curvature. See what kind of surface do we have? We have a concave spherical surface. Okay, concave spherical surface of radius of curvature. Straightforward I am writing it as minus 100 centimeter. Okay, straightforward I am writing it as minus 100 centimeter. Okay, so what it says, separates two media of refractive indices, What are the refractive indices? Mu1, let's write it as 1.5, and the mu2, that's been given as 4/3. Okay, that's been given as 4/3, is kept in the first medium at a distance of 30 centimeter. That means U equals to how much? U equals to minus 30. Yes or no? Definitely yes. Now only how many formulas I gave you? How many formulas I gave you for this spherical surface? Only one formula. Okay, only one formula. Just apply that one formula. You're going to get the answer. So what's going to be the formula? That's simply mu2 divided by V equals to, mu2 by V minus mu1 by U equals to mu2 minus mu1 by R. Yes or no? Definitely yes. Yes or no? Definitely yes. What is mu2? Mu2 is 4/3 divided by V. 4/3 divided by V. Yes or no? Yes. Minus mu1 by U. Mu1 is 1.5. That means 3/2. And U itself is negative. So this is plus this much. Okay. Equal to mu2 4/3 minus mu1 3/2. 4/3 minus 3/2 divided by R. R is how much? R is negative minus 100. Okay. Substitute and calculate. When you find this, you get V equals to whatever you get the answer. Okay, find the answer. I'm giving you the answer. If you calculate this, you're going to get V equals to minus of 80/3. Calculate it. Okay, calculate it. I'm leaving this task for you. Okay, concept is in front of you. Simply if you find it, you get the answer. Okay, so now we are beginning with another very important. Where are the slides? What? Just a second. No worries, I'm giving you the discussion. Listen, we are talking about the lenses. Now I'm giving you another very important discussion. We are talking about the lenses. So basically what the lens is, it's the combination of two individual spherical surfaces. Okay, lens is basically the combination of the two individual spherical surface. The way we have seen the formula for one surface, we are going to club that formula for these two refracting surfaces. And now what happens in a lens, try to understand. Okay, listen very carefully. This is surface number 1. Imagine that if there would have been no surface 2, then the rays which are coming, let's say this is the object, it would have been converged at this point, but actually there is the second surface. So what it did, it made it converge at some other point. This is the final image. That means actually what is happening? There is convergence due to both the surfaces. Definitely yes. So this is U, this is V, and what we are talking about the focal length of the lens. So remember the lens maker's formula, 1/f equal to what? That equals to mu2, just a second, by mu1 minus 1 bracket 1/r1 bracket 1/r1 minus 1/r2 Now remember that again what is mu2? Again, what is mu2? Mu2 is the refractive index of the medium in which the light is going. Mu2 is refractive index of the medium in which the light is going, isn't it? Mu1 is the refractive index of the medium from which the light is coming. R1, R2, the radii of curvature. Remember that you need to substitute R1, R2 with proper signs, okay? With proper sign. If I talk about this situation, then R1 is going to be positive, R2 is going to be negative, okay? Mu2, that means the refractive index of lens. Mu1, that means the refractive index of medium. If the lens is greater than if mu lens is greater than mu medium, then definitely the focal length is always going to be positive, because this is positive, this is negative, so this whole term is positive. Mu2 is greater than mu1, this whole term is going to be positive. Remember, very, 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 very important. Listening, all of you. Focal length for convex is going to be positive if mu L is greater than mu M. But what if the medium is inserted that is having a greater refractive index? If the medium is having greater refractive index more than the lens, that means this is the convex lens, okay, of refractive index mu L, and you have dipped this convex lens inside a medium. You have dipped this convex lens inside a medium. What is the medium? Medium is mu M, and the refractive index of medium is greater than the refractive index of lens. Then what is going to happen? Then the nature of the lens is going to change. Then the nature of the lens changes. That means the converging lens becomes diverging, because 1 by f in this situation you are going to get it as negative. That means the converging lens has changed into a diverging lens. Convex will behave as a concave, and concave will behave as a convex. Okay. Is this point very clear? Okay. So if you talk about the cutting of a lens, then definitely what is going to happen? If you cut it this way, the intensity is going to remain same. I is going to remain same. Okay. If you cut it into two halves, so what is happening? Less number of incident rays would be gathered. So brightness is going to decrease. Brightness of the image is going to decrease. That means if you cut it this way, the intensity is going to get half. Okay. Power of a glass lens in water is 1 by 4 times the power in the air. Okay. That means the focal length is 4 times the focal length in air. Focal length is going to be 4 times. Okay. Just remember. So now let's discuss the general case of the image formation due to the lenses. So we know if the object is placed at infinity, this is the lens, okay, and the object is placed at infinity, so the image is formed at the focal length, okay, at the focus. Image is a point sized image and it's a real image. Okay. Yes. Image is between infinity and 2f. Okay. That means this is f, both the sides, first and second principal focus, f. Okay. This is c. So image is formed beyond c, or let's say between infinity and c. Okay. So the object is going to be formed between c and f. The object is going to be formed between c and f. Image is going to be formed between c and f. Object, image. Okay. Something like this. What is the image going to be? It's a real, inverted and diminished. Yes, school. If the object is placed at 2f, if you place the object at 2f, okay, this is focal length, this is 2f. So the image is going to be formed exactly at 2f. That means at c. Okay. So image is formed at 2f. It's a real, inverted and enlarged. If object is placed between f and 2f, we have seen this, okay, at focus, at infinity. Now, one important case that I want to discuss, because that's the discussion of the simple microscope also. So if this in front of you is a convex lens and you place the object between F and optical center O, okay, so what kind of image formation is going to be? Send a ray parallel to the principal axis, passes through the focus, send another ray from the optical center, okay. So this is going to be the image. This is going to be the image, okay. Is this point very clear? What kind of image is this? What kind of image is this? This is virtual. This is virtual, enlarged, okay, and erect. Virtual, enlarged, and erect. Okay. Is this point very clear? Okay. Okay, that's cool. So here we go. What about the combination of the lenses? Listen. Who is this saying बंद कर रात हो गई तो भाई तू सो जाना जाके? Who is stopping you? Okay, blocked. Cool. Blocked. Okay. See. Listen. Combination of the lens. See. If this is one lens, this is another lens. Okay. So if you combine these two lenses, okay, if you combine these two lenses L1, L2, so what is going to happen? Both are going to converge. So the converging powers are going to get added. P equals to P1 plus P2. What is the relation between power and focal length? We know that power is 1 by focal length. If focal length is in meter, you get the power in diopter. Okay, diopter. Remember. So simply you can say 1 by F equals to 1 upon F1 plus 1 upon F2. Okay, plus 1 upon F2. And what if you have these lenses at some separation? What if you have these lenses at some separation? Let's say at some separation D. This is going to be D times of P1, P2 or D times of 1 by F1, F2. Okay. Remember the discussion. So here we go. There's a question coming in front of you. Read this question. All of you. Read this question, what it says. 30 seconds for this question I'm giving you. 30 seconds for this question. We are cutting the lenses. Something like this. Okay. Two plano-convex lenses of equal focal length are arranged in this particular pattern. Okay. Let's say the equivalent is F1, F2 and F3. So what is going to happen if you cut them from the center and you arrange them like this? That makes no difference. So F1, F2, F3. Okay. The ratio of the combined focal lengths F1, F2, F3 is going to be same for all three of them. Okay. Okay. Next question coming in front of you. See, what are they saying? They are saying that a lens is made up of glass, has been given focal length F. It's immersed in water. 1 upon F equals to mu2 by mu1 minus 1 bracket 1 by R1 minus 1 by R2. Okay. If you are talking about air, if the medium is air, this expression is going to be 1 by mu equal to mu L, that means refractive index of lens, divided by mu air, which is 1, minus 1 bracket 1 by R1 minus 1 by R2. If you divide them and solve, just remember the direct result that I have given you. Just remember the direct result that you are going to get. The focal length in water is going to be 4 times the focal length in air. Power in water is going to be 1 by 4 times the power in air. Okay. If you divide them, you get anyways the same answer. Remember this. Are you going to remember this? All of you? Okay. So now the displacement method that we discussed for the mirror, we are going to discuss for the lens. Okay. We are going to discuss for the lens. What we are going to discuss? The displacement method. Very important. All of you. See. If this is the screen, okay, and this is the object, and this over here is the object, okay, object, and that's the screen. Now what we are saying we are saying that there are going to be two positions, okay, at which you are going to get a sharp image. Capital D is the distance between the object and the screen. X is the distance between the two positions of the lenses. Let's say this is the position number 1, this is the position number 2, at which you're going to get the sharp image. So what are we saying? That X is the separation between the going to be the separation between the positions of the lens, and this is capital D. What is capital D? Capital D is the distance between the object and the screen. F is the focal length. So remember directly, F is equals to, you have to remember this formula. Very important, very important formula. Okay, remember the formula as it is, okay, remember it. This is very important. So is this recorded? No, this is not recorded. This is not recorded. Who is saying it is recorded? Listen now. Combination of a lens and a mirror. Now basically what the situation is, this is lens, this is the mirror. So if the light enters the system, it is going to face one refraction at the lens. Then it is going to face a reflection at the mirror, and then again a refraction at the lens. That means 2 times refractions through lens and 1 times reflection through the mirror. Remember this point, okay? 2 refractions from the lens, 1 reflection from the mirror. So the focal length is going to be 2 by FL plus 1 by FM, okay? Mirror lens. The net focal length, or you can remember it like this. Remember it in terms of power. Power, because the object is going to be twice refracted by the lens. So P equals to 2 times PL plus PM. Okay, or 1 by F equal to like this. Now, if I talk about the focal length in any of the two situations, we know that 1 by F equal to mu 2. That means the mu of lens divided by mu of air, which is 1, minus 1 bracket 1 by R1 minus 1 by R2. So what we have done, we have planed, we are making one of the surface as plane. So this is going to be infinite. This is going to be infinity. So simply 1 by F, you can write it as mu minus 1 divided by R with proper sign conventions. Remember the expression, okay? Remember the expression, just substitute with proper sign conventions, okay? So this should be negative, this is, this should be negative. Okay. Please remember, repeat the trick for focal length. Which trick? The trick that I said. You're talking about this trick. This one. This trick. This one. What we are doing in this situation, we are simply applying the formula for the focal length 2 times and we are dividing them. So this term gets cancelled out. Substitute the value of refractive index of water. You get the relation that I've written over there. Okay? You get the relation that I've written over there. So now we are taking the discussion ahead. Another important discussion coming in front of you is the discussion for a prism. So basically, what is a prism? What actually a prism is? A prism is a structure that is made up of 3 rectangular surfaces, and 2 triangular surfaces. Okay. Mahindra is asking what to do if the questions are not getting correct. So make them correct. See, find out where the mistake is. Okay. This angle over here, this is what we call as the angle of prism. Okay. Let's say the light is entering. Over here, something like this. This is angle of incidence R. Okay. Angle of incidence R. And light is refracted. And light is refracted over here. This is R1. This is R2. And this is E. R1, R2 and E. Okay. Now see, if you complete this quadrilateral, you can simply find out that A equals to R1 plus R2. A equals to R1 plus R2. And we are talking about the deviation. So the first deviation occurs at the face number 1. The second deviation occurs at the face number 2. What is the deviation at the face number 1? I am talking about the deviation. What is the deviation at the face number 1? The light wanted to go along this direction. It has tilted over here. So what is the delta? Quickly. If this is the angle I, okay, this is R1, you can say that delta 1, this is basically the delta 1. This is delta 1. So you can say delta 1 is I minus R1. Okay. Similarly, you can say delta 2. Delta 2 is I minus R2. So total delta is delta 1 plus delta 2. You are going to write I minus R1 plus I minus R2 or E minus R2. Okay. E minus R2. And what you're going to say? You're going to say that the total delta is I plus E minus R1 plus R2. That is nothing but A. That is nothing but A. Okay. So total delta is I plus E minus A. Total delta is I plus E minus A. Okay. Total delta is I plus E minus A. Just a second. Just a second. Just a second. Yep. Okay. So this is the total delta. Okay. This is the deviation. Now, if you talk about the condition of minimum deviation, now see, for every single delta, you have written, what you have written? You have written that the delta, is nothing but I plus E minus A, isn't it? That means it depends upon the sum of I and E. And listen, how much can be maximum I or how much can be maximum E? I maximum can be 90. In that situation, E will be 0. E maximum can be 90. I will be 0. That means you are going to get the same deviation. You are going to get the same delta for two values of I and E. That means if I talk about this delta for I and E, for this value of I, this value of E, delta is same. Okay. That means I get the same delta for two pairs. Okay. Getting the point? All of you. So if you talk about the minimum deviation, if you talk about the delta min, what is going to be the condition for delta min? There is going to be only one condition for delta min, and delta minimum is going to be when I is equals to E. So if you substitute I equals to E, what is going to happen? Delta min, simply you can say I plus E, that means 2I minus A. And if we apply the Snell's law, at the surface, at any of the interface, you can simply say that mu1 times of sine I equals to mu2 times of sine R. Okay. So mu is equal to sine I by sine R. Mu is equal to sine I by sine R. Mu is equal to sine I. What is I? I is A plus delta min divided by 2 whole divided by sine R. And what is sine R? If I equal to E, then R1 equal to R2 equal to A by 2. Okay, so this is sine of R. What is R? R is equal to A by 2. Remember this. R is equal to A by 2. So this is the expression for mu in front of you. This is going to be the expression for mu in front of you for delta min. Simple. If you talk about a thin prism, what is thin prism? Angle is chotu. Angle is very small. Okay, angle is small. So sine theta is almost equal to theta. So mu can be written as, this 2 gets cancelled out, A plus delta min divided by A. Okay, so you can say that, what can you say? You can say delta. You can say that delta in that situation is A times of mu minus 1. Okay, remember the expression. Okay, remember the expression. Very important discussion this is. So let's try a numerical based on this discussion. Let's try a numerical. Where is the numerical? Yeah, read this, what it says. All of you read this question, what it says. A plot between the angle of deviation and the angle of incidence is shown in the figure. From the graph, one can say that the prism angle is. What is going to be the prism angle? Quickly. Now what this question says, I, E, delta, isn't it? Delta equal to I plus E minus A. Delta has been given to you. I and E has been given to. Now you have to do it yourself. I believe that you're definitely going to get the answer. Okay. So after this, let's begin with the optical instruments. So what are the optical instruments? The first and the very basic instrument is simply the converging lens. Now, how do we use this converging lens? That is very important. That makes it an optical instrument. Okay. This is a simple converging lens. Okay. This is a simple converging lens. Now, if you place the object between the focus and the optical center of this lens, you know that the image is going to be formed somewhat over here. And what is going to be the image? It's going to be enlarged. It's going to be enlarged. Okay. It's going to be what kind of image? It's going to be enlarged image. Now there are going to be two cases. You can talk about the situation when the image is formed at infinity and when the image is formed at D, the least distance of distinct vision, that's 25 centimeter. So when the image is formed at infinity, eye is very relaxed, okay, comfortable for that, corresponding to that point. If you talk about the condition in which image is formed at 25 centimeter, that means the least distance of distinct vision. So in that situation, trained eye, and it is going to be at the near point. Okay. So what is going to be the magnifying power? Just a second. You also have a sip of water. After this, we have to do wave optics and dual nature and atom nuclei semiconductor. Kamya, yes, Kamya, everything is same. Only the difference is in the language. Okay. If we talk about the magnification in the two cases, this is going to be D divided by F. Okay. And this is going to be 1 plus D by F. Okay, that's fine. If you talk about the magnifying power, that's simply the visual angle formed by the final image. That means if this is the normal eye, if this is the object, okay, and you are trying to observe the object through your naked eye, then what angle it is subtending? In the second situation, if this is the object, this is the image. So what angle beta has been formed? So this is going to be the ratio of, this is simply going to be the ratio of, see, this is going to be the ratio of visual angle formed by final image is to the visual angle formed by the object when the object is at D, that means beta divided by L. Okay, image is to the object. Is this point very clear? So let's take the discussion ahead. Here we go. Next point that's coming in front of you is the compound microscope. So basically, what is a compound microscope? Now, when one lens is not sufficient, then in that situation, what we need to do? We need to take a combination of lens. Okay, we need to take a combination of lens. And what is that combination of lens? That combination of lens is what we call as the compound microscope. What are the important parts of this compound microscope? This is the objective, this is the eyepiece. Okay, objective, eyepiece, and you are going to observe from this point. Let's say you are observing from this point, something like this. Okay, so this is the object. What is going to happen? There is going to be formation of one image. Okay, and then what? This is the image. Just a second. Okay, see, this is the eyepiece. Okay, this is the first image which is formed somewhat over here. Okay, send the rays, extend them. So this is the enlarged image that you're getting. For the same object. So is it beneficial? Definitely yes. Is it beneficial? Definitely yes. Now what are the important points regarding the situation? If you're talking about the objective lens, the object is placed near to the objective lens. It forms a real and inverted image between the two lenses. Okay, it has a smaller focal length. Why it is having smaller focal length? Why it is having smaller focal length? Why the focal length? Mr. Pradeep, what happened? Why are you coming in between and disturbing everyone? If you are talking about the final image, then that's going to be formed due to the combination of objective and eyepiece, isn't it? Now the image which is formed by the objective is going to be magnified due to the help of that eyepiece. Eyepiece is greater. Let's break. Let's block this person. Blocked. Simple. Okay. If you talk about the eyepiece, the focal length is greater. Okay. Why the focal length is greater? Because you are observing from the eyepiece, so you need a lot of rays to be gathered. Okay. That's why it should be greater. If you talk about the total magnification, that's going to be simply the objective into the eyepiece. Okay. This is going to be, again, there are going to be two cases. What are the two cases? When the image is formed at infinity, and when the image, let's say when the image is formed at far point, when the image is formed at near point. Okay. So for the far point, what we are going to say, m is going to be simply m naught into me. M naught is going to be v naught by u naught. Okay. And this is going to be the previous result, d by fe. Okay. Near point, m is going to be, this is going to be same, v naught by u naught, but this is going to be 1 plus d by fe. Okay. Exactly the same result we are using. Okay. Is this point very clear? So this was regarding the optical instruments. Now we are going to begin with the wave optics in the next 10 minutes. Okay. In the next 10 minutes, 3:20 onwards, we are going to discuss wave optics, modern physics. Okay. Modern physics and wave optics after the next 10 minutes. Okay. Go have some water, eat something, come back. Okay. Okay. Yups. Let's get started with the wave optics. So here we go, here we go, here we go. So we are about to finish the discussion because the major portion we have cleared. Ray optics was a very big topic. Now wave optics, atom, nuclear, semiconductor, all are very small topics. Okay, so let's get started. First of all, the first concept that's coming in front of you regarding the wave optics is the intensity of wave. If I talk about the expression for a wave, so any wave can be represented as a sine of omega t plus minus kx plus minus phi, isn't it? Definitely yes. So the intensity, remember the intensity is dependent upon the amplitude, something like this, I proportional to a square. If you talk about light, if you talk about sound, for all kind of waves, this expression is valid. Okay, so I is equals to half of omega square a square rho v. Okay, it's proportional to f square. F, it is proportional to a square. It is proportional to f square. It's proportional to a square. Okay, so remember this discussion. We are saying that I is dependent upon omega square. It's dependent upon a square. Okay, it's dependent upon the frequency. We know. So simple question. Ratio of intensities of two waves is given as 4:1. Then the ratio of the amplitudes. We know that I is proportional to a square. So what's going to be the answer? The ratio for I has been given as 4:1. The ratio for I has been given as 4:1. So simply A is going to be 2:1. Simple. Simple. Next question. What the question says, electromagnetic radiation of frequency n, wavelength lambda, traveling with a velocity v, enters a glass slab of refractive index mu. Frequency, wavelength and velocity will be. Again the same thumb rule. Again the same thumb rule. Listen, frequency, phase and color never change. We know this. Do we know this? Yes, we know. So frequency is not going to change. Frequency is going to remain same. That means this and this directly discarded. Now what about the lambda? What about the lambda? We know that mu is equals to c by v, and we know that v is equals to f times of lambda. So we know that mu is inversely proportional to lambda. So it is going to decrease by this amount. This is going to be lambda divided by mu. And simply v is going to be c by mu. V is going to be c by mu. Okay. V is going to be c by mu. So this is the expression in front of you. Okay. Remember that mu inversely proportional to v, inversely proportional to lambda. This is going to be the answer. Nice question. Okay. Important. Let's take the discussion ahead. If you talk about the sources, different kind of sources, if we discuss point source, then we know that this is a point source. What is the wavefront for a point source? For a point source, we have a spherical wavefront. We have spherical, okay, wavefront. I is proportional to a square, inversely proportional to r square, and a is inversely proportional to r. If you talk about a linear source, this is a linear source. Okay. So what kind of wavefront do we have for a linear source? We have a cylindrical wavefront. We have a cylindrical wavefront. Okay. And I again proportional to a square, inversely proportional to r, amplitude inversely proportional to root r. Planar source, this is a planar source. What kind of wavefront do we have? We have a plane wavefront for this kind of source. So remember, intensity is not dependent upon r, amplitude is not dependent upon r. Okay. Let's take the discussion ahead. Now what happens? What's the basic difference between a wave and a particle? That when two waves meet, they can interfere. They can produce a bigger wave or a smaller wave. Okay. That means if the two waves which are meeting are something like this, this is wave number 1 and this is wave number 2. That means they are in same phase. So what is going to happen? The resultant is going to be a bigger wave. Okay. And if this is wave number 1 and this is wave number 2, then what is going to happen? Then what is going to happen when they meet? They form destructive interference, a smaller wave. Okay. So we can say that A net, that's going to be what? That's going to be root over. Okay, we give the amplitudes as the vector treatment, the phasor treatment, a1 square plus a2 square plus 2a1 a2 plus 2a1 a2 cos of phi. Okay, so if you talk about the maximum value of cos phi, it can be equal to 1. So a max can be written as a1 plus a2. Okay, a max can be written as a1 plus a2, and I max is proportional to a square. So remember this expression. Okay, what is going to be the condition? The phase difference, either the phase difference is 0 or the phase difference is 2 pi or the phase difference is 4 pi n pi. Okay, 2 n pi. either it is lambda or 2 lambda or 3 lambda or 4 lambda, that means n lambda. Remember this condition. Destructive interference, minimum amplitude is going to be A1 minus A2. A min is going to be A1 minus A2. Okay. So what are you going to talk about the I min? I is proportional to A square. So you can say I min is going to be root I1 minus root I2 the whole square. Something like this. Okay. Something like this. Now, if we talk about there's a simple question coming in front of you. Read this question, what it says. The interference pattern is obtained with two coherent sources of light, Imax minus Imin upon Imax plus Imin. See, intensity ratio I1 is to I2 has been given to you as n. Okay. What is Imax? You need to find out this ratio. You need to find out this ratio. You need to find out this ratio in terms of n. So take Imin as common. Take Imin as common. Simply take Imin as common. So what are you going to? Someone is spamming. That's a second. Let's block the spammer. Cool. Don't spam here. This is 3:30 already. Okay, we are so late and still you're spamming and doing all this kiddish things. So Imax is simply root I1 plus root I2 the whole square. Imin is simply root I1 minus root I2 the whole square divided by what it's going to be, root I1 plus root I2 the whole square plus root I1 minus root I2 the whole square. Simply the ratio of the term that we are talking. Solve this and calculate. One step leaving for you. You're going to get the answer. Okay. After this, the application of interference. We know that if we have two coherent sources, what are two coherent sources? The coherent sources are the sources which are derived from the same parent source. That means if this is one source, okay, and I take a cardboard, I make two slits over here. The light that is coming is going to pass through both the slits. I'm representing through different colors, okay, but it's the same light. Okay, don't get confused between these two lights. So what are they going to do? They are going to form a pattern on the screen that is in front of it. They are going to form a pattern. Okay. At different locations, you are going to get at different locations, you are going to get alternating bright and dark fringes. You are going to get alternating bright and dark fringes. Okay. At different locations, you are going to get alternate bright, dark. Okay. This kind of pattern you are going to observe. So if we talk about the situation, okay, listen. If this is the screen, okay, if this is the screen, let's say these are the slits, okay, listen all of you. This is S1, S2. The separation between the slits is a small d. The separation between the slits and the screen is capital D. So what we are doing, we are talking about the position of any given point, any general point from the central line. That's why. Now what's going to be the condition for maximum and minimum? What's going to be the condition for bright and dark fringes? Let's try to understand. This in front of you is delta x. This is the path difference. Okay, what is the relation between path difference and phase difference? Delta phi is 2 pi by lambda delta x. So in short, if you have path difference, you can find out phase difference and vice versa. Okay, remember this relation. Now, what you need to know regarding the YDSC, this is delta x dy by d, okay, delta x d tan theta from the trigonometry. And if you talk about the position of bright fringe, that means the condition of constructive interference, that's going to be y bright, I'm writing bright, that's going to be n lambda d by d, y dark, d for dark, okay, constructive, destructive, 2n minus 1 lambda d by 2d. Now, some students argue that, sir, here in some books it's written positive, 2n plus 1 lambda d by 2d. That makes no difference at all. That absolutely makes no difference at all. Why? Why so? Because if you are taking n from 1, 2, 3, then this formula is valid. If you're going to take n starting from 0, take 2n plus 1. Okay? Getting what I'm saying? In short, both the things make no difference. Okay? Both are valid. N lambda d by d, 2n minus 1 lambda d by d, it can also be plus, but remember that what values of n you are going to take. Okay? And so on. 1, 2, 3 and so on. So here we go. What is the fringe width? Fringe width is the separation. Fringe width is the width of a fringe, or simply the separation between too bright or too dark. Fringe width is the width of a fringe, or simply the separation between two brights, alternating bright and dark fringes. This is simply going to be beta is simply going to be, let's say you are talking about n plus 1th bright minus nth bright. When you do this, you get lambda d by d. You get lambda d by d. Okay, so this is the fringe width. This over here is the expression for fringe width in front of you. Now, let's summarize the discussion that we have seen. Let's summarize the discussion. We have seen that I is proportional to a square. We have seen that I is proportional to a square. Yes, and intensity is proportional to the width of the slit. What is W? W is the slit width. Okay, so remember this expression. If you talk about the net intensity, it can also be written using the half angle formula, something like this. And the maximum intensity is going to be root over I1 plus root over I2 the whole square, root over I1 plus root over I2 the whole square. The minimum intensity is going to be root over I1 minus root over I2 the whole square. Okay, if you take the ratio of maxima is to minima, if you take the ratio of maxima is to minima, this is going to be the expression in front of you. Okay, maximum intensity is to the minimum intensity, this is going to be the expression. Remember this. Okay, this is minus. Okay, this is minus, not plus. Minus over there. Okay, what happens if you immerse the setup of YDSC in a liquid of some refractive index mu? Then beta is going to get reduced by mu. Okay, angular fringe width is also going to get reduced by mu. Okay, so what we are saying, YDSC with white light, the first maxima, initially it's going to be violet. Okay, initially it's going to be the first maxima, first it's going to be violet. Okay, and then red. So just go through these points. Okay, just go through these points once again. Let's try a question. Let's try a question based on the discussion. Let's apply the knowledge that we have seen. Interference was observed in interference chamber where air was present. Now the chamber is evacuated and the same light is used. A careful observation will be. Initially what was there? Initially air was present. Okay, air has been evacuated. And what you are doing? What is there? What is the situation now? It's vacuum. Okay, you need to comment on the fringe width. ABCD. All of you. In practical ground, if we talk, we know that beta equals to lambda d by d. That means beta is dependent upon the lambda. And you know that lambda is dependent upon inversely on mu. Yes, lambda is inversely dependent upon mu. Okay, so let's say in practicality, if you talk, air is having certain refractive index, you're talking about vacuum, so this is going to decrease. If the mu is decreasing, lambda is increasing, beta is increasing. That means interference is going to happen with larger fringe width. Very good, Aryan. Very good, Arya. Very good. All of you give the answer. If you're sitting, give the answer. Okay. Let's take the discussion ahead. Here we go. Next question, quickly. In YDSC, the distance between the slits and the screen is doubled. The separation between the slits is reduced. The distance between the slit and the screen is doubled. Separation between the slits is reduced to half. Okay. As a result, the fringe width is going to become how much? The fringe width is going to become lambda d by d. This is 2, this is 1 by 2. Okay, so it is going to become 4 times. Simple. Very good. Let's take the discussion ahead. Another question. In YDSC, the separation between the coherent sources is halved. That means D. Separation between the coherent sources is halved. D by 2. and the screen from the again the same question. Oh, again the same. See, repeated concept. Can you see repeated concept? Same to same question. 2013, 2020. So simply directly we are going to give the answer as 4 times. If you get this kind of question in NEET examination, it's like a free hit for you, isn't it? It's going to be a free hit for you. Just give the answer and get the marks, okay? If a yellow light is emitted by a sodium lamp in Young's double slit experiment, it is replaced by blue light. VIBGYOR. Okay, VIBGYOR. Yellow, it is replaced by blue. So what is going to happen? This is the sequence. This is the sequence of lambda. This is the sequence of lambda. Okay. So lambda is going to decrease. Lambda is going to decrease. So beta is going to decrease. So the answer is going to be, it is going to decrease. Hey, who is saying C? Who is saying C? A is going to be the answer. Beta is going to decrease. Simple. NEET 2018. Read the question. In YDSC, what are you doing? In YDSC, what are you doing? The experiment is immersed in water. So what is going to be the angular fringe width? That's simply going to be theta divided by mu. That's simply going to be theta divided by mu. Okay. That means whatever that is 0.2 divided by 4/3, do that, you're going to get the answer. You're going to get the answer, theta by mu. Okay. Next question coming in front of you. All of you read the question, what the next question says. In YDSC, there is no initial phase difference between the light from the 2 slits, a point on the screen corresponding to the fifth minimum. Fifth minimum has a path difference. Delta x is 2n minus 1 lambda by 2. Okay, 2n minus 1 lambda by 2. Fifth minimum, n equal to 5 if we substitute over here. Delta x is 10 minus 1, 9 by 2 times of lambda. 9 lambda by 2, that means the answer is C. That means the answer is C. Okay, next topic that's coming in front of you is the diffraction. Simply, I would say that diffraction, exactly the opposite results as that of the YDSC. What basically diffraction is? When you talk about the scattering of light, okay, through the obstacle which is having, let's say this is the separation A. This is comparable to the wavelength of the light. So what's going to happen? Some light which is passing through the center is going to pass exactly straight. Okay. Some light is going to scatter. Okay, from the two edges like this and like this, and we are going to form the pattern. Okay, we are going to form the pattern at that point. So remember the expression. First of all, delta x is nothing but that's equal to n times of lambda. If you talk about the condition for minima for diffraction, that's exactly the condition of maxima. Okay, this is the condition of minima. Width exactly the same, angular width exactly the same, and this is the condition of maxima. So simply, I'm writing it over here. I'm writing the result over here. Nth maxima is going to be 2n minus 1 lambda d divided by 2d. Okay, this is the condition for maxima. This is the condition for minima. Okay, so this was very important. And one more important topic, a very short topic regarding the resolving power and the resolving limit. This question was being asked in 2018, 2013, and I think in 2021 also this was asked. Okay, if I'm not wrong, it is asked in the past 6-7 years 3 times. Resolving limit, just remember that resolving limit proportional to lambda, inversely proportional to mu, inversely proportional to sine of theta, or inversely proportional to theta. Resolving limit I am saying. Okay, and resolving power, if you talk, that's inversely proportional to lambda. Just remember these 2 points. That's it. Just remember these 2 points. Okay, that's it. So let's try a question. Let's try a simple question based on this. Read this question, what it says. Quickly read this question, what it says. Assuming the light lambda has been given to you 600 nanometer NEET 2020, the limit of resolution you need to find out. Resolving limit. What is the resolving limit? Resolving limit is simply 1.22 lambda divided by d. Sir, where is mu? Mu is equal to 1. We are talking about air, isn't it? So substitute the data and find the answer. Substitute the data and find the answer. Okay. Now see, what is Brewster's angle? What is Brewster's angle? If you talk about unpolarized light, that means the normal light that we deal with. Okay. So normally any electromagnetic radiation, it consists of what? It consists of electric and magnetic vectors which are oscillating in mutually perpendicular directions. Okay. Electric and magnetic vectors which are oscillating in mutually perpendicular directions. Let's say this is X, this is Y, this is Z. Electric and magnetic vectors oscillating in mutually perpendicular direction. So over here you have the reflected ray, you have the reflected wave, and this is the refracted ray. Okay. So the angle of incidence for which the angle between the reflected and the refracted is 90 degree. Repeat what I said. The angle of incidence for which the angle between the reflected and refracted is 90 degree. That's what we call as the Brewster angle. Okay. This is 90 degree. Okay. So remember the expression. Now the point is that if you talk about an unpolarized light, okay, that means, see, this is basically the doubt that lot of students face, that sir, when we substitute the value, let's say this is a Polaroid, okay, this is a Polaroid, okay, this is a Polaroid, this is the incident light, so when we substitute the value, we have to substitute I naught or I naught by 2. We have to substitute I naught or I naught by 2. So if you are dealing with unpolarized light, definitely while it passes from a Polaroid, this simply reduces to half. And now if you place another Polaroid in front of this polarized light, what is this light? This is polarized light. What happens with the polarized light? What is the condition? What basically polarized light is? What you're doing, try to understand. Let's have a look at the figure. You are deliberately stopping one of the two vectors that were present in the situation. See, initially it has electric as well as magnetic vectors which are oscillating in mutually perpendicular direction over here and over here. Okay. So what has happened? This is partially polarized. This is completely polarized. You have stopped the magnetic vector or electric vector. One of the two vectors has been stopped, and this is the situation. This is polarized light. Okay. This is polarized light. So what has happened with the polarized light? The intensity is reduced to half because one component has been eliminated, isn't it? One vector you have eliminated. Now if you change the angle between the two Polaroids, so the intensity is going to be this I naught is the intensity entering. Try to understand. This is the Polaroid. This is the polarized light. If you're talking about the polarized light, take the value, whatever this is. For example, this is 100 units. Take 100 units. It's entering over here, na? Take 100 units. Getting the point what I'm saying? Getting the point? Okay. So the formula is simply going to be I polarized. Whatever the intensity is of the polarized light, take that intensity times of cos square theta. Okay. Simple. So here we go. This was the discussion. Regarding the wave optics. So let's begin with the discussion of dual nature of matter and radiation. Basically, what the name suggests that we are talking about the duality involved with the matter. We know that if we talk about light, okay, if you're talking about light has always been a very controversial issue, a very controversial topic. Mr. Newton said that light is made up of particles in his corpuscular theory. Newton's corpuscular theory, okay, and everyone was convinced. But later on certain experiments were done which did not prove the particle nature of light, like diffraction, reflection, refraction, polarization, isn't it? Isn't it? Yes. So there is an experiment that we call as the photoelectric effect that proves that light is particle, because the nature of light that we are dealing with, see, there are two functions. One is continuous, another is discrete. If you talk about a tap from which water is coming out continuously, this is the continuous function. If you talk about a tap from which water is coming drop by drop, this is discrete function. So now the point arises that the light that is coming in front of you, the photons that are coming, is it a continuous function or is it discrete function? Getting? What's the argument? So the quantum theory says that the light that you're talking about is made up of discrete bundles of energy, discrete packets of energy. These are what we call as quanta. Photons. Every photon is having same energy. How much energy? Equals to hc by lambda or equal to h nu? Equal to hc by lambda or equal to h nu. Okay. If you substitute the value of h and c, this is 12400 divided by lambda. If lambda is in angstrom, this is in electron volt. Remember. Okay. What about the photons? Okay. What about the photons? The rest mass of photon is 0 because we do not discuss the mass of photon. We discuss the momentum of the photon. This is very interesting. We discuss the momentum. We discuss about the energy of the photon, but we never discuss about the mass of the photon. We take the rest mass of the photon to be 0, charge of the photon to be 0, energy of the photon equals to hc by lambda, and E can be written as equal to Pc. So P can be written as E by C. That means P can be written as h by lambda. P can be written as h by lambda. Okay. Now this is, if you write momentum of photon this much, so you can say that we can find out mass. Let's equate it with mv. Let's equate it with mv. That's wrong. That's not the mass of the photon. That's effective mass of the photon or moving mass of the photon. It's just a concept. It's just a concept because the mass energy equivalence says that delta E, that means the energy radiated equals to delta m times of c square. Delta m times of c square. Okay. That means if this is a mass, if I project it with c, this is going to get converted into equivalent amount of energy. So this is the mass equivalence. Okay. Remember it like that. So we cannot talk about the, definitely we cannot talk about the mass of the photon. Okay. So if we talk about the, if we talk about the energy of light, light is definitely made up of n number of photons. So the total energy of light is n times of h nu or n times of hc by lambda. If you talk about number of photons, so number of photons can be written as total energy divided by energy of one photon. And what is the energy of one photon? That's hc by lambda. This is the number of photons. Okay. This is the number of photons. Okay. This is the number of photons. What is the power of light beam? That's the energy falling per second. That's nothing but n times of hc by lambda divided by t. N times of hc by lambda divided by t, or n times of h nu divided by t. Number of photons per second. This is the number of photons per second. From here you can find out the number of photons per second in terms of power. Okay. I hope that this point is absolutely clear. Now the next important term that's coming in front of you, is the intensity. Intensity is simply the energy falling per unit area per unit time. That means how many photons are falling. Let's say these are photons which are coming. Okay. So this is my umbrella. I'm hiding myself from photons. So how many photons are striking a given area per second? That's what we call as the intensity. That's what we call as the intensity. Okay. Yeah. So the number of photons falling per unit area per unit time. Okay. Frequency does not depend upon the medium and the distance. This is the expression for intensity. We have already seen. So let's take the discussion ahead. Now the point is that if these photons that you're talking about, if they carry momentum, listen, if these photons carry momentum, okay, then definitely if they are striking the surface, momentum is changing, and if momentum is changing, they should exert a force. Yes or no? Yes or no? Yes, definitely yes. If this is a surface, okay, just say if this is a surface, this is the ball which is going, striking and coming back. Okay, so this is momentum P, this is minus P. So what is the change in momentum? That's 2 times of P. What is the change in momentum? That's 2 times of P. Okay, that's cool. What if the ball is being absorbed? Simply the change in momentum would be P. Similarly, if you talk about the radiation pressure, that means the pressure exerted by the photon, that's going to be I by C if the photons are absorbed, and that's going to be 2I by C if the photons are being reflected from the surface. Okay, basic thought, just remember this. Okay, clear? Clear. Okay, so here we go. Now if we talk about the photoelectric effect, basically what is photoelectric effect? Photoelectric effect, the name suggests photoelectric effect, that means electric effect of photons. Photons are coming and you are going to observe electricity. Now how it happens? Definitely electrons are going to be emitted due to these photons. Okay, so if you say that this is a metal, quickly, if this is a metal in front of you, this is the incident light, this is the incident light. Okay, so this is the work function. Work function is the minimum amount of energy. Work function is the minimum amount of energy required to pull an electron out. Okay, work function is the minimum amount of energy required to pull an electron out of the metal. So students say that the energy should be greater than work function. This is what commonly students say. This is wrong. This is wrong. Energy, not the energy of light, the energy of one electron. One photon. Energy of one photon. That's hc by lambda, or let's say hf. This should be greater than work function. Then the photoelectric effect is going to be observed. Okay, then the photoelectric effect is going to be observed. So what is the condition of photoelectric effect? That the frequency should be greater than a particular frequency. That's what we call as the threshold frequency. And the lambda should be lesser. Lambda should be lesser than a particular lambda. Okay, that's what we call as the threshold wavelength. That's what we call as the threshold wavelength. Okay, so now if you talk about the expression for photoelectric effect, if you talk about the expression for photoelectric effect, let's say this is a metal. This is a metal. Try to understand all of you. This is the work function phi. Okay, this is the incident energy, E incident, h c by lambda. Okay, so what is going to happen? Let's say an electron is being ejected from the situation. So some part of energy has gone into the work function, remaining part has gone into the kinetic energy of the electron. Yes or no? Yes or no? Definitely yes. Definitely yes. So what are we going to say? We are going to say that for this situation, the incident energy goes into the work function and the kinetic energy of the ejected electron, and the kinetic energy of the ejected electron. Okay, so what is incident energy? That's hc by lambda, or h times of f. Okay, work function, the minimum amount of energy required. Okay, that's h f naught. F naught is the threshold frequency. Kinetic energy half m Vmax square. What is the concept of Vmax? See, basically the thing is that if this is the setup, of photoelectric effect, okay, if this is the photosensitive metal, so in this situation, a lot of electrons are ejected with different velocity. So we are talking about the electron which is moving with the maximum velocity. Who is this? Asking, sir, आपने नहा लिया? सुबह ही नहा लिया था, कल ही नहाया था. तो ब्रेक कर देते हैं पगले. Yeah, so if this is the incident energy, these are the electrons, this is the electron moving with maximum kinetic energy. Okay, yeah. So now see what's the concept? If I apply battery over here, okay, listen, if I apply a battery over here, something like this, let's say this is positive, this is negative. So this electron that's coming is going to face a repulsion, isn't it? The electron which is coming is going to face a repulsion due to the two sides? Yes or no? Definitely. So if the fastest moving electron stops, the potential that you applied at which the fastest moving electron got stopped is what we call as the stopping potential. That's what we call as the stopping potential. Okay, remember this point. That's what we call as the stopping potential. So you can simply say that H times of F equals to H times of F naught plus EVS. This is the expression for photoelectric effect. Okay, this is the expression for photoelectric effect. Okay, so here we go. What are the laws of photoelectric effect? Since we know that it's a particle phenomena, since we know that it's the light that is coming is a quanta, it's a discrete bundle of energy, it's an instantaneous process. That means the time is only 10 to the power minus 9 seconds. Efficiency is very low. But what we assume? We assume that one photon corresponds to one electron. That means I am an electron. I am sitting. Energy is coming. I will take the energy and I will get something like this. Okay, so one photon corresponds to one electron. This is what we assume. Okay, expression for the photoelectric effect. Okay. Let's have a look at the graph. See, very clearly I am saying that if you talk about intensity, intensity is simply related to number of photons falling, because greater the number of photons will fall, greater the number of electrons would eject. Okay, so more number of photons, more number of electrons ejected in the situation. That means more amount of current, greater amount of current, isn't it? Definitely yes. So intensity is related to current. Okay, so if you increase the intensity, the current in the situation increases. Okay, if you talk about frequency, so what we can say, frequency is increased, so what happens? The incident energy increases. If frequency is increased, E incident, that's HF, that increases. If the incident energy is increased, then what happens? Then the kinetic energy maximum increases with which the electron is coming out. If that is increased, then the stopping potential is increased. Okay, that means frequency is related to stopping potential. But it's not dependent upon the current. I said the reverse. Current is not dependent upon the frequency. It's simply dependent upon the intensity. Okay, so this is the expression for current versus frequency, independent. Okay, all of you be attentive, all of you. Okay, it's already quite late, so I don't want you, okay, to just sit here and waste your time. If you're not getting the concept, you're wasting your time. So be alert, try to take 100% out of it. Okay, now see, I'm drawing some graphs, very important graphs. Okay, see, the first thing that's coming in front of you is this. Just a second. What we are doing? We are trying to plot the graph between current and the EMF. Okay, you know that in the situation of photoelectric effect, in the setup of photoelectric effect, even when there was no applied potential, even in that situation, there was certain amount of current. Yes, this is the incident light that's striking the electron. Okay, so there is certain amount of current in the situation. Okay, there is certain amount of current even when the potential is zero. Okay, even when the potential is zero, there is certain amount of current. If you increase the potential, that means, let's say this is positive, this is negative. If this end is positive, this end is negative, it's going to pull more amount of electrons. Yes or no? It's going to pull more amount of electrons. Yes, definitely yes. So current is going to increase with the increase in positive potential. If you reverse the potential, let's say this is negative now, this is negative now, and this is positive. So the electron is going to face a repulsion, and at a particular value of negative potential, that's what we call as the stopping potential. Finally, the electrons are going to stop. So this is the graph for current versus the EMF. Now, if I change the intensity without changing the frequency, so what is going to happen in the situation? See, this is intensity of 1, this is intensity of 2. Definitely intensity of 1 is greater than that of 2. Okay, frequency of 1 equals the frequency of 2. Therefore, the stopping potential of 1 equals the stopping potential of 2. I hope that this point is absolutely clear. All of you, is this point absolutely clear? Okay, so I'm summing up what I've said. Frequency, intensity is dependent upon the frequency. Simply, stopping potential is dependent upon the frequency. Current is dependent upon the intensity. Why? Because greater the intensity, greater the number of photons that are coming. So greater the number of electrons that are ejected. Yes or no? If greater number of electrons are ejected in the situation, greater is the current in the situation. And if you increase the frequency, what is going to happen? Incident energy is going to increase, and if the incident energy increases, then maximum kinetic energy increases. That means the stopping potential increases. Okay, absolutely clear? Done? Let's take the discussion ahead. Let's try a numerical on this. So here we go. Okay. So try this one. Read this question, what it says. Read the question, what it says. The question says that this is from NEET 2016. When a metallic surface is illuminated with a radiation of wavelength lambda, the stopping potential is V. If the same surface is illuminated with a radiation of wavelength 2 lambda, you have changed lambda, that means you have changed frequency, isn't it? So what's going to happen? Stopping potential is V by 4. The threshold wavelength you need to find out. Simply, what's the expression? Expression is E in equals to phi plus Ke max. What is Ke max? What can you say about Ke max? Ke max is nothing but, this is HF equals to HF naught. Ke max is going to be E times of Vs. Okay. So this is the expression number 1. Similarly, generate the expression number 2. Solve the two expressions. You get the answer. Okay. So let's take the discussion ahead. Now the point is that you have said that light is having dual nature. Definitely yes. So definitely the next thought that comes in our mind, that what about the particle? If light is having particle nature, do particles have wave nature? That's what we are thinking. Okay, that's what the question was. And then it was proved that yes, particles also possess wave nature. That means if this is the particle which is moving, so there is a wave associated with the motion of this particle. Isn't it interesting? Definitely yes. Isn't it interesting? All of you, no spamming. Okay, it's already quite late. In 20-25 minutes we'll be stopping the session. YouTube will be stopping the session because it will be, overtime. I think 12 hours is the limit of the session. So please be attentive. It's just short time that's remaining. We need to cover some more topics. I want to cover the topic today itself. So please be attentive. See, lambda is equals to h by p. What do we write? We write that lambda is nothing but that's equals to h by p. What is p? P is equals to root over 2 KEM. Root over 2 KEM. What is KE? KE, kinetic energy, is Q times of delta V. Yes or no? Definitely yes. Substitute it over here. Q delta V. Okay. So this is the lambda associated with the particle. Okay, this is what we call as the lambda of the matter wave. Lambda of the matter wave. Okay. If you talk about a charge in magnetic field, H divided by QBr. Similarly, if you talk about the gaseous molecules, it's H divided by root 3. H divided by root 3 MKT. Okay. And this is for electron in nth orbit. Basically, we are relating it with the energy for any given orbit. It's like this. Okay. Okay. So here we go. If you substitute the value of Hc into the expression, you get the lambda. Remember the lambda for electron. This is the lambda for the electron. What is it going to be? Lambda for the electron. This is going to be 112.27 divided by root over V. 12.27 divided by root over V. Okay, V you are going to substitute in volts and lambda you are going to get in angstrom. Okay, is this point clear? Remember. Okay, so here we go. Just a second. Now, the next thing that we need to discuss is the atom. So here we go. See, the point is that there were different models. First of all, Mr. Thomson's model, what it said that Mr. Thomson said that the atom is simply the structure like that of a plum pudding. That means what is happening in the atom, there's complete positive charge distributed and there are negative charges embedded. Okay, there are negative charges embedded within the system. But definitely if that is the system, it's highly unstable system, it cannot prevail. Okay, that model was discarded. After that, Rutherford's model. What was the Rutherford's model? The alpha ray scattering experiment. But there were again some limitations of Rutherford model. It could not explain the stability of electron in an orbit. We know that if let's say this is the nucleus, and this is the electron orbiting around the nucleus. So if the particle is in circular motion, it is continuously having a centripetal force, isn't it? It is having centripetal acceleration, and if the particle is having centripetal acceleration, it's going to radiate energy and finally it's going to collide with the nucleus. So why it does not happen? Mr. Rutherford could not explain this. Okay, this was the limitation of Rutherford's model. So came Mr. Neil Bohr. What he said, he gave postulates and he said that if you apply my postulates, if you agree with my postulates, these concepts can be explained. It's not a universal rule, to be very clear, it's a postulate. Okay, and we are assuming the motion of the electron around the nucleus to be what? To be circular. Okay, we don't know what the actual motion is. Okay, but according to Bohr's model, it is circular. So if it is circular, let's say this is hydrogen or hydrogen-like species. This is the electron. Okay, so what we are going to say? We are going to say that the centripetal force required for the motion is provided by the required electrostatic force. Definitely yes, and you are going to say that centripetal force m v square divided by r equals to k q1 q2 divided by r square. Definitely yes. So r gets cancelled out. You are going to say r is nothing but k z e square by m v square. Okay, this is the expression for the radius. Now the point is what Mr. Bohr said. He said that the angular momentum of the electron in this orbit is quantized. Okay, and the total circumference of the path of the electron is going to be an integral multiple of its wavelength. That means it's going to be either lambda or 2 lambda or 3 lambda, lambda, 2 lambda or 3 lambda or n lambda. That means 2 pi r equals to n times of lambda. Okay, angular momentum is conserved. mvr is going to be integral multiple of a quantity, that's h upon 2 pi. Okay, so using these two what we can do, we can find out the expression for radius, velocity, time period. Now let's just go through the 3 points. Okay, regarding the Bohr's atomic model. Electron revolves in stable orbit. Okay, the orbit in which the electron is revolving, this is a stable orbit. Why? It's not radiating energy. Mr. Bohr could not explain this. He just said that these orbits are stable orbits, and what is important regarding these orbits? The angular momentum is conserved. That means MVR is going to be n times of h upon 2 pi. Okay. Photon emits due to the transition of electron from higher stable orbit. That means, let's say there's an electron, there is an electron in a lower orbit, there is an electron in the lower orbit. Okay, there is an electron in the lower orbit. Okay, and what you're doing, you are providing certain amount of energy, to this electron, so it goes to the higher orbit. But in the higher orbit it is highly unstable, so in 10 to the power minus 8 second it comes back. And when it comes back, what it does, it radiates energy. How much energy it radiates? It radiates E2 minus E1. Okay, it radiates this much amount of energy. That simply, if you calculate this, hc by lambda equals to, the energy difference between the two, you get the expression 1 by lambda equals to r bracket 1 by, after solving, energy is negative, so this is 1 by n1 square minus 1 by n2 square. Okay, this is the concept. This is the concept of the electron emission. Now see, let's generalize the discussion and let's have a look at the various parameters. This slide is very important. I want you to remember this slide as the summary. Okay, this is a very important slide. If you talk about the radius of any given orbit, that's going to be 0.53 times of n square by z. Okay, 0.53 times of n square by z. Okay. If you talk about the velocity, v naught times of z by n, that means v is dependent upon z by n, r is dependent upon n square divided by z. Okay, that's fine. If you talk about the time period, it's going to be, let's call this constant t naught, times of n cube by z square. Inverse of time period is frequency. Okay, remember this discussion. Potential energy, the magnitude of potential energy is twice the magnitude of total energy. The kinetic energy is equal to the total energy magnitude wise. Okay, and the total energy is negative, potential energy is also negative, kinetic energy positive. What is the meaning of total negative energy? It means that the system is a bound system. That means the electron cannot leave the nucleus. This is what we call as the bound system. Every bound system has total energy as negative. Remember this discussion. Okay, so this is the ratio of the energies, kinetic, potential, and the total energy. Okay, so here we go. If you talk about the energies of different orbits, you have simply said that it's inversely proportional to n square. That means E equals to minus 13.6. If it is hydrogen, Z is equals to 1, n square, substitute n equal to 1, 2, 3, 4, 5, you get these values. Okay, you get these values. Now corresponding to different orbits, okay, that means to which orbit you are coming and from which orbit. Let's say you are coming to the first orbit. Okay, from any orbit, if you are coming to the first orbit, it's called Lyman series. From any orbit, from any higher orbit, you are coming to n equal to 2. This is Balmer, Paschen bracket, and so on. Okay, just remember this basic discussion. So here we go. Read this question, what it says, a simple question coming in front of you. What the question says, the ratio of kinetic energy to the total energy. You know that the kinetic energy to the total energy magnitude are same, but the total energy is negative. So the answer is going to be what? The answer is going to be 1 ratio minus 1, isn't it? After this, if you talk about the radiation, okay, X-ray radiation, just remember continuous and characteristic X-ray. The thing is that if you are talking about a system, let's say this is the nucleus, okay, these are the electrons which are revolving around the nucleus. Okay, so if this is the incident energy, okay, if you have sent some particles, they are going to get deviated from the positive charge, and if they are deviating from the positive charge, something like this, one kind of X-ray is going to be a continuous X-ray due to this motion, and it might be possible that some electrons get ejected from the system due to the collision of particles with these electrons. In that situation, it's going to be characteristic X-ray. That means two types of X-rays are possible. Remember the same expression, nothing new for this. One important point, the relation between frequency, okay, That's root f equals to z minus b. Z is the screening constant, k alpha and k beta. Okay, just a second, let's have a sip of water. All of you, all of you, all of you. Yeah. Minimum wavelength of X-rays produced by electrons accelerated through a potential difference V is proportional to, we know that it's inversely proportional to, right now we have seen that it's inversely proportional to V naught. Okay, it's inversely proportional to V naught. So the answer is going to be inversely proportional to V. Okay, simple question, all of you, simple. So let's take the discussion ahead. Let's begin with the next concept. We have covered the concepts of atom, now the concepts of nuclei. So what basically a nucleus is? What basically the nucleus is? From the Rutherford's alpha ray scattering experiment, we found that we found that the central part of the atom is a very dense matter in which maximum of the mass, 99.9% of the mass and whole of the charge is concentrated, whole of the positive charge is concentrated. Yes or no? Definitely yes. So basically the thing is, see, this is the nucleus. What basically a nucleus consists of? It consists of nucleons. Okay, it consists of nucleons. Okay, now see if you talk about the structure of a nucleus, what is going to happen? What we are going to discuss? If this is a nucleus, it consists of proton, neutron, neutron. Okay, just for example, how we represent it? We represent it by X, Z, A. What is Z? Z is the number of protons and A is the number of protons plus neutrons. That's what we call as the nucleons. Now the question arises that we know that energy is related to mass, something like this. Delta E equals to delta M times of C square. Yes or no? Definitely yes. So why this nucleus is stable? Why this nucleus is stable? Why so stable? This is the big question in front of you. Why this nucleus is stable? Inside this there are protons which are facing a repulsion. Definitely yes. Still this is intact. How? Reason is the nuclear force. See, inside the nucleus, between the nucleons, no matter what nucleons are you talking about, proton, neutron and neutron. There is presence of a force. That's what we call as the nuclear force. Okay, this force bounds the whole system. Okay, and this is the strongest force. We'll be discussing the properties of this force, but the point was that if these individual constituents are forming a nucleus, definitely the system should be stable. And if the system is stable, then it has released certain amount of energy. So in what form the energy has been released? The energy has been released in the form of mass defect. This is the concept of mass defect. Okay, delta M times of C square. What is delta M? Delta M is whose mass should be greater? Definitely this mass should be greater. This mass should be smaller. So energy is released in the form of mass, isn't it? So mass defect is the difference. The mass defect is the difference between the mass of constituents. That means number of protons, Z, into mass of protons, plus number of nucleons into mass of nucleon. Okay, we measure it in AMU. Okay, this is A minus Z times of mass of proton. Let's take it proton minus the mass of the nucleus. This is delta M. This is delta M. Okay, this is delta M. Okay, remember this. Now if we talk about see, if we talk about the size of the nucleus, then definitely the size is proportional to its mass. Yes. Okay. R is proportional to a to the power 1 by 3. Okay. If proportionality is removed, you get a constant R equal to R naught into a to the power 1 by 3. Okay. R equal to R naught a to the power 1 by 3. So simply you are going to get R1 upon R2. R1 upon R2 is A1 upon A2 to the power A1 upon A2 to the power 1 by 3. Okay. Remember this. Okay. Basic discussion. Apart from this, if you talk about the nuclear density, now this is very interesting. If you talk about the nuclear density, this is going to be total mass. That means A times the mass of nucleon, okay, nearly same in AMU, divided by the volume. Volume is what? What is volume? That's 4 by 3 by R cube. R cube is R naught cube into A. Okay. So this A gets cancelled out. That means density is independent of A. Oh, these people come. Talk it again. Okay. Yeah, cool. It's independent of A. Okay. So do this simple question quickly. Do this simple question fast. Two nuclei have mass numbers in the ratio 1:3. The ratio of the nuclear densities, you're not going to get full. This is going to be A. Okay. This is going to be A. Next question in front of you is this. This is aluminium. This is aluminium. A has been given to as 21 and A2 has been given to you as 125. What has been asked? What they are asking? They are asking the radius. Okay. R1 has been given to you. R1 has been given to you. R2 you need to find out. So simply what you can do, R2 divided by R1 equals to A2 divided by A1 to the power 1 by 3. Simple. Okay. Do this, find out the answer. Okay. Cool. After this, the concept of mass defect. So we have seen the concept of mass defect. This is the total mass of constituents. This is the total mass of constituents. This is the mass of the nucleus. This is the mass defect, and this is going to be the energy. Remember, the energy released is 931 MeV. Okay. Just a second. Is 931 times of delta M MeV. This is in AMU. Okay, this is in AMU. The energy you get is in million electron volts. Okay, the energy you get is going to be in million electron volts. Quickly, the next question. The energy required to break one bond of DNA is this much. This is valid in EV. This value in EV is nearly going to be this value in EV. Now see, energy has been given to you as 10 to the power minus 20 joule. What is 1 electron volt? What is going to be 1 electron volt? Substitute the value of electron is 1.6 into 10 to the power minus 19. Okay. E. Okay. So this is going to provide you the energy in joule. Just substitute and get the answer. Okay. Let's get ahead. Let's get ahead. Now, the concept. Before that, let's do one more question. The energy equivalence of 0.5 gram of a substance. Now see, they are talking about the 0.5 gram of a substance. Okay. So simply, this is not in AMU. This is not in AMU. Convert it into kg. That means 0.05 into 10 to the power minus 3. This is delta M. Okay. So E is going to be delta M 0.5 into 10 to the power minus 3. NEET 2020 times of C square. C square is 3 into 10 to the power 8. The whole square. Okay. So this is going to be the answer for energy release. Just calculate and find the answer. So here we go. The next concept is the concept of binding energy. Now we can define binding energy as the amount of energy that should be taken away from the constituents, so that it forms a nucleus, or the amount of energy that should be given to the nucleus, or the amount of energy that should be given to the nucleus so that it splits. Just general example I am taking. Okay, the amount of energy that should be given to the nucleus so that it splits into the individual constituents. Okay, and that's going to be how much? That's going to be delta M times of C square. Okay, So let's take the discussion ahead. Let's take the discussion ahead. Here we go. Yeah, what the question says, the question says that mass of 3Al7 nucleus is this much AMU, okay, less than the sum of the masses of its nucleons. Okay, that means by default what has been given, delta M has been given to you. Delta M has been given to as 0.042 AMU. That's cool. Okay, now what they're asking, binding energy per nucleon of lithium nucleus is nearly. Binding energy per nucleon of lithium nucleus, you know that if you talk about 1 AMU, if delta M is equal to 1 AMU or 1 U, the energy is going to be 931 million electron volts, isn't it? 931 million electron volts. If you talk about the first situation, what is going to be the binding energy per nucleon? That's simply going to be binding energy per nucleon. That's going to be the binding energy divided by 7. So how much that is going to be? Delta M C square divided by 7. Delta M C square divided by 7. Okay, calculate and get the answer. After this, if you talk about the binding energy per nucleon, just remember, okay, before this let me give you the curve. Okay, the curve for binding energy per nucleon, goes something like this. It goes something like this. You don't have to mug up the curve. Okay, the only thing that you need to remember that this is Fe. Okay, the isotope of iron which is having maximum binding energy per nucleon. Okay, maximum binding energy per nucleon. That means that is maximum stable. Next question coming in front of you. Read the question quickly. Read the question. What it says. How does the binding energy per nucleon vary with the increase in number binding energy per nucleon of nucleons? So what was the graph? This was the graph. So what happens? It first increases and then it decreases. Okay, first it increases and then it decreases. Okay, let's take the discussion ahead. So here we go. What the question says: Mn and Mp represent the mass of neutron and the proton respectively. An element having a mass M has n neutrons and z protons, then the correct relation will be, see, the mass of the nucleus, is lesser than the mass of the constituents. Individual constituents. That means what are the constituents?